Hello everyone, welcome to this LangChain Masterclass, a complete, beginner-friendly, to absolutely advanced journey into building powerful AI applications and agentic systems. In this series, I'm going to take you from very basics of LangChain all the way to advanced concepts like agents, tool calling, routing, rack systems, LangGraph workflows, and even full production deployment using LangServe. So, if you follow every episode step by step, you'll not only understand LangChain, but you'll also be able to build real world AI projects and products that stand out in the industry. And this series can be extremely fruitful for anyone aiming to master modern AI development. So let's begin by answering the most important question first. What exactly is LangChain? So LangChain is a framework which is built to help you build applications powered by large language models. So instead of writing the raw API calls and manually managing prompt, memory, and tools integration, LangChain can give you a structured way to build complete AI systems. You can think of LangChain as a toolbox, or even better, you can think of it as a blueprint that helps you connect models, tools, and data in a clean and scalable way. So when you work directly with LLM APIs, everything becomes manual. You need to manage prompt, handle long context, integrate external tools on your own, and orchestrate multi-step workflows by hand. But LangChain solves all of that. LangChain makes your application modular, adds built-in memory, supports complex reasoning workflows, and reduces a massive amount of boilerplate code. It also standardizes patterns like RAG, tool calling, and agent calling, so you don't have to reinvent the wheel every time. In short, you can say that LangChain lets you focus on what you want to build, not how to wire everything together. So these days, LangChain is used everywhere from small personal project to large enterprise systems. Some popular use cases include document-based chatbot, which are also known as RAG chatbots. They're also used as research and automation agents, also used in multi-step workflow pipelines, data extraction and summarization, SQL agent for business analytics, and full AI assistance and AI-powered products. So if you've ever wanted to build your own AI product, LangChain is one of the best frameworks to learn in present context. So why don't we just use raw API calls? So with raw API calls, we'll be responsible for everything like I said, prompt, memory, state, workflow logic, and integrations too. So it works for very small script, but it becomes messy and unscalable when we try to scale it very quickly. So LangChain, on the other hand, gives you the following features here. It gives you a cleaner abstraction. It also provides you a built-in memory. It also provides you a platform to easily integrate vector databases and APIs. Also, you can build tools and agents, and then it also provides you a better structure for large applications. So this is why modern day AI apps rely totally or maybe in most cases rely on LangChain as a foundation and not raw model calls. So the ecosystem of LangChain has also grown far beyond just LangChain here. So we now have LangChain, which is the most powerful or the core framework for building LLM powered apps. And then we have LangGraph. So LangGraph is a powerful graph based workflow engine for building reliable agent systems. And then we also have LangServe, which can also be used as a deployment layer that turns our LangChain or LangGraph pipelines into our production ready APIs. And in this masterclass, we will be covering all of them. So that's what you can expect from this complete LangChain masterclass. The series is chosen to be progressive, meaning every episode builds on the previous one. So if you follow along, practice the code, and build the mini projects with me, I promise you'll walk away with the skills to build real world production grade AI applications. Welcome back to the LangChain Masterclass. In the previous video, we talked about what LangChain is, why we use it, and how it fits into the modern AI development ecosystem. And today in episode 2, we're getting our hands dirty. This video is all about setting up your development environment so that you can start building real LangChain applications with me. And by the end of this video, you'll have everything installed: LangChain, Gemini, and Llama models, your environment variables configured, and you'll run your very first Hello LangChain pipeline using both Gemini and Llama models separately. So if you follow these steps exactly the way I show them, you will be fully ready for the rest of this series. No confusion, no missing dependencies, and no setup issues later. So let's start by installing LangChain and the model libraries we'll use throughout the course. First of all, we're going to create a virtual environment, and for that, I'm going to open a terminal. So, Python venv and then provide your virtual environment name. So as you can see, my venv virtual environment is created, or the folder is created. After this, I can activate my virtual environment easily using my venv scripts activate. Okay, so the virtual environment is activated too. Let me go to my requirements.txt file, create a file there, and then I'm going to list down the necessary libraries that I will need. So here at the first, I'm going to need LangChain, then I'm going to need LangChain core, LangChain community, then I will need LangChain Google Gen AI, and also LangChain Grok. Okay, so these are the 5 libraries that I'll be using. So let me install these libraries through the requirement file. So pip install -r requirements.txt, run them, and then it will take some time for the requirements to be installed. Meanwhile, what I will need is I will need a new file called .env file, and inside this file I am going to create two different keys here. So one will be for Google API key. This is going to store my Google API key, and then another is for Grok, and then I'll be declaring Grok API key here. So these two keys will be essential for loading the Gemini model as well as the Llama model using Grok. So now that the requirements are almost installed, what I'm going to do is I'm going to create my API key and then paste my API key from here. Well, I'll not show you the API creation part. You can do it on your own, but I'll tell you from where you can create your API key and then paste it in your .env file. So you can get your Google API key from this ai.google.dev/AI Studio link or Google AI Studio, and then you need to sign in, and then you need to get your API key and then paste that Google API key in your .env file. Also, you can create your Grok API key from Grok console that you see here. I've already logged in. You just need to create this API key and then paste it on your env file. I'm not going to show you my API key, obviously, for security reasons. So let me prepare both my API keys and then I will start the code next. Now that I prepared both of my API keys and then pasted it into .env file, I am ready to start my code. So for that, I'm going to create a folder called introduction, or let me call it basic LLM. And then inside this, I'm going to create two files, one for Gemini LLM.py, and then other for open. Sorry, let me create a new file here again, new file, and then the next is grok llama.py. Okay, so let me start with Gemini LLM.py. So let me first import the necessary libraries. So first of all, I'm going to pull up LangChain underscore Google Gen AI, import chat Google, import chat Google generative AI, and then from .env import load.env. Also, I can call this function load.env that loads my credential from the env file. Then I will be using this uh, Gemini model here. So my model name is going to be Gemini 2.5 flash model. Then let me create a basic pipeline here. So I'm going to invoke my LLM model with a message. Hello LangChain, explain yourself in one sentence. So basically I need to invoke this with an LLM, not a model, because my model is loaded in an LLM variable. Now I can print my response here. Okay, now open the terminal again, and I can basically run this particular file here. So to run it, what I'm going to do is let me clear this and then do Python 1.basic LLM and 1.Gemini LLM.py. So if I run this script, then I should get a response from this particular LLM here, or the Gemini 2.5 flash model here. Okay, so it has provided me an answer, but you can see the answer in a very long format. It has a lot of things here in its answer. But if I just want to, okay, first we'll analyze what it has sent. So at first we see a content which contains the actual answer that we've asked for the model to provide. Then we have additional key arguments. It doesn't have anything inside that. Then it has response metadata. It has prompt feedback, block regions, safety ratings, finished region, model name, safety ratings, model provider, and then an ID with which we can track our conversation later on, and then uses metadata here. So the total number of tokens that I had inputted was 12. The output token number is 755. The total tokens utilized is 767, and yet there is also a reasoning token for output token details, reasoning 726. So we have a lot of content here, but if I want to filter out simple stuff, just the answer from the model, then I can just do response.content and then basically run it again. It will only provide me the answer I'm looking for without any additional information like these additional keywords or any kind of metadata. Okay, so when I've asked explain yourself in one sentence, the model replies, I am a framework for developing applications powered by large language models, enabling them to connect with external data sources and computational tools through chain of components. Okay, so this is a very basic LangChain pipeline with Gemini model. We're going to do the same with our Grok model too here. So using the Grok model, I can again do the same. So from LangChain underscore Grok, I can import chat Grok. Then from .env, I can import load.env. I can load my Grok API key here, and then basically define a model here. Model equals to chat grok. I'm not sure on the model, so let me try one. Llama model, let me call 8 billion llama model 18192. Okay, so let me use this model and see if it's available or not. If it's not, then we will try to change it into something else. So I will invoke the model here with my model.invoke function, and then I'm again going to pass the same sentence. Hello LangChain, explain yourself in one sentence. And then I'm going to see response.content, because printing only response will give me a lot of other additional content too, but I'm just interested in the answer here. So clear this output. Let me save this and then run this. So Python 1 basic LLM 2 grok If the model is not available, then we should see some error here, but if it is, then I'm sure we get an answer. Okay, as I told you, the model llama 8 billion 8192 does not exist, or I do not have access to it, so I will have to use some other model that can be easily accessed here. So here I've changed the model to llama 3.1 8 billion parameter instant model, and then let me run my code again with this particular model here, and as you can see, I get my answer from the llama model that is initialized using the chat grok class from LangChain underscore grok library. So the answer is, I'm a large language model and my primary function is to process and respond to human language input by generating human like text and so on. So this was a very basic coding exercise for building LLM pipeline, or for building large language pipeline with LangChain. So in the upcoming videos, we're going to go to more advanced stuffs in LangChain through our coding exercises. Welcome back to LangChain Masterclass. In the previous videos, we learned what LangChain is and how to set up our environment with Gemini and Llama models. Now, it's time to dive into the fundamentals of building LLM-powered applications. In this episode, we'll cover the core concepts that every LangChain developer must understand. Tokens and context windows to understand how LLMs see and process your input. Chat models versus base LLMs to understand when to use which and why. Prompts with system, user, and AI messages to understand the building blocks of conversations, and structured outputs in JSON mode for predictable and program friendly responses. And by the end of this episode, you'll understand the key mechanics behind LLM apps and be ready to start building structured conversational AI workflows. So let's get started with the first topic, tokens and context windows. Let's start by talking about tokens, one of the most fundamental concepts in working with LLMs. Tokens are essential units of text that the model processes. You can think of them as the building blocks of the input text you give to an LLM. So a token can be a whole word, it can also be a subword, or even a punctuation mark here. For example, if you take this text hello world, here the tokens are the word hello, world, and this punctuation mark. That makes a total of 3 tokens. It is important to note that tokens are not the same as characters. One token can include multiple characters depending on how the model's tokenizer splits the text. And understanding token is crucial because LLM processes one token at a time, and things like context, window limits, cost, and response length are all measured in terms of tokens. Now that we understand what tokens are, let's see why they matter. So LLMs process everything in tokens, like I said. That means both your input and the model's output are counted in tokens. And this is important because the cost and the response length are measured in tokens. The longer your input or the longer your response, your request, the more tokens the model uses, which can increase computation cost. Additionally, every model has a maximum number of tokens it can handle at once. known as the context window. So let's dive detail into what a context window actually is. So the context window is a maximum number of tokens a model can see at one time. It determines how much text the model can consider when generating a response. So if your input plus the expected output exceeds the context window, the model cannot access the older tokens. This means it might forget earlier part of the context. For example, GPT-4 model comes in versions with 8,000 token and 32,000 token context windows. A 32,000 token window can roughly handle 20 to 25,000 words, enough to process long document or multi-turn conversations. And understanding tokens and context window is essential because it helps you structure prompts efficiently and avoid cutting off important information and manage cost while working with LLMs. Now that we know what tokens and context windows are, let's look at some of practical implications for building LLM applications. First, we always try to keep our prompts concise. So shorter prompts are more efficient, they use fewer tokens and reduce computation cost. Second, when working with large documents, it's a good idea to split the content into smaller chunks. This allows the model to process each part effectively without exceeding its context window. And LLMs cannot remember text beyond their context window unless you use some memory augmentation features. That means they can forget earlier part of a conversation or document if it's too long. And this is especially important in applications like Retrieval Augmented Generation or RAG. In RAG, you feed the model relevant chunk of text from your document so it can provide accurate answers without needing to see the entire document at once. So by understanding the token and context windows, you can design more efficient prompts, manage long text, and even build smarter LLM applications. Now that we've covered tokens and context windows, let's move to understanding the difference between the LLMs and chat model, which is a crucial concept for building effective AI applications. First of all, what is a language model or LLM? A large language model is trained on massive text dataset to predict the next token in a sequence. So essentially, it learns patterns in language so it can generate coherent text, answer questions, summarize content, translate languages, and even more. Some popular examples of such large language models include GPT-3, Llama 2, Falcon, and Mistral model. The key feature of LLM is that they are general purpose models, and with the right prompt, they can handle a wide range of tasks, but they don't inherently understand conversation structure or roles. Now, let's look at chat models. A chat model is essentially an LLM that has been fine-tuned for conversation context. It is trained on dialogues with specific roles like system, user, and AI, so it knows how to respond in a coherent, context-aware manner across multiple turns. Example of chat model includes ChatGPT and Gemini Chat and also Llama 2 Chat. The key feature of chat models is that they are optimized for interactive multi-turn conversations. They can remember the flow of a dialogue, understand roles, and produce more natural conversational responses than a standard LLM. Understanding the difference between a LLM and chat optimized model helps you choose the right model depending on whether your application requires a single turn text generation or multi turn conversational AI. So, to summarize the difference between LLMs and chat models, here's a quick comparison. In terms of training first, LLMs are trained on general text dataset while chat models are trained on dialogue dataset with reinforcement learning from human feedback or RLHF. LLMs are ideal for cases like text generation, summarization, and translation, while chat models excels at conversational AI and agentic applications. The input to an LLM is a plain prompt, while the chat model expects a structured message including system, user, and AI roles. And in terms of output, LLM produce a single text block while chat models generate coherent multi-turn responses that maintain the conversational flow. In terms of context handling, LLMs only see the current prompt, while chat models naturally maintain context across multiple turns. And finally, there are examples which we have already talked earlier. So in short, LLMs are used for single turn tasks, while chat models are used for multi-turn interactive applications. Let's look at a concrete example to understand the difference between a base LLM and a chat model. So, in case of base LLM, if we give a single prompt like explain how a black hole forms in simple terms, the model might respond a black hole forms when a massive star collapses under its own gravity, and so on. Notice that the response is direct and informative, but it does not have a conversational tone. Now, using a chat model, we structure our input as messages. So you see that we have a system message saying you are a friendly AI tutor, and then you have a user message saying explain black hole in simple terms. So the output here is sure, imagine a star so heavy that its gravity pulls, and then and so on. Here, the chat model output seems more conversational, role aware, and friendly. It responds according to the system instructions, making it ideal for interactive applications. So, when do we use LLMs and chat models? We use LLMs for general text generation, summarization, translation, or code generation. And then we use chat models when we need chatbots, multi-turn dialogue, personal assistant, and agent that require structured conversations. The key advantage of chat model is that they understand and maintain roles, system, user, and AI, which is essential for building agentic applications or any system that requires coherent multi-turn interactions. Now let's dive into prompts, another key concept for building LLM applications. So a prompt is basically the input text or message you give into an LLM or chat models to generate the response. In chat app-based applications, prompts are often structured as messages with specific roles, which helps the model understand context and respond appropriately. There are three main roles to know. The first is a system message or the system. So the system message defines the AI's behavior, personality, or rules. For example, if you say you are a friendly tutor that explains complex topics simply, you are explaining the AI's behavior or rules, upon which you'll add some more questions and then send it to the bot or the model. The second is the user message. The user message is where you provide instructions, questions, or request on top of your system message. So for example, if I say you are a friendly tutor that explains complex topics simply as a system message, now in terms of user message, I'm going to provide explain quantum physics in simple terms. And then the third is the AI message. The AI message represents the model's previous response. It is used to maintain context in multi-turn conversation. So for example, when asked explain quantum physics in simple terms, maybe the model starts responding quantum physics studies the behavior of particles, and so on. So by clearly structuring your prompts using these roles, you can control the AI's tone, maintain conversation flow, and handle multi-turn conversations much more effectively. We will look at a practical example of a multi-turn chat to understand how system, user, and AI messages work together. So consider this chat history here, where we have a system message saying you are a friendly AI tutor. You have a user message asking to explain black holes in simple terms. So we have an AI message giving us or explaining what a black hole is. And then we have a user message saying, can you give an analogy for kids here? So when the AI generates its response after this particular chat history, it might say, sure, imagine a whirlpool in the ocean that pulls in everything around it. That's similar to a black hole in space. So here's what's happening in this example. The system message is setting the AI's tone and behavior. In this case, it ensures the AI responds in a friendly teaching style. User message provides instructions or questions. They guide what the AI should respond to next. And AI messages store previous responses, allowing the model to maintain context across multiple turns. This structure is essential for building chatbots, tutoring systems, or any other conversational AI that needs to handle long, coherent dialogues. And by using system, user, and AI messages effectively, you can create AI applications that feel natural, responsive, and context aware. So at the end, we'll quickly go over some best practices for creating effective prompts in LLM applications. First, we always define our system instructions very clearly. This sets the AI tone, behavior, and the rules it should follow throughout the conversation. Next, we make sure our user messages are specific and concise. Clear instructions helps the AI generate accurate and relevant responses without confusion. In case of multi-turn conversation, it's important to store AI messages so the model can maintain context across multiple interactions. This allows chat models to interact or to respond coherently even in long dialogues. And additionally, keeping prompts concise helps the model stay within the context window limits, preventing older messages from being forgotten and avoiding overloading the AI. So by following these best practices, you can ensure that your chat models remain coherent, context aware, and efficient, which is critical for building professional AI applications. And finally, let's talk about structured output, often called the JSON mode, which is a powerful way to make AI responses easier to work within applications. So, what are structured outputs here? Structured outputs are responses formatted in a predictable, consistent way, usually as JSON instead of free-form text. Why is this useful? Because it makes responses easier to parse, validate, and use programmatically. And structured outputs can also be directly fed into applications like database, dashboards, or other software without needing extra processing. But why use JSON mode specifically? So while LLMs naturally generate plain text, many applications require specific fields. For example, you might need a book's title, author, and publication year in separate fields. By using JSON mode, the AI has a consistent structure, making it predictable. It reduces errors when extracting data and makes downstream automation smoother. Using structured output is especially important when building apps that rely on accurate, machine readable data like forms, APIs, or multi step AI workflows. Let us look at a practical example of structured output to understand why this approach is so useful. Let's consider a use case where we extract book information from AI. Suppose we ask the AI to provide the details of the book Harry Potter in JSON format with keys title, author, and published year. The AI might respond with a structured JSON output like this: a title, author, and published year, all in a JSON format. If you compare this with a free-form text output like this one, you can notice the few differences here. Structured output here is much easier for programs to read and use directly, and free-form text would require parsing to extract the relevant information, which adds complexity and potential errors. So now, how to use structured outputs in LLM apps? So to work effectively with structured outputs, you can ask the model to strictly follow a JSON schema, and you can validate output using JSON parsers before using them in your application. And structured output are particularly useful for databases, forms, API responses, and multi-step workflows. For example, in Python, we can easily extract a certain value from a certain key if the key and value are in a JSON format here. In this particular example, we have easily extracted the author from the book data variable that contains the AI response JSON as given here, and then we can easily output the author name or the name JK Rowling here. Okay, so there are some best practices for structured outputs here. So how do we do that? First of all, we define a clear schema for our AI outputs. Then we try to include mandatory fields in the instruction to ensure consistent responses. Then we validate outputs programmatically before using them in the app. And for complex workflows, we combine structured output with multi-turn conversation to maintain context and accuracy. So using structured output effectively allows us to build robust, reliable LLM applications that can automate tasks, integrate with systems, and handle data programmatically. And that wraps up episode 3 of our LangChain Masterclass. In this video, we covered the fundamental of LLM applications, including tokens and context windows, which helped us in understanding how models read and process text. We also understood chat models versus LLMs, base LLMs, understanding when to use which for our applications. We also looked at prompts with system, user, and AI messages, and also structured output in JSON mode. These are the core concepts you need to build efficient, context-aware, and reliable LLM applications. In the upcoming videos, we'll deep dive into further complex concepts in case of LangChain. Welcome to episode 4 of the LangChain Masterclass. In this video, we'll explore prompt templates, one of the most powerful tools in LangChain for designing reusable and dynamic prompts. We'll start with prompt template for single-turn prompts, move on to chat prompt template for chat-based multi-turn prompts, and learn how to use dynamic variables to make our prompts flexible. By the end of this video, we'll apply these concepts in a mini project, maybe in this video or in the next video, and build a template based blog writer using LangChain. So let's start with prompt template. A prompt template is a single turn template that lets you define a prompt with placeholders for variables. And why do we use prompt template? Because prompt template makes prompt reusable and dynamic so that we don't have to write new prompt for every other input. Let's consider this example. Here we have a template variable write a short blog about topic in a style here. So these topic and then the style here are the placeholders. What we can do is we can create a new prompt using a placeholder where the template will be the same template that we've defined earlier, and then the placeholders will be defined using these input variables here. So to produce the final prompt, what we're going to do is we're going to use prompt.format and then provide the topic that we want and then the style that we want. So in order to generate another prompt for some another topic or another style, I don't need to define my template as well as this prompt. I just need to invoke this prompt with a new topic and a new style. So the output for this will be write a short blog post about AI in education, which will be placed in this topic placeholder in an style will be informative, which will be placed in the style placeholder style here. So this will be our final output. Now let's move on to chat prompt template. So a chat prompt template is a multi-turn prompt template basically designed for chat models. What it does, it allows us to define system, user, and AI roles with dynamic variables. We've already talked about these various roles and various messages in our chat models here. We'll understand this with an example. We see that we have a chat template that is invoked from messages where we have a system message that says you are a professional blog writer, and then a user message which calls write a blog about a placeholder in a placeholder style. So to create a prompt about a certain topic and a certain style, we just need to invoke this chat template, basically call the format message function here and then provide the topic and a style. So the output of this is going to be a system message which tells you are a professional blog writer, and then a user message that tells write a blog about this particular topic, AI in healthcare, which will be placed in this placeholder in friendly style, which will be placed in this particular placeholder here. So if you have noticed something, what we have been doing is these two placeholders can accept dynamic variables here, and that's what we are going to talk about next. So dynamic variables allows us to pass values at runtime into our prompts. So example, all of these placeholders you see are the dynamic variables. What they do, they tend to make our templates flexible and easy to reuse across multiple tasks. Next, we move on to multi-turn prompt templates. So multi-turn prompt templates allows us to chain multiple prompts together in a conversation. Each turn can include a system, user, and AI message, and each can use dynamic variables. And multi-turn prompt templates are basically helpful in building chatbots, AI tutors, or workflows that require the context. So that is all for this video. In the next video, we are going to see a mini project basically titled as a template based blog writer, where we'll be using both prompt template as well as chat prompt template to generate blog posts dynamically. So welcome to episode 5 of LangChain Masterclass. In this video, we're going to dive deeper into prompts in LangChain. We'll get our hands dirty and we'll learn about implementing prompt template, which will teach us how to create reusable prompts for our AI applications. We'll also learn about implementing messages. Those are the building blocks of chat-based prompts. We'll also learn about implementing chat prompt template for designing multi-turn conversation, and basically message placeholders for dynamic variables that makes prompt flexible and adaptable. And by the end of this episode, you'll understand how to structure a prompt effectively, both for singleton and multi-turn interactions, and how to make them dynamic and reusable. And this is going to be an essential step towards building powerful context-aware AI applications with LangChain. So let me revise what a prompt template is. So a prompt template is a blueprint for your prompts. It will allow you to define text that the AI will see and optionally include placeholders for variables. There are two kinds of prompts here. The first is the static prompt, and then the second is the dynamic prompt. So when we define a static prompt using a prompt template, we will not have any placeholders. The prompt is always going to stay the same. Whereas if we talk about dynamic prompt template, we are going to include variables in it, making the prompt flexible and reusable for different inputs. So using prompt template will help us write clean, reusable, and maintainable prompts instead of hard coding text each time we want the AI to generate something. So let's start with a static prompt here. I've created a new file called static prompt, and then I'm going to write my code here. So first of all, I'm going to basically import prompt template, and that is going to come from langchain.prompts import prompt template. After this, I'm also going to uh, generate my model, but I don't think I need to use this model, because basically I'm just going to see whether my prompt will be generated or not, or my static prompt will be generated or not. So for that, what I'm going to do is I'm going to declare static template or static prompt using prompt template and inside this, for static prompt, like I said, we will not have any kind of placeholder, so the input variables will be empty. And then we'll define a template, basically saying write a short fun fact about AI. Now from here we can generate our prompt text, and then for that we need to invoke the static prompt dot format. Since we don't have any variables to pass, so we don't need to pass in any variable, and then basically print our prompt text. So if I run this code, python to prompts one static prompt dot py, so there is an error. Let me check. The import for prompt template is not available. Okay, it's not available inside prompts. So let me check inside LangChain core here. LangChain core dot prompts import prompt template. Okay, now let me rerun this code again. And basically we can see our prompt being generated from our prompt template or our static prompt variable using prompt template. But the only difference here is that we don't have any kind of input variables here. Sorry, this should have been a small v. We don't have any placeholders and we don't have any input variables inside this template. So if we need to write something new, we need to go and make changes to this particular template content here. Suppose if I need something on knowledge representation, then I need to explicitly define it in my template and then basically run the template again. So this is static template. Next we're going to see is dynamic template here. So let me create a new file, do this in new file called dynamic underscore prompt dot py. So let me import LangChain underscore code dot prompt import prompt template. Then I'm going to create a dynamic prompt using prompt template, and then my template will be write a short paragraph about a topic. You see the difference here. We've not hard coded our topic here. In fact, what we've done is we have kept a placeholder in place of topic. We can also place multiple placeholder here in a certain style. So here we have placed multiple placeholders. Where are the values going to come from? The values are going to basically come from the input variables. So these variables or these input variables are the dynamic variables that we talk about. So we can change these variables at runtime to generate customized outputs for like different topics and various writing styles. And this actually makes the prompt reusable and flexible, because if I'm going to prepare my prompt text, I basically need to invoke this dynamic prompt, provide the topic here, which will be placed inside my topic placeholder, and my style here, which will go into my style placeholder. And if I print my prompt text and basically run this code, then I can see that my prompt is created, but it is created through these dynamic input variables that is passed to the template. Now if I need another prompt from the same template, I can basically create it using or without making any changes to this particular dynamic prompt template that I've defined here. So if I do print prompt text1 and basically run this code, I can get two different prompts from the same prompt template in this particular case. So prompt template is a powerful way to structure our prompts in LangChain. Static prompts, as you can see, are always fixed. Great for repetitive tasks, but dynamic prompts lets us pass variables at runtime, making our prompts flexible and reusable. So using prompt template also ensures clean, maintainable, and professional prompts ready for single-turn applications especially. Now, if we need to uh, include prompts for multi-turn applications, we need to go into another concept, which is chat prompt template. So we've seen prompt template for single turn prompts. Now we'll move on to chat prompt template, which is designed for chat based multi-turn interactions. So in a chat application, prompts are structured as messages with three different roles. So first I'll create a file here mentioning chat prompt template.py. So we have three roles here. The first role is the system, which basically defines our AI's behavior, tone, or constraint. The second role is the user, which contains instructions or questions from the human. And the third role is the AI, which contains the AI's previous response used to maintain the conversation context. And what chat prompt template does is it allows us to define these messages with dynamic placeholders, so we can reuse the template for different inputs while keeping the conversation structured. Uh, so let's do this and then implement it and check it out. Wow, how we can implement prompt template. Sorry, chat prompt template. So from LangChain underscore core dot prompts, we are going to import chat prompt template. I will again not need a model because basically I need to print my prompt here. So what I'm going to do is chat underscore prompt equals to, I'm going to create this from chat prompt template dot, and then uh, this is going to come from my messages. So what will we consist inside our message? We will have a system message, uh, and a human message, and also an AI message for that reason. So let me import. We can do this in various ways. First of all, we're going to import it in this way here. So system message and system message prompt template and human message prompt template. So inside this, I'm going to include a system message prompt template, and then the prompt is going to be, or the prompt is going to come from this particular topic here. So you are a helpful assistant that provides information about a subject, and then a human message prompt template that again contains another placeholder called subject here. So let me just go down and then actually define what I'm going to pass in this particular subject variable. Or what I can do is I can basically print my final prompt, invoke it using chat prompt template. Again, we can do it or invoke it using from messages, and then basically pass in the subject placeholder here. Again, this subject is going to be my dynamic variable in this particular case. Now if I'm going to print my final prompt and then basically run this, what I can see is I can see my prompts basically containing of a system message at first, where the content is you are a helpful assistant that provides information about the quantum computing, the subject I've passed to this placeholder, the additional keyword argument, response metadata, and then the human message that tells, can you tell me something interesting about the same topic which I've passed into this particular subject placeholder here. Okay, so finally at the end we are going to work on a blog post generator project that I promised you in the last video. So here I'm going to create a new file for .project.py, and then this particular project will include a continuous conversation using chat prompt template, and then we will keep on editing our blog post until and unless we're satisfied with what the model has generated. I basically want to show you the contextual information that is saved throughout the conversation session using the system message prompt and the human message prompt that I showed you earlier in case of this chat prompt template.py. Okay, so let me start the code. So from LangChain underscore core dot prompts, I'm going to import chat prompt template, system message prompt template, and human message prompt template. Then from LangChain underscore Google underscore Gen AI, I'm going to import chat Google generative AI. Also from .env, I'm going to import load.env, and then basically call the load.env function to load our Google API key credential here. So let me first define my model. So the chat model will include our, or will basically define our Gemini 2.5 Flash model. So this is going to be a blog post generator, and then what we're going to do is we're going to ask the user to provide ideas or topics for the blog post in the beginning, and if the user don't want, he or she can type exit to finish. Okay, so take in the user input inside the variable topic. So input, enter blog post topic. Now I'm going to define my chat prompt template. So chat prompt template will use chat prompt template dot from messages, and then this is going to include a system message prompt template, and then using that we will write you are a professional blog writer, help generate informative, engaging, and well-structured uh, blog post about a topic. So let me do word wrap here so that you can easily see what I've been typing here. Now that the system message is included, I'm going to include a human message from, or using human message prompt template, and then I'm basically going to write a detailed blog post about a topic, and then that particular topic is going to be a placeholder. Now what I'm going to do is I'm going to initialize my chat history, or basically save my chat history in a list. So for this I'm going to create a list called chat history, and I'm going to run a loop because this is going to be a continuous conversation. So the user input will be asked. Basically user has already provided the topic, and after that we are going to ask for the ideas the user have, ideas or instruction the user has for that particular topic, or type exit, or the user can also type exit here. So let me check if the user input is exit, and if it is, then I'm going to exit from the blog post generator, or else what I'm going to do is I'm going to prepare my prompt here. So chat prompt template dot from messages, and then inside this I will allow the user, or I will provide the topic that is given by the user to the prompt here. Okay, so if there is an AI message from the previous response, then I need to include that. So from prev in chat history, chat underscore history, let me include messages dot append, sorry, for prev. So prev in chat history, I'm going to include the previous messages from the chat history in this particular prompt itself. Then I'm going to append the current human message that the user has provided into this message as well. So message dot append human message dot from template, and then I'm going to input the or place the user input, and then use format messages, and inside this I'm going to put in the last message provided by the user using this here. Now let me invoke my model using chat model dot invoke, and then I can basically print the response here. So if I run this, let me run this Python to prompts for project.py, then I will first be asked for a topic. Let me provide a topic, quantum mechanics. Then I'll be asked for instructions, or basically I can type exit here. I'll provide instructions. So the instruction is going to be 4-point each with 2 words about the topic and include my name Abhi at the end. So I've got an error here. Let me check what happened. Okay, so this should have been invoke, not invoke messages. So let me clear this and run this again. First of all, it will ask for a topic. So I'll provide the topic. Let's say quantum mechanics. And then ideas or instruction. Let me type 3 points, each point in 4 words, and add my name Abhi at the end. So based on the topic and then the idea that we provided, the model will now generate a blog post exactly on the basis of the instruction and topic that is provided to it. So I told only 3 points. Well, it did provide in 3 points, but it also went on explaining it. So anyways, it also added my name at the end. One thing I want to check here is whether it remembers the context or not. So it generated the topic or the blog post on the quantum mechanics, right? So what I would like to tell it now is I don't like my short form name. Change it to Abhishek. So I want to check if it remembers that it has kept my name at the end of this blog post here, and then whether it will change it to Abhishek from Abhi or not. And if it does remember the context of our conversation, which has already happened. So let me give this and then allow it to generate again. So it is taking some time because the model is not having. Okay, so yeah, it did change my name from Abhi to Abhishek. It also added something, some more points during the regeneration phase, but it did remember the context here. So this is it. Demonstrated the use of prompt template, chat prompt chat prompt template, and also we have implemented a project blog post generator with a continued conversation scenario here. So I hope you understood the concept. I hope the implementation runs for you.
Hello everyone, welcome back to the LangChain Masterclass series. In our previous videos, we explored the foundation of large language models working with prompt template, chat prompt template, and other core concepts that help us interact with AI models efficiently. And today, we're diving into a very important topic that can dramatically improve how our AI agent handles output, which is structured output. So structured output allows us to define a clear, predictable format for the responses we get from AI models. Instead of receiving unstructured text that we need to parse or interpret, we can directly tell the AI exactly how we want the output to look, whether it's a dictionary, a TypedDict, a Pydantic model, or even a JSON schema. This makes our AI agent more reliable, robust, and easier to integrate into real-world applications. Now, you might wonder, why do we even need structured output? Let me explain with a few real-world scenarios. Often, AI model returns text that's inconsistent. Sometimes a number is written as text or keys are missing. Without structure, we spend extra effort trying to extract the correct information. And if you're building an agent that populates a database, generates report, or interact with APIs, unstructured output can lead to errors. structured output enforces rules on the AI response, AI reducing mistakes. Next is when the AI's output is predictable, we can easily automate downstream processes from form filling to choice making workflows without manual intervention. And next, using typed outputs or Pydantic models allows us to validate the AI's response instantly, ensuring it matches the expected format and types. So, in short, structured outputs bring clarity, reliability, and robustness to our AI agent. And in this video, we'll explore 4 different ways to implement structured output in LangChain. First with TypedDict, then with Annotated TypedDict, then with Pydantic, and finally with JSON schema. And by the end, you'll know exactly how to enforce output structures in your AI project. So without any delay, let's start with the first project where we implement TypedDict for our structured response. In this first project, we are going to implement TypedDict class in order to structure our output response. So first of all, let's import our LLM class. So this time I'm going to use LangChain Grok, and from LangChain Grok, I'm going to implement or import ChatGrok. Then to load our credential from .env, I'm going to do load.env. Then from typing, I'm going to import TypedDict, as I said. Then I'm going to load my credential. Then in place of our model from ChatGrok, I'm going to use our Llama model, Llama 3.3 with 70 billion parameters here as our large language model. Now for the schema, I am going to define a class. Let's call it review. So this will be of type TypedDict. And then inside this, what I need is a summary, which will be in the form of string, and then a sentiment, which will again be a form of string here. Okay. So first of all, let me first show you my prompt. So in the place of prompt, I'm going to put a review of a hardware or a gadget, and then based on that particular review, I will try to extract the summary and sentiment of that particular review. So first of all, let me copy this prompt here to make it easily readable for you. What I'm going to do is I'm going to do word wrap so that you can easily read what the prompt is here. So first of all, what we're going to do is we are directly going to call our ChatGrok model and then basically see the limitation of what I've been talking about before in the theoretical part. So let me directly call this model. So model dot invoke and then call our prompt in this and basically print the content of our response. So if I run this, so if I activate my virtual environment and then run the class here. So Python, this is inside the third folder and then the first example. If I run this, then the output we get from the model will look quite messy. So as you see, the output is not exactly what we want. What we basically want is a summary and then the sentiment of the review, but it contains a lot of text. We haven't received a precise response from the model. So in order to get a precise response from the model, what I'm going to do is I am going to enforce a structured model here. Structured model using model dot with structured output and then enforce my review schema provided or created above. Now, if I generate a new response or basically invoke the model, response equals to structured model dot invoke, and then provide a prompt. And basically, if I see the content, let me rerun this again. So, okay, I'm not going to clear this. I'm just going to run it on top of this here. So if I rerun the code again, I should get a precise response here, basically a summary as well as the sentiment. Sorry, it should not be response.content. It should only be a response out object here. So let me rerun this. Then as I see, I have been provided a sentiment as well as a summary, just like I asked for, instead of all these bloated text box or text that I have. So in this case, the response from the LLM is not precise, but with structured output, enforcing the review schema that I've created using TypedDict. Now my output is very much structured and in the format that I actually want. So for the next program, I'm going to do the same, but with much more details on these keys provided here using the annotated keyword. So let me create a new file to annotated typedict.py. Okay, first of all, I'm going to import the LangChain grok model, import chat grok, and then from .env import load.env, and then from typing I will import TypedDict, annotated, and then optional. So again, my model will be the same as the previous model. So I'm just going to copy these two here, these two statements. So basically I want to load my credentials and then load my model here. So I'm going to again create a schema. The schema will have a type of TypedDict as its type here inside its parameter. But here, what I'm going to do is I'm going to declare a few more keys here. So the first key will be key themes, and then this will be annotated list of strings, and then I can also provide the additional information of what kind of content should be in key themes. So this will include must write down all the key themes discussed in the review in a list. Let me do word wrap so that it will be easier for you to follow. My next will be a summary. This summary is going to be an annotated string, and then in the explanation part, it will contain must write down a brief summary of the review. So basically, you're going to write the exact stuff that you want in this particular key here from the model. Next is going to be a sentiment. So sentiment is again going to be an annotated string, and then I will do must return sentiment of the review. Basically, it had given me a neutral sentiment, right? So I will ask the model to either say positive or negative only, not neutral. So the model will never provide a neutral sentiment in case of the response. I'll also show you the use of the optional keyword that I've imported here. So for the prose, what I'm going to do is I'm going to change its type to annotated list, or before doing the list, so I'll keep an optional keyword and then list of string, and basically write its explanation. So write down all the rows inside a list. So since this is an optional parameter, if it can find any kind of prose in my review, it will basically show it, or else if it does not find anything, then it will not return anything for prose. Now this particular prose is going to be an optional keyword. If it can extract the prose, it will. If it cannot, then it will leave it blank. Then I can do the same for cons. I'll just copy this for now. So for cons, I will write down all the cons inside a list. Okay, so since this is done, I am going to convert my model into a structured model using the with structured output function, and then enforce the schema that I've created earlier. Now let me create my prompt. Now since this prompt is again too long, I'm just going to copy this, and then you can follow or pause the video and then basically see what it is in the prompt. So this particular prompt is about this Google Pixel phone, and then it talks about the user shared reviews and then stuff like that. So basically this is the review that I will be working on. Now next, what I'm going to do is I am going to call my model with this particular structured model that I've created, and then invoke it passing the prompt here, and then I'm going to print my response. So it should provide me key themes from the review. It should provide me a summary. It should provide me a sentiment, and then if it is available, it should provide me pros and cons from the particular review. So let me clear this and then rerun this code again. So now the file will be annotated typedict.py. Run this and see what happens. Okay, so since it found some cons, so the cons are low GPU score, may struggle with demanding games. It also found key themes. So the key themes are GPU performance, Google Pixel 10 Pro, and mobile gaming. It also found some pros: may fail faster in everyday use, may perform better for AI tasks. The sentiment is negative. If I had given an option to also generate a neutral sentiment, it might have written down a neutral sentiment here, because there are both pros and cons in this particular review. And the summary is that the Google Pixel 10 has a lower GPU score than its predecessor, the Pixel 9 Pro, and other rival phone, which may affect its style in demanding games. So this is how we enforce our model to get the output in a specific structure using an annotated TypedDict as well as the optional keyword in the TypedDict part. So now for another code, I'm going to use the same or enforce the structured output using Pydantic. So we'll create a new class, free.pydantic, pydantic response.py, and then first of all I'm going to import my chatgrok class. So that will come from chatgrok, import chatgrok, then from .env import load.env, then from typing I'm going to import TypedDict, and annotated, and optional, and then a new one called a literal. I'll show you why we need this particular keyword here, and then where do we implement it. And then from Pydantic class we import base model and then field. So if you haven't used Pydantic at all, then please you can install Pydantic on your system using pip install Pydantic, and then basically do this code here. We might not need typing at all in this particular case, but we will use this literal as well as the optional keyword here. We might not use the TypedDict part in this particular program. So now, like in the previous video, I'm going to copy these two lines here, the load.env as well as the model part. So now these two are implemented. I'm going to create a class called review, or just call it a schema. And then inside this, instead of importing TypedDict, I'm going to use base model from Pydantic class. So again, like earlier, I will have key themes. Key themes is going to be a list of string. I can keep it as annotated, but here since we have this field variable, so for the explanation part, we can use this field. We can use this field class from Pydantic to explain what we exactly want in this particular part here. So in field and description, I can write down the key themes discussed in the review in a list. So let me do word wrap again here so that you'll see everything what I have been doing here. So first is going to be key themes, then the next is going to be a summary. The summary is going to be string, and then for the explanation part I can use field again. So description will be a brief summary of the review. Then I can have sentiment, and in place of sentiment I can use the literal keyword to enforce the exact stuff that I want. So the sentiment can be pause or negative, indicating the positive and negative sentiment. And then I can have a field for the expression part where the description is going to be return sentiment of the review. Then I'll have prose. Again, the prose is going to be optional, but it is going to be a list of string. If it is present, then for the expression part I can use a field. So if we don't have anything, then it can return none here. So the default value is going to be none for optional. And then for the explanation part, I can write down all the rows in a list. And similarly for cons, this is also going to be optional, list of string. With field, I can first define a default value none, and then in the explanation part I can write down all the cons inside a list. Okay, finally I will also add a name here. Again, the name is going to be optional. So, and then the explanation for this is going to be, so first of all we'll have a default because this is optional. So default is none, and then especially in the explanation part I can explain that you need to write down the name of the reviewer. Okay, so all of these classes and then the parameters are based on the Pydantic base model class, and then the field function or the field class from the Pydantic library. Now I'm going to convert my model. So structured model equals to model dot with structured output. So I'm going to pass in the review, and then to strictly enforce the model to follow the exact guideline that I provided, what I can pass in is strict equals to true here. So this will okay, it's not review, it's schema, sorry, schema class, and then strict equals to true here. Okay, now for the prompt I'm going to copy the same prompt that I've used earlier. So let me just copy this prompt. So this is my prompt. You can pause the video and then see what it is, or I've already shown it to you in the previous code here. So now what I'm going to do is I'm going to call the model using my structured model dot invoke. Okay, where is invoke? INV. Okay, invoke, and then pass in the prompt that I have, and then I'm going to print my response. So we can enforce a structured output from the model using the Pydantic class too. So let me run this code and then show you what the output is. So 3.pydantic response.py, it is running, and then I can see that I have key themes, which is GPU performance, benchmark scores, gaming capabilities, The summary is Google Pixel 10 Pro, GPU something something. We have pros and then we have cons, and then we have a name, but this is not a person name here, right? So I'm going to enforce the model, or like enforce it to write down the person name of the reviewer if found in the review. And then I'll also provide additional information like generally found at the end of the review. And then what I'm going to do is I'm going to pass a sample reviewer name, let's say like John Cena. So the review is done by John Cena. So the code is saved, and then if I run this again, then I should get the reviewer name too. And then here it is, the reviewer name is also present. So in this way, we can enforce a structured output using our Pydantic and using our Pydantic class here. So finally, at last, we're going to use a JSON schema to force our model to provide a structured output, and then we'll do that in our next program. So for that, I'm going to create a file again. So this will say JSON schema.py. Here I'm going to import LangChain grok first. Import chat grok from .env. Import load.env from typing. I might or might not use this, but anyway, I'm going to import everything. So TypedDict, Annotated, literal, and then optional. And then from Pydantic, I might not need Pydantic in this particular case here. So, okay, I'll not do Pydantic for now. And then, okay, what else? So I need to load the credential and then reload the model again. So I'm just going to copy this model reload part. Okay, so here in place of schema, I have prepared a schema or a JSON schema here for the output pattern that I need. So I'm just going to copy this from here and then I'll show you what it contains. Okay, so let me close this and then see this JSON schema from the very beginning. So the title is the review, type is object, properties are key themes. It should contain a key theme. It will be in array, and then each array item should be with type string, and then it also contains the explanation here. Then again we need a summary in the form of string, and then it also contains its explanation here. Then we need sentiment, it can be positive or negative, and then we have our string here. I'm not going to put on neutral in this particular case. Then we need our pros. This can be an array or this can be null since this is optional. And then if we get an array or a list of pros, then it should be in string, and then this is the explanation. And then finally we need our cons. We have an array or a default value is null. If it is present, then it should be in the form of string. Each cons should be in the form of string, and then this is the explanation. And finally we need a name, which can be a string or a null, and then I have extracted the name of the reviewer. And then all of these parameter key themes, summary, sentiment are required, and all other exceptional parameters are all other remaining parameters are optional. Okay, now what I'm going to do is I'm going to create a structured model. So from model dot with structured response, with structured output, and then pass in the JSON schema that I've just created. And then to ask it to follow it strictly, I'm going to pass strict equals to true. Again, I will have the same prompt that I had earlier. So I'm just going to copy this and then paste it here. So I have this prompt. Now, based on this prompt, what I'm going to do is I'm going to invoke my structure model. So structure model dot invoke, and then pass in the prompt here, and then finally print my response. So if I clear this, and then it is not saved, so let me save this, and then if I run this code again, so the code is now 4.jsonschema.py. I should get my structured response here. So I have cons, I have key themes, I have pros, I also have a name, and then the sentiment is given as neg. Since I only give pause and neg as the option for sentiment here, basically pause and neg, then I have a summary of my review. And that is a wrap on structured output in LangChain. So today we explored how to make AI responses predictable, reliable, and easy to work with. We started with TypedDict and annotated TypedDict, then moved on to the Pydantic model, and then finally saw how to enforce structured using the JSON schema here. So by using these techniques, our AI agent can now return consistent, validated data, making them far more robust for real-world applications, whether we're building chatbot, data extractors, or automated workflows. So I hope this video helped you understand not just how to implement structured output, but also why they are essential for professional AI development. So if you found this video helpful, make sure to like, share, and subscribe so you won't miss the upcoming videos in the LangChain series, where we'll continue exploring advanced AI agents, concepts, and implementations. So thank you for watching, and I'll see you in the next one. Welcome back to the LangChain Masterclass. In the last video, we explored how to enforce structure in our AI outputs using TypedDicts, Pydantic models, and even JSON schemas. That gave us predictable, validated responses directly from the LLM. But today, we're taking the next big step toward building reliable, production-grade AI workflows. In this episode, we're diving into output parsers, one of the most essential components for controlling, transforming, and sanitizing raw LLM responses. So whenever we ask an LLM to generate something, whether it's text, JSON, or structured data, the model simply returns a blob of text. And as developers, we often need that text to be converted into something more useful. Maybe a dictionary, maybe a Python object, maybe valid JSON, or maybe just a cleaned up string without extra formatting. And this is where output parsers become incredibly important. So output parsers act like a bridge between the LLM's response and the exact format your application needs. They help us solve common problems that show up frequently in real AI development. For example, when you ask an LLM for JSON object, it might wrap the responses in backticks, add explanations, or provide, here is the JSON you asked for text. So this makes the output impossible to directly load into the parser. Output parser strip away noise and give you exactly the content you asked for. Similarly, even if we instruct the model carefully, sometimes it forgets a quote, adds a trailing comma, or formats arrays incorrectly. This will break your entire pipeline. So using something like JSON output parser helps enforce valid JSON and repairs common model mistakes. And if you're working with structured data like user profiles, product details, form fields, or classification labels, you rarely want raw text. Instead, you want a validated Python object that you can immediately send to an API, database, or UI. That's where Pydantic output parser becomes incredibly powerful because it converts AI output directly into Pydantic models with type checking and validation. And when your AI agent needs to make choices, calls APIs, or trigger tools, you can't rely on messy text. Agent need exact formats, clean fields, and guaranteed structure. Output parser is going to give us that stability. So in this episode, we'll explore 3 essential output parsers in LangChain: the str output parser, the JSON output parser, and then the Pydantic output parser. Here, we'll implement each one, see how they behave with real prompts, and understand when to use which parser. And by the end of this video, you'll not only know how output parsers work, but you'll You'll also be able to design AI pipelines that transform raw LLM text into clean production ready data. So without any delay, let's go into the implementation. So we'll start with the simplest parser in LangChain, which is the str output parser. This parser does exactly what its name suggests. It takes the raw output from the language model and returns it as a clean plain string. Think of it as the most lightweight and default parser that simply says, no matter what the model returns, just give me the text cleanly. This is especially useful when your pipeline involves further string processing, sentiment analysis, keyword extraction, or when you just need the response itself without any structure. So in short, str output parser will be our baseline parser. It doesn't enforce structure, it doesn't validate JSON, it does not convert into object. It simply ensures that the final output of the model is delivered as a clean, predictable string ready for the next step in our workflow. So to implement str output parser, I will first load my LangChain grok model, import chat grok, then from .env import load.env, then from LangChain underscore core dot prompts import prompt template, and then from LangChain core dot output parsers import str output parser. Okay, now let me call my model here. So my model is going to be from chat grok, and then the model name is llama model 3.3 with 70 billion parameters and versatile. Let me quickly confirm the model name here. So llama 3.3 70 billion versatile. I think the name is correct, even though I will try to make it consistent. Anyways, now at first I'll define a template. So that will be from prompt template. I can write template and then write a detailed report on a topic. So the topic is going to be my placeholder, and then the content that will come inside topic can be defined in the input variables, and then input variables will define a topic object. Okay, so this is my first template or my first prompt. So first prompt template. Then similarly, I'll define my second prompt template here. Second prompt template. So the template 2 is going to again come from prompt template. And inside this, I'll first define my template, write a 5-line summary on the following text. So the text again will be a placeholder, and then it will also be defined inside our input variable. So comma. So input variables will be our text. Now this will be our second template. I'll now define a parser, str output parser. So we might not have talked about chains here. I will do that in the upcoming video. But for now, I'm going to define a chain. A chain is a sequential step in our AI agent that will take place. So at first, template 1 will create a prompt for the first prompt. Then it will be passed to the model. I think I have a model. Yeah, model. Then I will call a parser object, which will convert our model response into a string or a readable string. Then I will generate template 2 and then basically call the model and then pass the parser object here again. So for our response, I'm going to invoke the chain. So while invoking the chain, since the first template is going to be called, so I need to pass in the topic here. So for that, I'm going to define a topic and then pass a topic. Let's call it black hole, and then we are going to finally print the result. Sorry, it is going to be response, not a result. Okay, so if I run this, so this, let me save this first. So if I run this, this is inside my fourth folder output parser, and then one str output parser.py. So okay, what's wrong here? Okay, so I think I forgot to load the credentials. So to do that, I need to call load.env function. Let me save this and then rerun the code again. So to do that, let me hit clear and then rerun the code again. So my credential will be loaded. My first parser, sorry, my first template will be called, and the prompt will be write a detailed report on black hole. Then the model will generate this particular response based on this first prompt, and it will be passed to a parser. Now the parser will generate a readable string based on the first template. Then I'll pass the same output or the parsed output into the second template, where it says write a 5-line summary on the following output from the parser, which is text. Then based on that, I'll pass it again to the model, and then finally I'll again call the str output parser. Now here, if we see the response, we'll see the last part of the response here. So it contains exactly 5 lines, 1 2 3 4 5 points here. 4 points. Actually it contains 4 points, not 5 here, but anyways, so here we have a precise summary that we exactly want, and then there is no additional content in the response. The response only contains a readable string in this particular case. So this was the case of str output parser. Welcome back to the LangChain Masterclass. Up to this point in the series, we've explored how to work with LLMs, how to build prompts, how to structure outputs, and even how to enforce strict schemas for reliable data. But as your AI application grows more complex, a single prompt or a single model call is no longer enough. Real world AI workflows are rarely one shot. They involve multiple steps. One step generates something, another transforms it, another validates it, another analyzes it, and another uses the output to trigger a choice or an action. And unless these steps are connected, orchestrated, and executed in the right order, your AI system becomes unpredictable and impossible to maintain. And this is where chains enter the picture. Chains are the backbone of LangChain's workflow ecosystem. They allow you to combine multiple operations, model calls, transformations, utility functions, data processors into a single, reusable, and reliable pipeline. Chains help you go from a single prompt to a structured multi-step AI workflow that behaves the same way every time you run it. In this episode, we're going to explore 4 essential types of chain that every LangChain developer must master. The 4 chains are: the first is simple chain, where a single input leads to a single output. The next is the sequential chain, where multiple steps run one after another like a pipeline. The third is the conditional chain, where different branches execute based on rules or model output. And fourth is the parallel chain, where multiple tasks run side by side to save time and improve efficiency. Each of these chains solves a different class of problems, and by the end of this video, you'll know exactly which one to use and when. So why do we need chains? Let's look at real problem scenarios. Imagine you're building a resume analyzer. One step extracts the details, another step cleans them, another summarizes the candidate's background, another evaluates the experience level, and so on. If you rely on a single prompt for all of this, the output becomes messy, inconsistent, and impossible to control. A chain helps break this into clean, manageable steps. Or consider content creation system, where you first generate an outline, then expand each section, then refine the writing style, then correct grammar, and finally create a meta explanation. Doing this in one prompt leads to bloated outputs and hallucinations. A chain lets each step handle its own responsibility. Or imagine building an intelligent agent that needs to choose between multiple options like retrieving information, generating content, or calling an API. Without conditional chains, your agent has no structured way to choose paths. And finally, think about the use cases where generating multiple items at once saves time, like summarizing various sections of a document simultaneously. And that's where the parallel chains shine. So in this video, we're going to break down how chains work, how they enable step-by-step logic, and why they form the foundation for building advanced agents, tools using systems, and multi-stage AI pipelines. And by mastering chains, you'll unlock the next level of LangChain development. We will start with a simple chain. A simple chain is exactly what it sounds like: a single linear flow from input to output, where you provide an input, it passes through a prompt, the language model processes it, and finally, a parser cleans or formats the result, and then we get an output. There are no branches, no choices, no multiple steps, just one clean, straightforward pipeline. Think of simple chain like a conveyor belt, where the object moves from one station to the next without interruption. Basically, one prompt will lead to one model call, and that will lead to one output. Simple chains are perfect for tasks that need consistent single-step transformations like generating text, extracting a short answer, rewriting or summarizing content, or producing quick structured text snippets. They keep your workflow clean, predictable, and easy to trace. Another major advantage of simple chain is composability. Each component, the prompt, the model, and the parser here is modular. You can easily swap out any one of them while keeping the chain intact. If you want a more detailed prompt, you can replace the prompt. You want a different parser, you can swap it. The chain still behaves the same way, just with a different internal logic. But the real power comes from how LangChain lets us build these chains visually and programmatically. Because each step is defined clearly, you get a transparent, debuggable workflow that you can inspect, visualize, and reuse across your applications. Now, let's connect this concept to the use case in our program. In the implementation that we're going to do, our simple chain will follow a classic 3-step flow. First, a prompt will ask the model to generate 3 facts about a user-provided topic. Then, a model call will process the prompt and generate the text. And then finally, a string parser will clean the output and give us a nice final answer. So these 3 components will be connected in a single linear chain. And when we invoke a chain with a topic, the chain will automatically run each step in order and return clean, ready-to-use text. And because it's a simple chain, the entire flow is easy to understand and perfectly suited for quick generation tasks like this. We even visualize the chain using its built-in graphic representation, which shows exactly how the data flows through the pipeline. Now, we'll move on to the implementation of our simple chain. Here, we'll first import the chatgrok class from LangChain _grok import chatgrok. Then from .env, we'll import load.env from LangChain _core.prompts. I'm going to import prompt template. Then from LangChain _core.output parsers, I'm going to import str output parser. Then I'll call the load_.env function, define my model. So my model will come from chatgrok class, and then I'll be using a llama model here as my LLM. Now I'm going to define my prompt, and then that will be defined using my prompt template. Template equals to generate 3 facts about a topic, and then I'll provide the topic as a placeholder here. Now, since we have a placeholder, we need to define our input variables. So my input variables will be the placeholder that I have here. So it will be topics. Now I will define my parser object using str output parser. Then I will define my chain here. So the chain will first generate a prompt. It will pass the model or the prompt to the model. Then the model output will be passed to the parser, and then the parser output will be generated. So if I need to invoke this chain, I can simply call chain dot invoke and then pass in the topic that I've represented here in the form of placeholder. So the topic can be aliens. And then finally, I can print out the result. So in the result, I should get a 3-point fact, basically 3 facts about aliens here, and then it should be in the string format. So now let me run this code. Chains on simple chain .py. Okay, so I have these 3 facts about aliens here. So this is the implementation of a simple chain. As you can see, It's a simple linear chain with a prompt, a model, and a parser. Now that we understand simple chains, let's move to the next level of workflow design, the sequential chain. A sequential chain is essentially a pipeline made of multiple simple chains connected one after another. Instead of transforming the input once, you break the task into several ordered steps where the output from one step becomes the input for the next. Think of it like an assembly line in the factory. Step 1 creates a rough shape, step 2 refines it, step 3 polishes it, and step 4 adds the finishing details. Each stage handles a very specific responsibility, and because the tasks are separated, the entire process becomes more reliable, interpretable, and reusable. Sequential chains are incredibly helpful when your workflow cannot be completed in one shot. For example, generating an outline, then turning each point into content, or extracting data, then cleaning it, then summarizing it, or generating a concept, then translating it, then rewriting it in a specific style, or doing multi-phase reasoning where each phase needs isolation. But with a sequential chain, you get a clear structure. Step-by-step reasoning, each performed intentionally without overloading the model with too much context at once. Another strength is how easy it becomes to debug. When something goes wrong, you know exactly which stage misbehaved. And because each step is its own mini chain, you can reuse, replace, or enhance individual stages without breaking the whole pipeline. So, in the example that we're going to do for sequential chains, we will follow the structured multi-step approach. We'll have a first chain that generates an explained piece of content based on the user's input. In the second chain, it takes the generated content and further transforms or expanded. And in the third chain, which is optional, will clean, refine, or format the final result of the user. Actually, we will use a parser for this. So each step has a single job, and together they create a smooth, controlled workflow. When we invoke the sequential chain, the LangChain automatically runs each segment in order, passing the output of the first chain into the second and then into the third, giving us a polished final result. So this will make your workflow significantly more organized compared to trying to squeeze everything into one huge prompt. And instead, we break the logic down to smaller, understandable units and let the chain connect them. That is the real power of a sequential chain, turning a complex operation into a predictable, well-structured pipeline. Now, let's move on to its implementation. We will first import our chatgrok class. So that is going to come from LangChain_grok import chatgrok. Then from .env, I'm going to import load_.env. From LangChain_core.prompts, I'm going to import prompt template. From LangChain_core.output parsers, I'm going to import structured output parser. Sorry, it is string output parser. Then I'll call the function load.env and then actually define my model. Now let me define prompt 1. So prompt 1 will use prompt template to define a template which will say generate detailed report on our topic. Since we have a placeholder, we need to define input variables here. Input variables, and then input variables will contain this topic. Then we'll have prompt 2. Prompt 2 is going to be about generating a summary of the content generated by prompt 1. So here what I'm going to do is generate a 3-point summary of the following text, and then I'll have a text placeholder, and similarly I need to have an input variable with text. Now I'm going to define my parser, which will be from string output parser, or sorry, yeah, str output parser or string output parser. Now I'm going to define my chain. So my chain will first use prompt 1, then the model, then prompt 2, then the model again, and then okay, so before we pass it on to prompt 2, we'll also use a parser, then prompt 2, model, and then finally a parser. So after this, I can invoke this chain easily using invoke function, and then I need to provide the starting context, which is the topic that is required in prompt 1. So the topic again is going to be aliens, and then I can print and see the result. Okay, so in this code we have multiple prompts where prompt 1 will be generated. It will pass to the model. The output will be parsed using str output parser. Then it will be passed to prompt 2, and then prompt 2 will be passed to the model, and then the output will be generated by str output parser, and then the final output from here will be seen in the terminal here. So let me clear this and then run the file. We will not be able to see the intermediate results generated by these tools here, but we'll only see the result after this particular parser. In order to visualize or see the result or the intermediate result of the chain, we need to introduce a monitoring tool, and we already have a tool in the LangChain ecosystem called LangSmith, but that will be for the further videos. Okay, so finally we have received a 3-point summary of our provided topic. So this is how we implement sequential chain in LangChain. Now we move on to conditional chains. In many real-world workflows, what we want the system to do next depends on the situation. Not every piece of information follows the same path. Not every input deserves the same treatment. And definitely, not every user message should trigger the same response. Imagine you're building a support system. Some users send praise, some send complaints. Some provide neutral feedback. Each type of message deserves its own specific, meaningful reply. But if we try to handle all these cases with one fixed chain, the workflow becomes rigid, and the output starts to feel generic and unnatural. That's because not all tasks are sequential, and not all tasks are parallel. Sometimes the workflow needs to branch, to split paths, and run different logic depending on the result of a choice. This is exactly where conditional chains shine. A conditional chain introduces intelligence in the workflow itself. Instead of following one straight line, the chain can evaluate something, make a choice, and choose the correct path to follow. It's like adding a brain to the pipeline. In the example we'll be doing, we're simulating something extremely practical, responding to customer feedback, but in a way that's tailored to the sentiment. Here's the workflow we're designing. First, we classify the sentiment of the feedback. Is it positive or is it negative? The system must choose. Then, based on that decision, take a different path. So if the sentiment is positive, we generate a friendly, appreciative reply. And if the sentiment is negative, we generate a thoughtful, empathetic response. And if something unexpected happens, we have a fallback message. So this is a perfect real-world example of conditional reasoning. One input, one choice, two completely different workflows. And the beauty of conditional chains is that all of this happens automatically. We don't manually check the sentiment. We don't manually choose the right path. The chain itself handles the branching logic behind the scenes. And this is what makes conditional chains so powerful. They let your AI pipeline adapt to the situation just like a real human workflow would. Now, let's move on to the implementation of this conditional chain. So first, we'll import our chat grok, load.env, prompt template, str output parser, and then I'll also keep a Pydantic output parser. Then I'll import runnable parallel, runnable branch, and runnable lambda. Then from Pydantic, import base model and field. And then from typing, we import literal. Okay, so load the credential from .env file, define a model. Let's call it model 1. This is going to be a llama model. Now I'm also going to define a str output parser object. So for the feedback, let me define a class which will take in the base model from Pydantic. And then inside this, I'll have one field, sentiment, which is going to be a literal. Basically, I'll have two options, positive and negative. And then if I need to explain this, I can use field. The sentiment of the feedback must be either positive or negative. Let me do word wrap so that you can see everything fit inside one screen. Now I will define parser 2 using Pydantic output parser, and then the Pydantic object is going to be feedback class that I've created. Now let's do prompt 1. It will be generated from prompt template. The template is classify the sentiment of the following text into positive or negative. So I will provide a feedback. This will be a part of my placeholder. And then I'll also provide my format instructions because I need the output to follow this Pydantic output parser or the format that I've defined in this feedback class here. Then I'll define my input variable. Input variable is going to be feedback. And then I'll also define a partial variable. So this partial variable is going to be format instructions, format instruction, and then this will come from parser 2 dot get format instructions. Now let me create my classify chain. So this will contain prompt 1 and it will contain model 1, or I might only have a model. Okay, I have model 1. Then it will contain parser 2. Now I'll have prompt 2 and this will do the following. So write an appropriate response to this positive feedback, and then I'll provide the feedback. Again, this is a placeholder, so I need to define my input variables as feedback. Similarly, I'll have prompt 3. I'll just copy prompt 2 because it is not going to be changed much, except I'll call this a negative feedback and then pass in the negative here. Now I need to create a branch chain. So my branch chain will be created using this runnable branch class. And inside this, if my sentiment is positive, then for that I'll define a lambda function. So x dot sentiment equals to positive. Then I want to run prompt 2, model 1, and then parser. Else, if the sentiment is negative, x colon x dot sentiment equals to negative, then I want to call prompt 3, model 1, and then parser. Okay, so this should have been prompt 3 here. So prompt 3, model 1, and parser. And for default, I'll call runnable lambda x, and then basically I'll return no valid sentiment found. Now finally I'm going to define my final chain. So this will contain my classifier chain as well as my branch chain. Now let me invoke this final chain using the invoke function, and then what I need to provide is a feedback, and then maybe my feedback is going to say this is a beautiful place. Then let's see the result, and then let's see if this positive feedback will generate a positive response to it or not. So let me clear this and then run 3.conditional chains. Okay, it says no valid sentiment found. Let me elaborate this, which has a lot of amazing historical insights, and the people are also very good. Thank you for having us here. So let me check again if I've done anything wrong. So positive, negative. This should be sentiment of the feedback, and save it and then run it again. Still says no valid sentiment found. So let me check whether I've done anything wrong here or not. So this is sentiment. This is correct. It should be a literal with two options, positive and negative, where the sentiment of the feedback must be either positive or negative. This is also correct. Now I've created parser 2. Here I've passed in feedback and then the format instructions from parser 2, which is also correct. And then here I have called prompt 1 model 1 parser 2, which is also correct. Then I have prompt 2, which basically says to write an appropriate response to this positive feedback, and it is also good. And in prompt 3, write an appropriate response to this negative feedback, which is also good. Now, if the response is positive, I want to invoke prompt 2, pass it to the model and parser. And then if the response is negative, then I want to invoke prompt 3 and pass it to the model. Let me not have this default value. because the model might get confused with this particular default value here. Or even if I remove this, let's see if we get an error. So if I run this again, okay, so runnable branch must default must be runnable. Okay, so I need to keep this, and then we'll say no valid sentiment found. Let me change the temperature of my LLM here. So let me keep it to 0.7 and then run this again. Okay, it still says no valid sentiment found. At least what it is doing is, or let's say the sentiment is neutral for this particular case, and then change our sentiment here. My stay here was horrible. You people are stupid. And then run this again. Okay, so it did identify the negative sentiment and then generated the the response for this particular negative feedback here. Okay, so this is how we implement conditional chains in LangChain here. Now we move to the final type of chain, which is the parallel chain. So sometimes when we build AI workflows, the problem isn't about choosing one path or the other. Sometimes the challenge is speed, efficiency, and the ability to get multiple things done at the same time. In many real-world scenarios, a single input can be used to generate multiple outputs. For example, if you have a chapter of text, you might want notes for revision, a quiz for practice, a summary for quick reading, and a study guide for students, all based on the same source material. Now, if you were to run each of these one after another, first produces the notes, then wait, then generates the quiz, then wait, then makes the summary, then wait, you waste time, you waste compute, and your workflow becomes unnecessarily slow. But what if all these tasks could happen simultaneously? What if your pipeline could take the same text, split it into different branches, run each branch independently, and then bring all the results back together? And this is exactly what parallel chains enable. Parallel chain let your workflow perform multiple tasks at once using the same input. You're not doing sequential work. You're not branching based on a condition. You're simply letting the chain split into multiple workers, each focusing on a different goal and then combining the outputs afterward. It's the closest thing to multitasking inside an AI application. So in the implementation you'll see we take a single block of text, a piece of content, maybe about a certain topic, and we use it to produce two different outputs at the same time. First, a short, simple note, something clean and minimal, which is good for revision, and then a set of quiz and answers, something interactive and useful for learning. Both tasks will run in parallel, which means there is no waiting for one to finish before starting the other. And once both pieces are ready, we merge them into one polished comprehensive study response, a document that contains both the notes and the quiz. So this is the real power of parallel chains. They'll allow you to transform a single input into multiple meaningful output, all in one coordinated process. Whether you're making study materials, generating variations of content, or building multi-output AI tools, parallel chains will allow your workflow to scale horizontally, fast, neatly, and efficiently. So now let's go to the implementation of this parallel chain. So just like in the previous implementation, I'll first import ChatGrok class. And then from .env, I'm going to import load.env from LangChain core.prompts, import prom template from LangChain core.output parsers, import str output parser, and from LangChain core.runables, I'll import runnable parallel. Now load the credential in the beginning. Then I'm going to define two models here. So model 1 is going to come from ChatGrok. The model name will be Llama 3.3. I'll have another model, model 2, with the same LLM, but I'll use these in two different parallel workflows. So I'll have prompt 1 using chat prompt template. Sorry, it will be using prompt template, and then a template is going to be something like generate short and simple note from following topic. So I'll provide a topic here, and then since this is a placeholder, so I'll also define input variables, and inside this I'll provide a topic. I'll have prompt 2. Let me recorrect the spelling here. Prompt 1. I'll have prompt 2 that will say generate 5 short question answer from the following text. Template equals to, and then I'll provide a text placeholder here. So I'll also need to pass an input variable called text. And then I'll have prompt 3, which will say merge the provided notes and question answers into single document. So I'll provide notes and QA. And since both of these are our placeholders, I'll now define my input variables. Template equals to, okay. So input variables, I'll have both notes and QA. Okay, so I'll also define a parser using str output parser class. Now let me define my runnable chain. So my runnable chain will use runnable parallel to define this chain, and then I have two paths for this. For nodes, I'll pass prompt 1, model 1, and then parser. And for QA, I'll pass prompt 2, model 2, model 2, and then parser. Now let me also create a merge chain. So this merge chain will have prompt 3, model 1, and then parser. Now let me declare my final chain. So my final chain will be, at first we'll run a runnable chain and then a merge chain. Okay, so yeah. So maybe what I can do is I can provide a topic here, or directly invoke the model. Basically, let me invoke the model using my invoke function in the final chain. So final chain dot invoke. Okay, what do I need to pass? I need to pass the topic first. Okay. Okay. So let me do something. It's not going to be topic. It is going to be text here. So what I'll do is I will prepare a text from somewhere, Let me just paste this. So this text is about support vector machines. Let me remove this. So I'll paste this and then do a word wrap so that you can see what the text is. You can put any text that you want. So basically I have this text. Now finally I'm going to invoke my final chain dot invoke and then pass in the text here. So based on this text, I'll generate a note as well as Q&A and then merge these both into one. And finally, let me print out my result. So what happens here when I run this code is, let me run this first. So what happens when I run this code is, there are two parallel chains going on. First is for the nodes. The second is for the Q&A. Now these two chains will run parallelly, and then once both of these chains are complete, then it will be passed through this particular merge chain here, and then merge chain is going to generate a string result which contains, let me elaborate this. So this is going to contain a comprehensive note as well as the frequently asked questions, or basically the question and answer section here too. So this is how we implement parallel chain in LangChain. And that brings us to the end of this session. So we explored how chains give structure to our AI workflows, starting with simple chains, moving into multi-step sequential pipelines, branching logic with conditional chains, and finally parallel chains that let us execute multiple tasks at the same time. And by now, you should have a clear sense of how powerful and flexible LangChain becomes once you begin connecting these components together. So this is the foundation that allows us to build real production-grade AI systems that are modular, scalable, and capable of handling increasingly complex logic. But this is just the beginning. In the next videos, we're going to step into more advanced concepts in LangChain, deeper routing, agent architectures, memory, tool use, and everything you need to design intelligent autonomous AI systems. So if you enjoyed this breakdown, make sure to like, subscribe, and follow the entire LangChain Masterclass series, because things are only getting more interesting from here. Thanks for watching, and I'll see you in the next one.
In this video, we're going to break down one of the most powerful ideas behind modern AI systems, that is, Retrieval Augmented Generation, or RAG. We'll start from the ground up. First, we'll understand why RAG is needed, what problems it actually solves, and how it fundamentally different from simply prompting an LLM. Then, step by step, we'll build a basic RAG pipeline, from document loading and chunking to embeddings, vector stores, retrieval, and response generation. As the series progresses, we won't stop at a static RAG system. We'll upgrade it by adding memory so the system can remember past interactions, maintain context, and behave more like a real conversational assistant. We'll also introduce conversation threads, showing how multi-turn conversations are handled internally and how retrieval changes when history comes into play. Every concept will be explained clearly with practical examples and real implementation details, not just theory. And by the end of this video, you won't just understand how RAG works. You'll be confident enough to design and implement your own RAG pipeline from scratch and extend it for real-world use cases. So let's get started and build intelligent retrieval-powered systems one step at a time.
Most of the time, the data we want our AI system to use doesn't live in a single prompt. It lives in files, it lives in folders, it lives in PDFs, documents, spreadsheets, website, and entire directories full of unstructured text. That is where traditional prompting starts to fall apart. You can't simply copy paste a 200-page PDF into a prompt. You can't feed a directory full of policy documents into the chat model. And you definitely can't expect an AI model to answer domain-specific questions without having access to actual source material. This gap, the gap between real-world data and LLM processing, is exactly what gives rise to Retrieval Augmented Generation, or RAG. RAG allows your system to pull knowledge from external data sources before generating an answer. But before you can retrieve anything, before you can chunk text, before you can embed text or build a vector store, you need to get the data into LangChain in the first place. And that is where document loader comes in. So document loaders are the entry point into every RAG pipeline. They take raw data, whether it's a text file, a PDF, an entire folder of documents, a CSV spreadsheet, or even a web page, and load it into a clean, structured format that LangChain can process. Without document loaders, there is no data ingestion. Without ingestion, there is no chunking. And without chunking, there is no embeddings. And without embeddings, RAG is impossible. So in this episode, we are going to explore some of the most commonly used document loaders in LangChain. The first will be text loader, which is perfect for raw TXT files. The next will be PyPDF loader, which is one of the most widely used loaders for extracting clean text from PDFs. The third will be directory loader, which will be used for loading entire folders full of mixed document at once. The fourth will be web-based loader, which will be used for scraping and loading content directly from web pages. And the final one will be CSV loader, which will be used for converting structured CSV rows into queryable documents. And by the end of this video, you'll understand exactly how to ingest almost any type of data, and more importantly, how these loaders become the foundation for everything we're going to build next. Because starting from this episode, we officially begin our journey into Retrieval Augmented Generation, or RAG, which is the engine behind chatbot, knowledge assistant, AI search systems, and intelligent applications that rely on your custom data. So let's dive in and start bringing real-world documents into our LangChain workflows. Alright, so now that we understand why document loaders are such a critical piece of RAG puzzle, let's begin with the simplest and most beginner-friendly one, the text loader. Think of text loader as the hello world of document ingestion. If you have a raw TXT file sitting on your computer, maybe notes, logs, transcripts, script documents, anything, text loader's job is to open that file, read it, and convert the entire thing into structured LangChain documents. But here's the key. It doesn't just read the text. It packages the contents and its metadata in a format that every other LangChain component understands. That means when you later split this text into chunks, embed it, or store it in a vector database, everything flows smoothly because the loader already organized it properly. And this is important because TXT files are one of the most common formats you'll encounter in early stages of RAG development. When you're prototyping an idea, testing extraction strategies, or simply working with small datasets, you probably start with a small text file. It's quick, it's lightweight, and it helps you iterate fast. With text loader, even something as simple as a TXT file becomes instantly usable by your AI system. Instead of copying and pasting the content into prompts, which becomes messy, unscalable, and error-prone, the loader brings it into the LangChain as a clean document object ready to move through your pipeline. And the beauty of text loader, like I said, is its simplicity. There's no heavy parsing, no special formatting issues, no PDF quirks, no web page markup, just clean, predictable ingestion. And because of that, it's the perfect first step in understanding how all other loaders work. So what you're going to see next is exactly how we take a basic TXT file and load it into LangChain as a document. And once you see how effortless that is, you'll start noticing how every other loader follows this same pattern, just with different data source. So let's load our first document and get things rolling. So for the implementation part, we are going to import document loaders from LangChain community, and inside that we'll have a loader here. So for now, I'm only going to import this particular content here. So basically, I have a text file named cricket.txt, but it actually contains a document here. It is a story about an LLM that I generated using Gemini model. So basically, I'm going to load this txt content into LangChain here. So for that, I'm going to call on loader and then call the loader class here. Basically, I'm going to provide my file name. My file name is cricket.txt. And then I'm going to use the encoding. If in case I have some characters that cannot be read properly. Okay, now if I do docs equals to loader.load, then I can see docs. I can see the type of docs. Then I can see docs 0. Okay, we'll see this and then we'll move further. So run this. So Python 6 document loaders, 1 text loader.py. So as you can see, whenever we printed docs, it has printed the entire content. Actually, the content is quite detailed here. So here, if we see the type of docs is a list. And then if we do docs 0, then it shows me the page content of the docs here. So what else can I do? Okay, I can also, let me comment down all of this. Then I can use docs 0. We've already seen the page content. We can also see the metadata of the document using this line here. So let me clear this output and then run the code again. So the metadata that the file contains is a simple source or file name called cricket.txt. And then if I want to see the page content of this, I simply need to do docs0 dot page content and then it will provide me, it should provide me the entire txt file content that I have. Okay, so this is how we use the simplest form of document loaders, which is text loader. Now that we've warmed up with a simple text file, let's move to something a bit more realistic and far more common in real-world applications, which is PDFs. So PDFs are everywhere. Whether you're dealing with research papers, books, scanned documents, reports, manuals, college notes, or corporate documents, almost everything is packaged as a PDF. And unlike text files, PDF are not friendly. They have pages, layers, embedded formats, headers, footers, and sometimes even weird spacing or invisible characters. This is where PyPDF Loader becomes a lifesaver. PyPDF Loader doesn't just rip all the text out of the PDF in one giant blob. It loads the PDF page by page, meaning each page becomes a separate document object. And why is that useful? Because page level granularity gives you more control. Later, when you chunk, embed, or retrieve sections, the model knows exactly which page a piece of information came from. If you're building a RAG system where citations or references matter, this becomes incredibly valuable. Another powerful benefit is metadata. PyPDF Loader automatically attaches metadata like page numbers and file names. So if your RAG assistant needs to say something like this answer comes from page 12 of the curriculum, that information is available right out of the box. What's even better is that PyPDF Loader handles a lot of PDF quirks gracefully. Whether the document has tables, bullet points, or multi-column layouts, it tries its best to extract clean, usable text, so you spend less time fixing formats and more time building your pipeline. So in the demonstration, we'll be loading a PDF file, inspect one of its document entries, and then look at the metadata attached to it. So this will give you a clear picture of how PDFs are transformed into structured LangChain documents and how ready they are for later steps of splitting, embedding, and retrieval. Let's jump in and see how PyPDF Loader helps us to unlock the content inside a PDF. So here in this implementation, I have this PDF, basically an audit report of National Audit Office, or like of some form of organization. We'll try to extract the text from this PDF using PyPDF loader. So for that, I'm going to import LangChain community dot document loaders import PyPDF loader. Then basically I'll call loader PyPDF loader and then pass in the file name, which is audit report.pdf, and hit docs equals to loader dot load. Then I can easily print the docs as well as the individual page of the docs here. So let me do print docs and then run this file. Okay, so one of the package is still required. So let me go to requirements.txt and then install PyPDF here. So I'll install the requirement -r requirements.txt. Let me install the PyPDF library first. And then rerun the code again. So as you can see, the first page document is loaded and then it is present inside page content. This page should also contain some form of metadata here. So to load the metadata portion only, what I can do is I can hit docs0.metadata, and then we'll be able to see what kind of information we have in the metadata section. So basically the producer of this PDF is Acrobat something software here. The creator is this, the creation date. We also have when the when the PDF was created. And then we have a title for this. We also have a file name. The total number of pages are 24, and then we are on page 0 and the page label is 1. So these are the additional informations that we have in the PDF metadata. And then if you closely look here, we use the same approach as we did earlier using this particular loader while loading a file here. The only difference that we've done is we have used a PyPDF class in this particular case, and then the loading mechanism is the same. So this is how we can import our PDF files into our LangChain ecosystem. All right. Now that we've handled individual files, both text and PDF, let's scale things up a bit. In real-world RAG projects, you rarely work with just one document. More often, you have entire folder full of files, multiple PDFs, books, chapters, notes, reports, manuals, or datasets scattered across a directory. Loading them one by one is not only time-consuming, it's also error-prone, messy, and completely unscalable. And that is exactly where Directory Loader shines. Directory Loader acts like a smart crawler for your local file system. You point it to a folder, tell it what kind of files you care about, and specify which loader should process those files, and it takes care of the rest. It walks through the directory, finds every title that matches your pattern, and automatically feeds each one into the right loader. The beauty of this is flexibility. For example, if your loader has 20 PDFs, you don't have to write 20 different load commands. Just give the directory loader a glob like PDF, attach the PyPDF loader, and every PDF in that folder becomes part of your pipeline with almost no effort. But here's the cool part. Directory Loader also supports lazy loading. Instead of loading all documents into memory at once, which can be a nightmare if you're working with hundreds of large files, it loads them one by one, only when you actually need them. This makes it incredibly memory efficient, especially for large-scale RAG systems or production environments. In the walkthrough, you'll see we'll load all PDF documents stored inside a folder, and instead of printing the content, we'll inspect the metadata of each document. And this will give us a clear sense of how Directory Loader organizes and streams document without overwhelming our system. So if your AI assistant needs to ingest entire libraries, batches of reports, or bulk research material, Directory loader is the tool that makes that workflow not just possible, but clean, scalable, and efficient. So let's dive in and see how it handles an entire directory of documents. So for this demonstration, I have a folder called docs, and inside that I have 3 different PDF files. Now, to load the document of all these PDF at once or from inside this folder, I'm going to use directory loader. So from LangChain underscore community dot document loaders import directory loader, and then I'll also use a PyPDF loader. So I can directly call my directory loader class and then create its object using passing a path first. So the path is the folder location that we need to give. Let me give out docs here. Then a globe, meaning this will represent what kind of files do you want to read from inside the folder. So here it can be any file with extension .pdf, which means all of these 3 files will be read from inside or by this directory loader. And then finally I'll need to provide the loader class, which is going to be the PyPDF loader. Okay, so as we did earlier, where we are going to do docs equals to loader.load, and then basically I can print out the length of docs here, and also see the metadata of our document or loaded document. So let me clear this and then run this code. So since we have 3 different documents, it is not going to take so much time because these are small documents here. But when we are processing a large number of documents inside a text, then it can be somewhat slow. Anyways, the metadata here contains producer key, creator key, creation date, author, mod date, title, source, total pages, page, and yeah, things like that. But as I told you, there's also a feature of lazy loading our document here. So for that, let me comment it out, and then I'm going to do docs equals to loader dot lazy load. Now for documents in docs, I do not need to load all the data at once. Once one data or one PDF file is loaded, then it is going to show my metadata or show the files metadata in the output here. So let me rerun this again. So yeah, there are a lot of pages in this particular document, and then it did not at once produce the result, but it did it slowly, loading the document one by one, and then basically loading the pages one by one here. So this is how we implement directory loader in LangChain ecosystem. Now that we've explored loaders that work with local files like text, PDF, and even whole directories, it's time to step outside our machine and walk into the wild, unpredictable, and glorious jungle called the internet. And honestly, this is where things get really interesting. Because in real world rack systems, your data isn't always neatly stored on your laptop. Sometimes it lives on a web page, sometimes it's inside a blog, sometimes in an online review, a product page, or a government site that refuses to format anything properly. And without a proper loader, trying to extract structured content from a live web page feels like trying to drink water from a fire hose. Messy, chaotic, and guaranteed to cause pain. And this is where web-based loader steps in like a digital superhero. With web-based loader, you can point to any URL and it jumps in, pulls out the readable text, cleans it, structures it, and hands it back to us like, here you go. Would you like this in a list of documents? And the best part is that we can instantly plug that loaded data into any of our LLM pipelines. So in this episode, or in this video now, to make things realistic, we will actually fetch a real web page and show you how easy it is to extract content from it. And to make it even more fun, we'll turn this raw web page into a tiny question and answer engine. We'll take the article text, feed it into a prompt, connect it to our model, and boom, ask the system a direct question about the web page content. No manual copy pasting, no scrolling, no headache. Just a clean loader that is invoked with a clean chain, and we get a clean answer. So this is the true power of document loaders. They're not just utilities, they are the foundation of a robust, scalable, real-world ready workflow. And web-based loader in particular opens the door for endless possibilities. Product comparison bots, news summarizers, Nepali market research tools, travel information assistants, you name it. So let me now show you how effortless it is to fetch a live web page, load it, and immediately ask meaningful questions from the extracted text. So let's jump in. So here I'm first going to start with my import. So from LangChain community dot document loaders, we import web-based loader. Then from LangChain grok, we import chatgrok. From .env, we import load.env. From LangChain core .output parsers, we import str output parser. Then from LangChain core .prompts, we import prompt template. And yeah, so as I said, we are going to turn this into a Q&A engine. So hence I'm importing all the models, the prompt template, and then the output parsers. So first of all, load the credential from .env file. I'm going to define my model. My model will come from chatgrok. I'm going to use llama model. .3. Okay. Now I'm going to define a prompt here. So the prompt is going to be from prompt template. First of all, I'll write down the template for this one. So the template will be answer the following question. I'll keep my question inside a placeholder. Question from the following text, and then I'm going to I'm going to keep text inside another placeholder. Now everything will be wrapped inside our input variables, all the placeholders especially. So question will be one, and then text will be the other. Okay, so let me go for the URL. So the URL I'm going to use is this one. Okay, first of all, let me make sure that the page is live. Otherwise, we'll get an error here. So, yeah, so the page seems to be live. So let me just paste down the URL. You can use any other URL of your choice, especially if that URL is kind of an article. So now I'm going to use or define loader object using web-based loader class, and then I'll pass in the URL, and then I'll do loader.load just as I did earlier. Now I'll define the parser using str output parser, and then I'm going to invoke a chain. So the chain will first take in a prompt. It will be passed to the model and then to the parser here. Now I'm going to invoke the chain. So result equal to chain dot invoke. I need to pass in the question here. So the question is going to be, what is the article talking about? Okay, let me see, what is the product the article is talking about? And then I also need to pass in the text. So for text, what I'm going to do is I'm going to do docs 0.page content, because I think it will contain the header that we want, and then from the header my model can answer the questionnaire. So basically this is about car price in our country, so I should get the appropriate answer based on my questionnaire. So now I'm going to print out the result. So print result, and then let me run this now. So clear everything in the terminal. So Python document loaders, and then for web-based loader.py. Okay, so it might need some package. Okay, so let's go to requirements.txt. I think it needs beautiful soup 4. So let me just install bs4 inside this. And then I'm going to do pip install bs4 directly, not from the requirements, because it will be done automatically from the requirements if I run it. But anyways, let me clear this and then rerun the code again. So it will try to scrape the content from the page and then try to answer here. So the product being discussed in the article is the Dongfeng Nami Vigo, an electric SUV launched in Nepal. So this is our answer. So this is how we can use web-based loader and basically scrape content from any website or any readable website, and then basically build a. Now that we've played with web pages and see how LangChain can transform online content into structured query-ready data, let's shift gears and move into a format that almost every real-world project eventually deals with, and that is CSV files. And honestly, CSVs are everywhere. Whether it's marketing data, survey results, user activity logs, bank transactions, product catalogs, education dataset, or government report, if someone hasn't figured out a fancy format yet, chances are it's a CSV. But here's the funny part. Even though CSV files feel simple, working with them in RAG pipelines is not always straightforward. You can't just give raw rows to an LLM and expect it to magically understand the context, the columns, the meanings, and the relationship. And that is where the CSV loader comes in, with a surprisingly elegant solution. CSV loader doesn't treat the dataset as a one giant blob. It goes row by row and converts each row into separate document object. This means each row becomes its own little knowledge packet, a self-contained chunk of information that the LLM can reason about individually. And this opens up endless possibilities. You can build a recommendation system from your product CSV, a customer segmented chatbot, a resume filtering agent, a dataset exploration assistant, and even a data auditing tool that checks for anomalies row by row. All powered by LLMs and all starting from something as simple as a CSV. So in this part, I'll load a simple CSV using a CSV file loader and show you how magically it transforms each row into a document object. This will give us full flexibility to process, chunk, search, map, or feed each row independently into an LLM chain. So let's take this very common and very practical file format and turn it into something intelligent, structured, and ready for any RAG workflow. So let's dive into CSV loader. So here I've first considered a CSV file called ads.csv, and then it contains a row user ID, gender, age, estimated salary, and so on. So this is my CSV file that I'm going to import here in CSV loader using my CSV loader from document loader class in LangChain community. So from LangChain underscore community dot document loaders import CSV loader. Now I can just call loader equal to CSV loader and then provide in the file path. So file path is going to be ads.csv, which is my file. And then here I'm going to do loader.load, just like I did in the earlier videos. So one document object for each row here. So let me just print data 0 first and then see what happens or what kind of result we get here. So Python what is it? So 6 document loaders. Let me do this again. So Python 6 document loaders and then 5 CSV loader.py. So as you can see, our very first row is being loaded here. So the page content is user ID, and let me verify this here. So the page content is user ID, gender is male, age is 19, and then the estimated salary is 190,000. And then in case of the metadata, we have a source which contains a file name, and then the row number from where this page content is being generated. So this is how we can load a simple CSV file in the LangChain ecosystem using the CSV loader class. And that wraps up our exploration of the most essential document loaders in LangChain. We saw how different formats like plain text, PDFs, folders full of documents, live web pages, and even structured CSV files can all be transformed into clean, consistent document object ready for intelligent processing. These loaders might look simple on the surface, but they're actually the backbone of a very powerful RAG system. Because without properly loaded, structured, and well-organized data, even the biggest LLM will struggle to give accurate, grounded answers. What we're doing in these episodes is actually building the foundation piece by piece. So each loader, each concept, each mini project, they're all stepping stones towards a complete end-to-end retrieval augmented generated pipeline. So in the next video, we continue moving forward and dive into text splitters, which is another crucial building block of RAG, where we'll see how to break large documents into meaningful LLM-friendly chunks. So stick around, because everything we're learning is leading us to a moment where we assemble the entire RAG system and make it work beautifully in the real world. Now that we've learned how to pull information from text files, PDFs, directories, web pages, and structured datasets, you might be thinking, great, I have the data, but it's huge. Now what do I do with it? And that right there is the exact moment why every RAG developer discovers their next big challenge. And that LLMs cannot handle your entire document at once. Your book is too long, your PDFs are too dense, and your scraped web page is full of mixed content. And your CSV rows are too large to process as a single block. So before we can retrieve, analyze, or generate anything intelligent, we need to break the data down into smart, meaningful, and manageable pieces. And that's where text splitters are the unsung heroes of every successful RAG system. Think of them as the editors of your pipeline. They decide where a paragraph should end, how much context belongs together, and what size of information the model should see at a time. They prevent your LLM from choking on massive documents and ensure your retrieval accuracy stays sharp and relevant. In this video, we're going to explore how splitting works, why size matters, and how different splitting strategies suit different real-world needs. For example, sometimes you want a very simple fixed size slicing of your text. Clean, predictable chunks for straightforward tasks. Other times, you need something smarter, something that can look at your text structure and then choose the best breaking points, like respecting headings, paragraphs, or punctuation. And then there are the scenarios where code enters into the picture. Code isn't like regular prose. It needs indentation, functions, classes, and logic to stay intact. Splitting it blindly can actually remove its meaning. So we'll explore how to split code safely and intelligently. And finally, we'll look at a modern AI-driven approach where chunks are formed based on the meaning of the text, not just its shape. This ensures that related ideas stays together and unrelated content doesn't accidentally gets bundled into the same chunk. So these different styles of splitting gives you complete control depending on the scenario. Maybe long articles, research paper, scrapped web pages, multi-label structured documents, datasets, and even complex coding scripts. By the end of this episode, you'll understand why chunking is one of the most important steps in building a high-performance RAG, and how different strategies protect the context quality and how they affect the accuracy of retrieval later in the pipeline. And This is where your data truly becomes LLM ready. So let's dive into the world of text splitters and prepare your documents for the intelligence layer that's coming up next. So now that we understand why text splitting is essential, let's begin with the simplest and most straightforward form of splitting, which is the character-based text splitter. This splitter doesn't try to be any smart. It doesn't analyze structure, it doesn't look at headings, paragraphs, or meaning. Instead, it follows a very direct rule. Take the text and chop it into blocks of fixed character length. Think of it like slicing a long rope into equal pieces with a ruler. Cut every 100 characters, cut every 500 characters, or cut every 1000 characters, and so on. You decide the size. The splitter will follow it blindly. But why is this useful? Because sometimes simplicity wins. If you're dealing with extremely unstructured text like raw logs, old scanned documents, transcripts, or OCR outputs, there's often no reliable formatting or paragraph structure to respect. In those cases, a character level splitter is predictable, consistent, and surprisingly effective. You also get full control over two factors. The first is the chunk size, meaning how big each piece should be. Smaller chunks will be easier to process but more retrieval calls later. Larger chunks will be more context richness but heavier for the model. And the next is the chunk overlap. How much each chunk should remember from the previous one. Overlap is useful when you don't want meaning to be accidentally cut in the middle. But if you are working with very clean slices or very short chunks, you can keep it at 0. And what are the trade-offs here? Character-based splitting doesn't understand semantics. So if the text suddenly breaks mid-paragraph or mid-sentence, it doesn't care. Its job is not to preserve meaning, just to break things consistently. But for a lot of projects, especially in early RAG prototypes or fast experiments, this type of splitting is more than enough. It gives you a clean set of manageable chunks to feed into embeddings and retrieval. And then in our demo, we'll see how we load a PDF, slice it into fixed size character blocks, and print one of those chunks. Nothing fancy, just simple mechanical text cutting. And because of that simplicity, it is one of the fastest and most widely used splitters when you don't need structural awareness. Okay, so we'll start with something very simple. So from LangChain _text splitters, we're going to import character text splitter. And from LangChain community dot document loaders, we'll import a PyPDF loader. So now we will have one of our PDF file and then read it using PyPDF loader. So I'm going to read this audit report.pdf file that I have in my project folder. Now I'm going to load this first. So docs equals to loader.load. Okay, so once we load our document, I'm going to define my splitter object using character text splitter class. And then here I need to provide two variables. The first is chunk size, and then I can mention the chunk size as the length of the characters I need in one chunk. So let me give it 500, and then I will also provide a chunk overlap. The chunk overlap can be used as maybe 50 characters. 50, okay. And then let me define a separator. So a separator can be an empty space here. Okay, so in case of result, let me split my text using splitter.split documents. Since we have loaded our PDF in the form of document here, so we use split documents here. And then we use text. Now basically we are going to not print the whole result, but we're going to print the just one part of the result and then see its page content. And also we can print its metadata. So now let me run this. So Python 7.textsplitters and then 1.characterTextSplitter.py. Okay, so I might have missed something. Yes, I have missed a comma here. So let me do this again. And then save it, and then run this code again, and I can see that okay, it is taking some time to run, so let's wait. I think the PDF file is too long, that is why it is taking some time. So yeah, I've split, or like the page content is being printed here, which contains around 500 characters, like I said, and then it also can, and then I can also easily extract its metadata here. So this is from page 0, but the page label here is 1. Basically, it is the second part of our splitted text here. So this is how simple it is to use a character text splitter. Similarly, I can also split my text contents easily using this character text splitter here. So suppose if I have any text like Python text like anything, so this is a LangChain tutorial, so you are going to learn a lot in this series. So if we have this text, we can also use the same splitter, but the function will be quite different here. So the function that we are going to do here is splitter dot split underscore text, and then I need to pass in the text here. So this will also work if we have a string text in our project, or if we have a document, we can do the same using split documents too. So let me comment this out, and then you can try this on your own later on. Now that we've seen the simplest form of text splitting, let's move one step ahead into something far more thoughtful and adaptable. That is the recursive character text splitter. If the basic character text splitter is like cutting a rope into equal pieces using a ruler, then the recursive version is like having a skilled editor do the cutting for you. Instead of slicing blindly at fixed character intervals, the splitter tries to preserve natural language structure as much as possible. It works through a hierarchy of separators, almost like a checklist. First, can we split by paragraphs? If not, can we split by double new lines? If not, can we split by sentences? If not, can we split by commas? And only when nothing else works, break by characters. It keeps doing this hierarchy recursively, always choosing the best possible cut that keeps the text coherent while still meeting your chunk size requirement. And why do we need this? Because when you're building RAG apps, semantics matter. You want your chunks to feel natural. You want ideas to stay together, and you don't want a paragraph about space exploration sliced in the middle of a sentence or a bullet point chopped completely out of context. Recursive splitting solves this beautifully. It allows the model to receive chunks that feel more human and more meaningful, which drastically improves both embedding quality and retrieval accuracy. What actually happens under the hood? So imagine you give the splitter 200 characters as the limit. It first tries, can I keep whole paragraph under 200 characters? If they fit, then great. If not, it drills down. Can I split at new lines? If the text is still too long, it drills. Sentences? Still too long. Words? And still too long. Alright, now it's time to cut at characters. This small fallback approach is what gives it the name recursive. It recursively tries the next best splitting rule until a chunk fits your defined constraint. So what does this mean for you? It means your chunks maintains context, keep sentences intact, feel more natural, work better at or for embeddings, and improve your RAG pipeline's retrieval performance. So in the demonstration that we're going to do, we will provide a short sample paragraph about any topic, something with clear sentence structure and flow. Then the recursive splitter will intelligently break it into pieces that preserve meaning without forcing random acts. It's like having a text splitter that actually respects the writing instead of slicing it like a robot. And with this, we move from a mechanical cutting to structure-aware splitting, bringing us closer to the world of truly optimized RAG processing. So first of all, we are going to import recursive character text splitters. So that will come from LangChain. underscore text underscore splitters, import recursive character text splitter. Then from I don't think I need a PDF loader here. So anyways, I'm going to import some text, and then this particular text will be chunked using the recursive character text splitter. Okay, here is the text. I've just copy pasted it in case it'll be easier for you to read it. So I'm going to do word wrap. So this is a small text content which is about space exploration here. So now I'm going to define my splitter object, and then that will be defined using recursive character text splitter. Then you provide the chunk size. So let's provide the chunk size of 200, and then let's do chunk overlap of maybe 100, or maybe do 10. So if this is it, then I am going to split using splitter dot, since this is not a document, this is only a text, so I can use split underscore text function and then pass in my text here. So let me print out the result and then see if it actually preserves the meaning before it tries to split it. So first of all, activate the virtual environment. So my venv scripts, and then activate, and then run this. So Python 7.text splitter and then 2.recursive character text splitter. Okay, so if I run this, then I should see my result. So my result contains two different splits here, or multiple splits in fact. So the first split that I can see begins from here to this particular full stop here. So the entire sentence meaning is captured here, meaning it's not breaking out in the middle of the sentence in between words. Similarly, here if we see, it did try to preserve the semantic meaning, but it had to break it down in between of the sentences, because it could because the next sentence was too long, and then it tried breaking it down. Maybe it tried doing it on the comma, but the length of the context was too short. So yeah, it broke down in the middle, and because I have a chunk overlap of 10, the word medical is being preserved from the previous context to the next context, or the previous chunk to the next chunk. So this is how we implement recursive character text splitter. Similarly, if you have a document, you can simply load your document using PyPDF loader, or like any other type of loaders that we've talked about in the previous video, and then basically use split underscore document function to split your document content. So just like splitting the text, what we can also do is we can also split codes. LangChain ecosystem also support the split of code, but whenever we're splitting a code, we need to preserve some form of semantic meaning in the code. The code might contain class, functions, or statements, maybe conditions, loops, etc. So whenever we are trying to break down our code into different chunks, or our code content into chunks, we want to make sure that the semantic meaning of the code is also preserved, meaning the chunk is not broken down in the middle of a statement, or it is not broken down in the middle of a class declaration or a function declaration, or in between a condition. So now we'll see how LangChain ecosystem supports that exact breakage of context into chunks whenever the content is in code, and then we'll take an example of Python code here. So for this implementation, we're first going to import recursive character text splitter. So for that, let's import it using LangChain text splitters. Import recursive character text splitter. We'll do it using two ways. So let's also import Python code text splitter and then a language here. So now let me copy a block of Python code and then paste it here, and you can pause the video and then see what is pasted here. So we have a Python class called student. It contains an init function with name as age and grade as its parameter. Then we have getDetails method, and then is passing method here. Then we create a student1 object, and then we basically print out the details or basically call the get details function. And also we have implemented an if else condition to check if the student is passing or not. Now to split this particular code here, what we're going to do at first is use the splitter using recursive character text splitter. And then here we're going to call the recursive character text splitter dot from lang. I think, oh, okay. So I think this is already deprecated. So here what we're going to do is we're directly going to do Python code text splitter. Then we'll define a chunk size. So the chunk size will be 300. The chunk overlap here will be 100. And then let me split my text here. So splitter dot split underscore text. Again this is a text content, so we'll use the split text function. If this was from a Python file or someplace else, we would use split docs here. So we'll pass in the text, and then basically we will print our chunks here. So let me see, or we'll see our chunks here. So yeah, use this text splitters and then 3.python text splitter. So if we see the chunks here, then the first chunk begins from here to the end of our init function. I think wait, so this is inside our isPassing function. isPassing function, isPassing, is this isPassing? Yeah, so we have our first chunk until here from the top, and then the next chunk is from the isPassing function again, because we have done some chunk overlap. So the next chunk goes from here down to the end of our code. So in this way, the semantic meaning of the function or the Python code is preserved. The chunk is not broken down in the middle of the statement, or without including maybe the function declaration and the function statement here. So this was possible using recursive character text splitter in the old library, but now it seems to have been removed during the new update. So along with Python code text splitter, you can also find some other, I think you'll also see some other type of text splitters here. So HTML section splitter, JS. For JS we have JS, then I think we should have something for NLTK2, then Spacey2, and then stuffs like that. So yeah, this is how we can split our code, not only text but also code using the splitter function from LangChain text splitter module. And with that, we wrap up one of the most important building blocks of any retrieval augmented generation workflows, which are text splitters. We started by understanding why splitting matters, how unstructured documents can overwhelm an LLM, how large chunks reduce accuracy, and how tiny chunks breaks context. Then we went hands-on with different splitting strategies. We began with a simple size chunking approach. We moved into the more intelligent and adaptive recursive character text splitter, which gives us fine-grained control without manually defining every rule. And then we even explored how the recursive splitter can adapt to code, respecting its structure and logical boundaries. So all of these tools gives us the power to recognize messy, unstructured content into rich, meaningful, model-friendly chunks. So this is a stage where our raw documents begin transforming into something an AI system can understand and reason over. And now that our documents are cleanly chunked, structured, and ready, the next step is to give them a vector meaning. So in the next episode, we move into one of the most crucial concepts in all of RAG, which is embeddings. We'll learn how text turn into numbers, how similarity search work, and how embeddings power the intelligence behind the entire retrieval system. So get ready, because this is where we start stepping into the real magic of RAG. Now that we know what we are sending into our retrieval system, it's time to understand how the system actually understands those chunks. And today, we move into one of the most crucial components of any RAG pipeline, which are embeddings. So embeddings are how we turn raw text into mathematical representations. Those are dense vectors that capture meaning, relationships, context, and even subtle nuances between words or sentences. In a traditional keyword search, the system looks for literal word matches. But with embeddings, the system looks for semantic similarity. It understands that the two words doctor and physician are related, even if the exact words never appear. This is what makes your retrieval intelligent, adaptive, and capable of handling natural language queries gracefully. We'll talk about why embeddings are absolutely essential in modern RAG pipelines. First, they allow your system to perform semantic search, not keyword matching. They let you compare and retrieve related ideas even when phrased differently. They enable vector databases to rank responses by meaning, and they form the foundation of context injection for LLMs. After we understand the concept clearly, we'll jump into hands-on demonstration. You'll see how to generate embeddings from your text chunks, store them, and prepare them for vector search. And by the end of this video, you'll be fully equipped to move from text processing to true semantic understanding. So let's get started. But before we dive into embedding models and their implementations, let's start with a bigger idea that makes all of this possible. That is, the vector space representations. In natural language, words are abstract. They carry meaning, relationship, intent, and context. Things that a machine cannot understand directly. But if we convert words into vectors, numerical points in a multidimensional space, something magical happens. Words that are similar in meaning end up close to each other, and words that differ in meaning naturally drift apart. So this is the essence of vector space representation in NLP. We take language, something humans understand intuitively, and map it into geometry, something computers understand perfectly. And this is meaningful because now we can measure similarity not by matching letters or keywords, but by measuring the distance between 2 points in space. This is why classic examples like king minus man plus women is equivalent to king, and even the doctor is equivalent to the word physician. The geometry captures semantics. But instead of manually designing these vectors, which is impossible at scale, we use embedding models. These models convert text into fixed size vectors that preserve meaning, context, relationship, and even the tone. And we can do this not just for words, but for sentences, paragraphs, and entire documents. Now, if we connect this to RAG, and when we ask a question inside a retrieval augmented generation system, the LLM doesn't search for keywords. It converts the question into an embedding, places it in the same vector space as your document chunks, and finds the closest vector that is the most semantically relevant piece of information. You can think of RAG as the scaled version of finding similar words in the vector space as shown here. But instead of comparing single words, we're comparing the entire chunks of knowledge. Instead of searching one dictionary, we are searching thousands or millions of vectorized text space. And this is why embeddings are absolutely foundational in RAG. They identify how your chunks are represented, they identify what gets retrieved, and they determine how accurate your final answer will be. So in this video, we're going to explore this concept hands-on. After understanding the intuition, now we'll generate real embeddings using a Hugging Face embedding model and use them the way RAG systems do to find meaningful, semantically similar document chunks in the upcoming videos. So let's begin the implementation part.
So here, for this implementation, I've already created an API key from Hugging Face Hub and then pasted it into my .env file. Now, let's import LangChain underscore Hugging Face. Sorry, Hugging Face LangChain underscore Hugging Face import Hugging Face embeddings. So not sure why this is being too slow, but anyways, the import is correct. And from .env import load underscore .env import load underscore .env. So let me load the credential first, and then I'm going to define my embedding model here. So my embedding model is going to come from Hugging Face embeddings, and the model name will be sentence transformers all mini LM L6 V2. So this will be my model for today. And here the text that I'm going to convert it into a embedding vector will be this one. So New York is a busy city with a lot of population. So this is a text that I have here. Now what I'm going to do is I'm going to do embeddings dot embed query and then simply pass in the above content here. Now if I print out the result and let me run this. So to run this, let's first of all I'm going to activate my virtual environment. And once that is done, I'm going to do Python. Okay, what is the folder name? So 8, sorry, not here. Python 8 embeddings and then 1 Hugging Face embeddings.py. So if I run this, I should see a list of numerical values here. It might take some time because the model might need to be downloaded and then downloaded locally, and then maybe it needs to be run, or I think it will not download the model. Instead, it is going to access the model through the Hugging Face API key directly here. So let the embeddings be loaded and then I'll show you. Okay, so as you can see, I can see a collection of numbers here. And then this is the embedding vector for this particular content here. So if we had some documents here, then we would use the embed docs function instead of embed query functions here. So this is going to be absolutely essential in our upcoming videos, where we are going to implement the RAG based systems here. So this is all for the implementation. And that brings us to the end of our deep dive into embeddings. So we explored how vector space representations give meaning to language, how embeddings convert text into meaningful vectors, and why this entire process is the backbone of any retrieval augmented generation system. Whether you're dealing with short phrases, large documents, or entire knowledge bases, embeddings are the bridge that allows LLM to understand, retrieve, and reason over your data. So in this demo, we saw how easily we can generate embeddings using Hugging Face models, and how these vectors open the door to semantic search, relevance scoring, and intelligent retrieval. So in the next video, we're going to take this a step further. Once we generate the embeddings like you see here, we need a powerful way to store, index, and search them efficiently, and that's where vector store comes in. So we'll explore what they are and why they matter, and how to use them to make retrieval blazing fast and scalable.
Now that we know how to generate embeddings, the next big question is, where do we store these embeddings? And even more importantly, how do we search through them efficiently when our dataset grow from a few lines to hundreds of pages or even millions of documents? And that is where vector store comes in. Vector store are specialized databases designed to store embeddings and perform fast similarity search, which is the core of retrieval augmented generation. Whether you're building a chatbot, a document assistant, or a full-scale enterprise knowledge system, Vector Store identifies how quickly you can search, how accurately you can retrieve, and how scalable your system becomes. In LangChain, we have multiple vector store options, but two of the most commonly used are Chroma, a lightweight, local, fast, perfect for prototyping, and FAISS, Facebook's highly optimized similarity search engine for large-scale applications. In this video, we'll explore both. We'll take the embeddings we generated earlier, store them in a vector store, and then gradually run semantic search to retrieve relevant content, just like a real RAG pipeline does at scale. So, let's dive in. Now that we understand what vector stores are and why they are essential for scalable semantic search, let's look at a practical option that fits perfectly into most LangChain workflows. The first vector store we are going to work with is Chroma. Chroma is built to make working with embeddings incredibly straightforward. It allows us to take our text chunks, convert them into vectors using an embedding model, and store them in a way that supports fast similarity search, all without worrying about heavy infrastructure or complex configuration. This makes Chroma an excellent choice when you are prototyping RAG systems, building local AI assistants, experimenting with document retrieval, or even running small to medium scale production workloads. You can think of it as a plug and play vector store that lets you focus on logic rather than setup. Another important aspect of Chroma is how naturally it fits into the LangChain ecosystem. Once your data is inside Chroma, you can immediately use it with retrievers, chains, and agents. Querying it feels no different than asking questions over your documents, except now the retrieval is driven by semantic meaning rather than exact matches. In this section, we'll take a small collection of text, generate embeddings using a Hugging Face model, store those embeddings inside Chroma, and then run a similarity search to see how the most relevant pieces of information are retrieved. This will give you a very clear mental model of how vector store works in practice and how Chroma acts as the storage and retrieval engine behind a real RAG pipeline. Alright, let's move into the code and see Chroma in action.
So for the sake of this implementation, I'm going to install a library here called ChromaDB and then LangChain Chroma. So I've added it in requirements.txt. You can install it, install these two from requirements or install it separately in your virtual environment too. So let me activate my virtual environment first and then start coding on this. Activate. Sorry. Wait. Okay, so my virtual environment is activated. Let me go to the code, and at first from LangChain underscore Chroma, I'm going to import Chroma. Then from LangChain Hugging Face, I am going to import Hugging Face embeddings, and from .env, I'm going to import load.env. So first of all, load the credential here, as I'm going to use my Hugging Face embedding model. So I have created an API key from Hugging Face Hub to use the Hugging Face embedding model here. So you need to paste in that particular API key first into your environment file and then do the code here. So load.env loads that particular Hugging Face API key into my code here. So I'm going to provide a few text here. So my text is going to be a collection of sentences. So let's say the first text is large language models are trained on massive data sets. The second is large language models, or let's call it LLMs, are particularly trained using transformers. The third sentence is Chroma is a lightweight vector store used in LangChain. And the fourth sentence that I'll have is embeddings convert text into numerical representation. Okay, so these are going to be my 4 sentences here that I'm going to convert into embeddings, and then I will store it into my vector store. So for the embedding model, I'm going to define my Hugging Face embeddings class and then use this sentence transformer all mini LM LXV2 model from Hugging Face embeddings. Now, once we have this embedding, we're going to create our vector store. So vector store is going to come from Chroma dot from underscore texts. In the text part, I'm going to pass my text variable all from here text. Now in the embedding part, I'm going to pass my embedding model that I have here, and then in collection underscore name, since this is going to be saved in our disk, so I'll name it LangChain underscore Chroma underscore demo. Okay, so now this will convert all of this text into embeddings and then store it inside this particular location here as a vector store. Now what I'm going to do is I'm going to pass in my query. So let me ask, tell me more about LLMs. Now what this is going to do is, if I use my vector store similarity search with my query and then ask for maybe our top 2 result, what this is going to do is it is going to convert this query into embeddings as well, and then run a similarity search on each of these embeddings stored in the vector store, and then it will give me the 2 most matched content or answers from the vector store here. So I can just print out the results and then see what happens. So let me run this. So Python, this is 9 vector stores 1 chromadb.py. So now that we see in the result, we have 2 different result here. Basically we have asked for top 2 results here. So in the first case, it's called large language models are particularly trained using transformers, and in the second case it has large language models are trained on massive data sets. So basically it understands that LLMs refer to large language models from this above context here. So this is how we use Chroma in case of our vector database.
So far, we've seen how Chroma helps us store embeddings and perform semantic search in a very simple and developer-friendly way. It's lightweight, easy to set up, and perfect when you're experimenting, prototyping, or working with smaller to medium-sized datasets. But as your RAG application grows, a new question starts to appear. What happens when you're no longer dealing with hundreds of or thousands of embeddings, but we're dealing with millions? And that is where FAISS comes into the picture. FAISS, which stands for Facebook AI Similarity Search, is built with one primary goal in mind: fast and scalable similarity search in high dimensional vector spaces. Unlike Chroma, which focuses on ease of use and persistence, FAISS is all about performance and efficiency. Think of it this way: with Chroma, you're working with a vector database that manages storage, collections, and metadata for you. It feels very close to working with a traditional database, just adapted for the vectors. FAISS, on the other hand, behaves more like a high performance search engine for vectors. It doesn't try to be a full database. Instead, it specializes in how quickly and accurately it can find the nearest vectors, even when the dataset becomes extremely large. Another key difference is how they are typically used. Chroma is often used as a persistent vector store, meaning your embeddings can live on disk, reload easily, and integrate smoothly into end-to-end RAG pipelines. FAISS is commonly used when you need very fast similarity search. You're dealing with large-scale embedding datasets, and you want fine-grained control over indexing strategies and performance trade-offs. In real-world RAG systems, FAISS often powers the retrieval layer when scale becomes critical, especially in research or enterprise-level applications. So conceptually, both Chroma and FAISS solve the same problem: storing and searching embeddings, but they do it with different priorities. Chroma prioritizes simplicity, persistence, and developer experience, while FAISS prioritizes speed, scalability, and efficient nearest neighbor search. So in the next part, we'll take this idea and actually implement FAISS in LangChain. So you can see how embeddings move from text into vectors and finally into a high performance retrieval system that sits at the heart of modern RAR architectures.
So for the implementation of FAISS Vector Store, again, I'm going to install this library called FAISS CPU. Again, I pasted it in requirements.py, so you can do it from here. And then I will go to my FAISSVS.py, and then I'm going to start importing now. So from LangChain Hugging Face, I'm going to use the same model as I did earlier. Import Hugging Face embeddings. Then from LangChain underscore community dot vector stores, I'm going to import face. Then from .env, I'm going to import load.env, load the credential first, and then I am going to define some text here. So this will be related to cricket. Let me just paste this so that it will not take any unnecessary time in our video. Let me close this now. Let me also do a word wrap so that you understand what kind of data we have. So this is all about cricket. And then I have 1, 2, 3, 4, 5 text sentences, which is about cricket here. So now I'm going to define my embedding model. Again, I'm going to use the same model, the sentence transformers, all LM, all mini LM, LXV2. Now, while creating vector store, I'm going to do a vector store equals to FAISS dot from texts. And then in the same pattern, I'm going to provide in the text. This is going to be my cricket underscore text. It will come from here. And then along with this, I'm going to pass in my embedding function. So embedding equals to embeddings that I've created here. So once this is created and our embeddings are saved in our vector store, I'll pass in a query, and the query will be maybe who is known as, or who is the god of cricket. Okay, so this is my question. Then what I'm going to do is I'm going to run a similarity search on the vector store. So results equals to vector store dot similarity search. I'll pass in my query, and then maybe I'll only try to retrieve the top one result here, because there can only be one god of cricket. And then in our second text, his name is Sachin Tendulkar here. So it should extract me the exact same sentence from the vector store using this similarity approach. So now if I print my results, and let me rerun this again. So now 2.vs.py. So as you can see, my answer is retrieved, and then the exact sentence that I'm looking for is extracted using this similarity search. So we can even do this for documents. If we have documents, we simply need to do FAISS from documents and then pass in our document here, and the embedding function will be the same. So this is how we can implement FAISS in our in terms of our vector store here.
And that concludes our deep dive into FAISS and how it allows us to store embeddings and perform semantic searches efficiently. We've seen how splitting knowledge into chunks and storing them as vectors makes it easy to retrieve meaningful information even for large datasets.
So far in this series, we've learned how to load data, split it, convert it into embeddings, and store it efficiently inside vector databases. But there's still one missing piece in this entire RAG pipeline. We have questions, or we have knowledge stored somewhere, but how does an AI model know what to fetch when a user asks a questions? This is where intelligent retrieval comes into play. In a real world system, you don't want to dump your entire database into the prompt. This would be slow, expensive, and completely impractical. Instead, you need a smart mechanism that can scan through massive amounts of stored information and pull out only the most relevant pieces based on user's intent. Sometimes that information can come from an external knowledge source that updates constantly. Other times, it may live inside your own vector database. And in many scenarios, it's not just about finding the closest match. It's about avoiding repetitive or overly similar results and ensuring diversity in what gets retrieved. In this video, we'll explore how LangChain enables this intelligent selection process. You'll see how context is dynamically fetched, how relevance is measured, and how retrieval quality directly impacts the final answer generated by the LLM. This is the layer that truly transforms embeddings into and vector stores into usable knowledge systems. And once you understand this, building powerful RAG applications become much more intuitive. So let's dive in. But before we jump into different retrieval strategies and their implementations, it is important to understand what actually happens under the hood when a retriever is used. At a lower level, retrieval is all about comparison. When a user asks a question, the query is first converted into same numerical representation, that is an embedding, that we used when storing our documents. Now, we're no longer dealing with raw text, but with points in a high-dimensional vector space. Once the query becomes a vector, the system compares it against all the stored vectors using similarity measures like distance or cosine similarity. The goal is simple: find the pieces of information that are closest in meaning, not just in wording. But retrieval isn't only about similarity scores. There are additional choices happening behind the scenes. How many results should be fetched? Should the system prioritize the closest match only or balance relevance with variety? Or should result come from a local knowledge base or from a constantly updating external source? This retrieval layer acts as a filter between your stored knowledge and the language model. It decides what the model gets to see and what's get ignored. And because LLMs are highly sensitive to the quality of context they receive, even small improvements at this stage can dramatically improve final answers. Now that we understand how retrievers operate at a foundational level, we can move on to exploring different retrieval approaches and see how LangChain makes each of them easy to implement in practice. We will start with a retrieval scenario where the knowledge doesn't live inside our own documents or vector databases. In many real-world applications, the information we need is public, factual, and constantly evolving. Think of topics like science, technology, history, or general definitions. In such cases, maintaining and updating your own knowledge base doesn't always make sense. Instead, the retriever directly connects to a trusted external knowledge source and pulls relevant information on demand. Conceptually, this works very differently from vector-based retrieval. There are no pre-computed embeddings stored in advance. Instead, when a query comes in, the system searches across a massive, structured repository of human knowledge and retrieves the most relevant articles or sections related to that query. This approach is especially useful when you need an up-to-date or general knowledge, when you don't want the overhead of managing your own dataset, and when the questions are more exploratory or informational in nature. Each retrieved result is returned as a document object, just like documents from files or websites. This consistency is important because it means the retrieved content can be seamlessly passed into chains, prompts, or even combined with other reviewers later on. In the code that follows, you'll see how a simple query can dynamically pull multiple relevant knowledge chunks from a large public source and make them immediately usable inside a LangChain pipeline. This gives your AI system access to a living knowledge base without you having to store or maintain it yourself. So the implementation that we're going to do is the Wikipedia Retriever. For the sake of this implementation, I don't need any additional libraries. So I can directly go to my code and then start typing. So from LangChain underscore community dot retrievers, I can import Wikipedia Retriever. Now, if I need to define the object for this, I'm going to do retriever equal to Wikipedia Retriever. Maybe I'll select the top key results as 2, and then the language I'm going to select is English. So now I just need to pass in my query. Let's call it artificial intelligence. And then basically I can simply invoke my retriever here. So retriever dot invoke query. Now, if you need to see how many documents have been extracted, you can do println docs, And to enumerate across each document, I can do for idoc in enumerate docs. Let me print the page content here or the result content here without the metadata part. So content /n comma doc dot page underscore content. So this is all I need to do. Let me run my code. So Python 10 retrievers, one Wikipedia retriever.py, and running this. Okay, so I seem to have one more library installed here. So in requirements.txt, you can type in Wikipedia, Wikipedia. So save this. I'm just going to install this from requirements. So pip install -r requirements.txt. So this will be installed inside my virtual environment. And once this is done, I can rerun my code and then check the result here. So we will allow some time for this to be complete, and then we'll continue running our code. Okay, so now this is up installed. Let me clear my terminal and then run my code again, which is Wikipedia retrievers.py. So the first thing that I should see is the number of documents that have been extracted. Simply because I've extracted the top two results, it should come as 2. And then I've only selected English language articles from Wikipedia, so it should provide me similar articles from Wikipedia. So let me go to the very top, and then I can see that I have 2 different documents extracted, and the content of first document starts from here, and then we move on to where do we go up to? Terminology, characteristics, intelligent state. We should have 2 different documents here. Let me insert a blank line so that it becomes easier for us to differentiate where these 2 documents are. Okay, so clear the terminal again and then run the same code. Okay, so the first content seems to be starting from here, and then it goes up to this point. I think we have some padding in terms of the content extraction, and then the second article is extracted from here, and then it goes up to the end of this particular part here. So the retriever, I think, is doing some form of padding to manage the sequence length that the model follows here. So this is how we can use Wikipedia retrievers in LangChain. Now we'll shift from external knowledge sources to a much more common and powerful scenario: retrieving information from your own data. In the example that we'll do, the knowledge doesn't come from the web or public encyclopedia. Instead, it comes from a small, controlled set of documents that represent information you care about. Think of this as your private knowledge base, which can be product documentation, internal notes, or domain-specific content. Before retrieval can happen, this information is first converted into a format that machines can understand semantically. Each piece of text is transformed into a vector representation, capturing its meaning rather than just keywords. These vectors are then stored in a vector database that are built for fast similarity search. Once the data is stored, we introduce a key idea here: turning a vector store into a retriever. So a retriever here acts as a smart interface on top of the vector database. Instead of manually performing similarity searches every time, we ask a retriever a question in plain language. Behind the scenes, it converts the query into a vector, compares it with stored vectors, and returns the most relevant pieces of information. The parameter that controls how many results come back is important. Too few and you might miss useful context, and too many and you might risk overwhelming the model. The retriever helps strike that balance. What's powerful here is that the retrieved results are returned as documents, the same format used throughout LangChain. That means they can be directly plugged into prompts, chains, or full rack pipelines without any extra transformation. At the end, you'll also be able to see a similarity score being returned. This will give you an insight into how confident the system is about retrieved result, which is especially useful when debugging or fine-tuning retrieval quality. So this pattern, where we store embeddings and wrap them with a retriever and query them dynamically, forms the backbone of most production-grade RAG systems. So let's go for the implementation and see that in practice now. This implementation, we don't need any additional libraries, but this is kind of what we've already done in our previous video. We've imported our Chroma, we've imported Hugging Face. The main difference here is instead of text like we did in our earlier videos, we are working with our documents, and our content is stored inside our document, and then we have a list of documents in this particular documents variable here. The embedding model is the same, and then creating a vector store from these embedding models, and then these documents is also kind of the stuff that we've already done in our previous video. Now what we're going to do is we're going to create our retriever. So for the retriever, we're going to do vector store dot as underscore retriever. So for this, I'm going to pass in the search keyword arguments, and then here I'm going to pass in k equals to 2, and then I'll define my query. So query can be what is Chroma used for. Now, unlike any other LangChain components, we can invoke this particular retriever here. So I'm going to do results equals to retriever dot invoke, and then pass in my query. Now I can simply print my results here. So now let me run my code. I'm already in my terminal. So if I run this particular vector store retriever.py, then I should see the top two results from these above documents, and then the result should be based on the match between the query and the document present above here. Okay, so let's see the document ID. We have so many more documents here. Almost everything is provided as our answer here. So Chroma is a vector database optimized for LLM based search. We only asked for 2, but it kind of provided us with 4. I think sorry, I did some wrong with the spelling here. So we'll only fetch the top one result in this particular case. Let me clear this up and then run this again. So I should only get one result here. So basically it will be for this particular query, what is Chroma used for, and then my possible answer should be Chroma is a vector database optimized for LLM based search. So let's see if we get that answer or not. So we indeed get that answer here. Chroma is a vector database optimized for LLM based search. Since we only asked for one result, we only got one result here. So this is how we can use our vector store as a retriever in LangChain. Now we'll talk about a retrieval strategy designed specifically to solve one of the most common problems in semantic search, which is redundancy. When we rely on similarity scores, the retriever often returns documents that are very close to each other in meaning. While this may sound ideal, it can actually hurt performance because the language model ends up seeing the same idea repeated multiple times, just phrased slightly differently. This is where maximal marginal relevance or MMR comes into play. MMR works by optimizing two things at the same time. First, how relevant a document is to the user's query, and second, how different that document is from the ones already selected. So instead of selecting all results purely based on similarity of the query, MMR selects the first most relevant document, then carefully chooses the next one by penalizing candidates that are too similar to what's already been picked. In simple terms, MMR asks, is this document useful for answering the question, or does it add something new? And this makes MMR especially powerful in scenarios where documents overlap in meaning, the knowledge base contains paraphrased or repeated content, and you want broader coverage instead of a narrow repetition. The balance between relevance and diversity is adjustable. One parameter controls how importance is given to matching the query, while the other encourages diversity among the results. Tuning this balance helps you shape the quality of retrieved context depending on your use case. The result is a retrieval set that is not only relevant but also informative, complementary, and diverse, which significantly improves how well an LLM can reason over the provided context. And this is why MMR is often preferred in production grade RAG systems where quality or context quality matters as much as context relevance. Now, let's see the implementation. So for this implementation too, we've jumped over some steps here. We are using our FAISS vector store, using our Hugging Face embeddings, and then documents. So I have these contents in the form of document, and then a single list holding all of these documents inside this. So I also have a Hugging Face embedding model for embedding here, and then what I've done is I've created a vector store from using the face library, and then from documents passing in the document, and then the embedding function. What I need to do here is build a retriever here. So for that, what I'm going to do is I'm going to call a retriever object. So create a retriever object and then call vector store dot as underscore retriever. And inside this, I'm going to do search type equals to MMR, which means maximal marginal relevance. And then in terms of search keyword arguments, I'm going to do maybe I will fetch the top 3 result, or I want to fetch the top 3 result. And then inside this, I'm going to pass in lambda underscore mult and then a certain value inside this. So the value inside this particular parameter here goes from 0.0 to 1.0. The meaning of the value or the meaning of the term lambda mult equals to 0.0 means full diversity. It actually ignores relevance completely, and it is also rarely useful. And the value 1.0 means full relevance. It means it ignores diversity, and then it is equivalent to standard similarity search here. So the value in between the balance or the values in between balances the two. The higher the value, the more the retriever prioritizes relevance over diversity, and lower the value, the more it prioritizes diversity among selected results. So for this particular value 0.25 here, it means 25% emphasis on the relevance and 75% emphasis on the diversity. So this encourages the query or the retriever to return results that are still relevant to the query but are more valid and less repetitive. Now I have invoked this retriever using this invoke function and then pass in the query here, and then I can simply print out the result. So now let me run this code and then run this file here 3.mmr.py. It might take some time, but we'll wait for it and then see the result. Okay, so the query was what is LangChain? So what it has done is it has provided this particular answer as my first or prioritized result. But even though the word LangChain is particularly provided in this particular query too, to maintain the variability, it has not returned me this particular uh, document in terms of its response. Instead, it has gone to embedding, and then after that it has gone to MMR. So this kind of shows the diversity in our result. If we had simply used a similarity search, it would have probably returned these two results with priority, because basically the query as well as the document contains this keyword LangChain here. So this is what maximal marginal relevance do. It introduces diversity in terms of the retrieval process. And that wraps our deep dive into retrievers and the critical role they play in connecting your stored knowledge with LLMs. We explored how information can be fetched from both external and internal sources, how vector-based retrieval works, and how advanced strategies like maximal marginal relevance help us get results that are both relevant and diverse. These components form the backbone of any robust RAG system. And now that we've covered document loading, embedding, vector store, and retriever, we have all the pieces we need. All the pieces to build a complete retrieval augmented generation system. So in the next video, we'll bring everything together and build a RAG system, demonstrating how these components interact to answer real user queries intelligently. We started by understanding how language models work, how to design prompts, how to structure their outputs. Then we learned how to load real-world data, split it into meaningful chunks, convert it into embeddings, and store those embeddings efficiently in vector databases. Finally, we explored retrievers, the intelligence layer that decides what information the models should actually see. Individually, each of these concepts is useful, but together they form something much more powerful. This is where retrieval augmented generation, or RAG, comes to life. RAG solves one of the biggest limitations of language model. They don't inherently know your data. By combining retrieval with generation, we allow the model to ground its answers in real, up-to-date, and domain-specific knowledge, whether that data comes from documents, websites, or internal databases. In this video, we're not introducing any new theory. Instead, we're going to connect all the dots. You'll see how document loaders, text splitters, embeddings, vector stores, and retrievers work together in a single pipeline. Step by step, we'll build a complete RAG system that takes a user question, retrieves the most relevant context, and generates accurate, grounded responses. If you've been following this series so far, this is where everything finally clicks. So let's build a real RAG application. Okay, so in this video, we're going to implement our RAG system now. So we'll start with import. So from .env, import load.env, and then I'm going to load the credential. Well, my credential contains the API key for grok model as well as the Hugging Face embedding model. So now, first of all, the first task that we're going to do is we'll load a PDF document. So to do that, I'm going to import LangChain underscore community dot document loaders import by PDF loader. And I have a PDF here for this audit report. I'm going to load the same document and then build a RAG system around it. So what I'm going to do is I'm going to create a loader object using PyPDF loader class, and then my document name is audit report.pdf. So let me use this loader and then call a load function. Once this PDF document is loaded, what we're going to do is we're going to split the document into chunks. So for task number 2, we're going to split documents into chunks. And to do that, we're going to use from LangChain underscore text splitters import recursive character text splitter. Now I'm going to define this text splitter object and then call this recursive character text splitter class, and then I'm going to define a chunk size. Let's keep the chunk size to about 500, and then a chunk overlap to about 100. Then after this, I'm going to create docs using this splitter object, and then I'm going to split documents inside this. Yes, so this is documents. Yes, okay, documents. Now that this is done too, what we're going to do is in step 3, now we're going to call our embedding model. So create embeddings. Now to create embeddings, we're going to use from LangChain underscore Hugging Face import Hugging Face embeddings, and then my embedding model will be the same that I've been using in my previous video. So embeddings equals to Hugging Face embeddings, and then my model name is sentence transformers all mini LM L6 v2. Now after this, I'm going to store these embeddings in a vector database. So store embeddings in vector database, and for that we're going to use Chroma for now. So in Chroma, what I'm going to do is I'm first going to import Chroma here. So from LangChain underscore Chroma, import Chroma, and then I'm going to create a vector store here. So vector store equals to Chroma dot from underscore documents. Now I'll provide my documents here. This will be the docs object that I've created using this splitter object here, and after this I'm going to call the embedding. My embedding will be the embedding model that I've defined here, and then finally a collection name. So the collection name will be RAG collection. Okay, we have done up to the vector store part. Once we have stored our embeddings in our vector store, we are going to define a retriever object. So defining a retriever. So this will be retriever equals to vector store dot as underscore retriever. Here I'm going to do search type equals to MMR. MMR basically means maximal marginal relevance. So MMR basically means maximal marginal relevance. Here we've already talked about it in the previous video. If you haven't seen that video, you can go and check it out to know more about this MMR parameter here. So in search queries, I'm going to maybe generate the top 2 results only, and then for lambda mult mult, I'm going to pass in 0.5 here. So in order to understand this too, please go to our previous video in this LangChain series. You can easily and clearly understand what this term MMR and then the lambda mult term means here. Okay, once this is done, now in step 6, I'm going to initialize my LLM here. So for the LLM, I'm going to use LangChain grok, and then from here I'm going to import chat grok. Now define my model. I'm going to define LLM chat grok. The model name that I'll place here is llama model, llama 3.3 with 70 billion parameter. Okay, so this is going to be my model for this particular project here. Then what I'm going to do is in step 7, I'm going to create my prompt template. So create prompt template, and to do that I'm going to import LangChain core dot prompts import prompt template. We can also use chat prompt template here. If you don't know the variation between the prompt template and the chat prompt template, you need to visit our previous video on prompts and then basically understand it from there. So prompt template, let me define a template here. So the template is provide a string. So the template is like this: you are an AI assistant, use the following context to answer the question. If answer the question if the context or answer is not present, sorry, so if the answer is not present in the context, say you don't know, and then I'm going to pass in the context here. So my context will come from context variable, and then my question will come from the question variable again. And then the model basically needs to provide me an answer. What I'm going to do here is I'm going to do input underscore variables. Then I'll pass in the two variables. First is the context, and then second is the question. Okay. So now we are going to build or indicate an output parser here. So let me write output parser definition. And then in this case, we're going to use a simple output parser or str output parsers. So from LangChain core dot output parsers, we need to import str output parser. So we're also going to create an object for this str output parser. This is done too. Now finally, in step 9, we are going to build a chain. So build a RAG chain. So for this RAG chain, what I'm going to do is I'm going to first define a function format underscore docs, then pass in my docs here, and basically I'm going to join my document into a single string here. So dot join doc dot page underscore content for doc in docs. Okay, so this is my function. Now I'll define my RAG chain here. So my RAG chain will indicate that at first I'll pass in my context. So my context will come from a retriever, and then if we have multiple, since we have called for top 2 results, it should also be joined into a single string. So I'm going to call the format docs function here. Then I need to pass in the question, and then the question will be just a single query, so as it is here. So yeah, lambda x colon x, just a simple query as it is. Question mbda lambda. Yeah, so now after this I'm going to pass it to my prompt, and after this I'm going to pass it to LLM, and then finally I'm going to pass it to a parser object. So this is my entire RAG chain here. And now what we need to do is now we need to interact with the bots. So maybe ask a question to the system. So query, I'll ask what is this document mainly about, and then I'll log the response in the response variable. And to invoke this question, I'm going to call on RAGchain dot invoke, and then I'll pass in the query here. So once the query is passed, where does the query go to? So the query basically goes to the question part here, and then from this particular question, retriever is called. So the top 2 results are called. They are joined into a single string using format docs, and then they are passed to the prompt here. So basically we now have question as well as context, and then from a prompt, or like after the prompt is prepared, we'll pass it to the LLM chat grok model, and then finally pass it to the parser. Now what I can do is I can simply print my answer here. So print response, it should be in a string because we have used a str output parser at the end. So now let me activate my virtual environment since my code is ready to be run. So scripts and then activate. So my virtual environment is activated. Now let me run the code. So 11.rag and then 1.basic-rag.py. It might take some time because it is a huge document. Everything needs to be converted into embeddings. It needs to be stored in our vector database, and then we we're basically asking a question to our system based on the document that we've uploaded, or based on the document that we provided. So we seem to have our answer here. So the answer says that this document appears to be an audit report. Obviously it is. It is an audit report here. And then what else? Mainly about the examination of internal controls, accounting records and financial statement, and the findings and observation resulting from that examination. Okay, what else? Let me ask one more question here. What is this? These are 70. So let me change my question here. For 2006 2007, INCAP increased the number of donors from 12 to 18. Okay, so how many donors were included by, okay, what is it? It's INCAP. Yeah, INCAP for 2006 2007, or will do 2006 7 year. So yeah, let me run this code again. It should find me the answer from this particular document and then basically give me that the donors, maybe it will provide me that the donors are 18, or maybe it will say that INCAP increased the number of donors from 12 to 18 or something like that. Well, we'll find it out. Okay, so in the answer, the model actually got confused, but it did not hallucinate and then provide any random answer. Instead, it said it didn't know. The provided context does not mention the number of donors included by INCAP for 2006 or 7. It only mentions that SICA accounted for 70% of all voluntary contributions in the biennium and recommends that INCAP. Okay, so we'll ask something else. If there is a table here, we can ask it from the table. We'll ask the INCAP's total income in 2004-2005. So what is INCAP's total income in 2004, sorry, 2004-2005? We will not say is, we'll say was. Again, run this code. So based on the document here, it basically went from $807,400 in 2004-2005, but we'll find out if the model can actually find that answer or not. The context does not provide the total income of INCAP for 2004-2005, only specific components of income such as miscellaneous or other. Well, it did find out that and quota income, 807,400, it did find this particular income from our document, but the model hesitated from hallucinating and then providing any random answer here. Well, we'll ask something else here. So the third question is going to be something like this. Can you find me the, or like we'll ask straightly, so who is the god of machine learning? The model should not hallucinate and then provide me an answer like something I don't know. Okay, so it says I don't know. The provided context does not mention anything about the god of machine learning. So if it can find any kind of answer here, it does try to provide me that answer. But if it doesn't know, the model or the rack system does not hallucinate. It simply says I don't know, just because of the prompt that I provided here. Okay, so this is the end to this basic rack system. Whatever we've done here, we first loaded a PDF document using a PyPDF loader. We've splitted the document into chunks using recursive character text splitter. Each chunk size is 500, and then the chunk overlap is 100. Then we've created embeddings using this Hugging Face embedding model. We've stored these embeddings into a Chroma vector store, and then we've used that same vector store as a retriever here. The source type is maximum marginal relevance. The top two searches are ordered here, and then we have used this ChatGrok model, or inside this we've used this llama model as an LLM. We provided a prompt here, and then a string output parser. In terms of the chain, we have provided the context using this retriever, as well as this format docs function, where the contexts are merged into a single string, and then we passed our question here. So at the end, we've invoked this chain and then passed our question to it and then generated the response. And with that, we built our first complete retrieval augmented generation system. But this is not the end, it's just the beginning. What you've seen in this video is the foundation of intelligent systems that can reason over documents, ground their answers in real data, and evolve far beyond simple question answering. From here, we can explore more advanced RAG variations, improve retrieval strategies, and build systems that truly understand context. So in the upcoming videos, we'll take this further by adding contextual conversation, memory, and more intelligent retrieval flows, transforming this basic RAG setup into a system that feels natural, adaptive, and production ready. So if you followed this series up to this point, you now have all the core building blocks. What comes next is about refinement, scale, and intelligence. Imagine you're building a RAG system for a client or for your own knowledge application. In the earlier videos, we created a basic RAG pipeline where you query a PDF, split it into chunks, embed the chunks, store them in a vector store, retrieve the most relevant chunks, and then feed them to a language model to get an answer. It worked well, where you got answers from your documents and the system was fast and functional. But there's a major limitation. When the model gives you an answer, you have no way of knowing which part of your document it actually used. The model could be hallucinating, or it might have picked a chunk you did not intend. This is fine for a quick experiment, but in real-world application, especially when building AI tools for knowledge, work, education, or enterprise, this lack of transparency is a big problem. Users and developers need explainable AI, answers that come with evidence. Ideally, the system should tell you which page in your PDF the information came from, which exact chunk of text was used to answer the question, and even when the multiple sources were used, if the answer is composed from more than one part. This is what we're tackling in today's episode. We're moving from basic RAG to a source-aware RAG, or what you can think of as an explainable RAG. Here, every answer your model generates will be accompanied by the context it actually used, along with metadata like page numbers or chunk references. This not only improves trustworthiness, but also helps developers and users verify, audit, and understand the answers. So in this video, We'll build a pipeline that loads a PDF and splits it into manageable chunks, embeds the chunk and stores them in the query vector, retrieves the most relevant chunks for a query, feed only the retrieved chunk to the LLM, and returns both the answer and the sources used. And by the end of this, you'll have a RAG system that is not only powerful, but also transparent and explainable, taking your knowledge application to a more professional and reliable level. First, we're going to do from .env import load.env. So this will be used to load our credential, as we already know. So in step 1, we're going to load a PDF. So to do that, from LangChain underscore community dot document loaders, I am going to import PyPDF loader, define the loader object, define my file name, then I'm going to do documents equals to loader.load. In number 2, I'm going to split my document into chunks, and to do that I'm going to use LangChain text splitters, and then inside it I'm going to import a recursive LangChain underscore text splitters import a recursive character text splitter. Let me define my splitter function here. So text splitter equals to recursive character text splitter. The chunk size is, okay, let's call it 500, and then the chunk overlap, let's call it 100. Now in step 3, I'm going to create embeddings. So I'm going to import Hugging Face embeddings from LangChain underscore Hugging Face. And then I'm going to define an embedding model. The model name is going to be sentence transformers all mini LM L6 V2. In step number 4, I'm going to store embeddings in Chroma. And in vector store object, I'm going to define Chroma dot from underscore documents. I'm going to pass in my documents from chunks. Documents are chunks. So what have I defined it here? Okay, so I might have missed this. So after my splitter, I need to split my text into chunks here. So this is going to be text splitter dot split documents, and then I'm going to do documents here. Now here I'm going to pass in chunks as documents. As my embedding, I'm going to pass embeddings, and in place of collection name, I'm going to pass source aware rag. I'm going to run a similarity search. So here I'm going to pass in my query. We'll ask what is the report about. In place of retrieved docs, I'm going to do vector store dot similarity search, pass in my query, and then I'm going to extract top 3 results here. In the next part, I'm going to build context plus source. So in terms of my result, let me put down context text as a variable and then source as a list here. So for I doc in enumerate, I've extracted top 3 results, right? So I'll run a loop on it. Retrieve docs. What I can do is page equals to doc dot metadata dot get, and then I can extract page here. If I don't find any page, let me give NA. And similarly, in terms of source, I can do doc dot metadata dot get, and in place of source I can provide source. If nothing is present, then a default value can be PDF. Now now for context text, I'm going to just add whatever thing I have in this page content here. So content plus equals to f, so chunk I plus 1 plus n doc dot page underscore content. And for source, I can do source dot append. So this can be sources. Here I'll put sources. So in the append function, what I can append is I can append the chunk number. So the chunk can be I plus 1, and then for page, it can be the page that I've extracted above here. Then for source, I can do source just from this variable here, and then for content, I can do doc dot page underscore content. Now I can define my prompt. So 7 is going to be prompt LM with context. So for this, I'm going to import from LangChain Grok. I'm going to import chat Grok from LangChain core dot prompts. I am going to import prompt template, and from LangChain core dot output parsers, I'm going to import str output parser. Let me define my LLM model, which will come from chat Grok. Chat Grok, and then the model that I'll be using will be Llama 3.3 model. Okay, now after this, what I can do is I can define a prompt using my prompt template. So my prompt will come from template class. Then inside this, I'll first define my template. So answer the question only using the context below. Also provide the actual chunk during a retrieval along with the page number of the document where I can find that chunk. Along with this, what I would like to define is I'd like to define my context. So my context will be context. My question will be question, and then okay, what else? I think that will be sufficient. And then I'm going to define my input variables. So my input variables will be context and then question. Now what I can do is I can define my parser. So my parser is going to come from str output parser, and I'll define my chain. My chain will be prompt LLM, and then parser. And finally I can invoke, so basically do chain dot invoke, pass in the context text. So the context underscore text will come from context text, and then my question QUESTR, the question will come from the query. So finally I can print my answer here. So let me just print answer, and then for sources what I can do is for src in sources, so I can first print out the chunk. So chunk is going to come from src chunk, and then its page number is going to come from src and then page. Then I can also print its content. So this will come from src content, and then let me print a horizontal line here. So now this is all my code. At first what we've done is we have retrieved our chunk from this vector store using this query here. The top three results, the actual content, the page number, as well as the source are extracted. The page number and source are extracted from the metadata, while the actual chunk is extracted from the page content, and then they appended into this sources list. Then I have my model, and then using my model and then using a prompt template, I'm passing it to an LLM and then a str output parser, and then getting my answer here. So there was a slight mistake in my code here. I had written context underscore test, but it should be context here. So once I run this code, I can see that my question was actually what is the report about. Where is my question? So yeah, it says that the report is about the audit of financial statement of institution of nutrition of Central America and Panama. In cap, it extracts the following chunk for me. So chunk 1, and then chunk 2 and chunk 3. So whenever I try to print my sources, it not only provides me the actual answer, but the chunk part as well as the page number where this particular chunk is present. So this now becomes much more explainable for this particular answer here in terms of its source, meaning in understanding where the source is actually coming from. So what we built today is a big step forward from a basic RAG system. We didn't just ask the model for answers, we asked it to show its work. By attaching page numbers and the exact document chunks to use to generate each response, we made our RAG pipeline transparent, verifiable, and trustworthy. So this is the foundation of what real-world production-ready RAG systems look like. Systems where users can trace answers back to their original sources instead of blindly trusting a black box. But this is still just one piece of the puzzle. Right now, our interaction is stateless. Every question is treated in isolation, and our interface lives in the terminal. That's fine for learning and experimentation, but not for real users. In the next part of this series, we're going to take this even further. We'll move from the terminal to a Streamlit-based chat interface, build a proper chat window, and introduce conversation memory so the system can understand follow-up questions, context, and intent across multiple turns. And that is where RAG starts to feel like a script and more feel less like a script and more like an intelligent assistant. So this isn't the end, it's the beginning of building interactive, explainable, and conversational AI systems. In the last video, we took our RAG system one step further. We didn't just retrieve answers anymore, we made the system explainable. We saw where the answer came from, which page of the PDF it was extracted from, and which exact chunk was used as context. But there was still one big limitation. Every time we asked a question, the system treated it as a brand new request. No memory, no understanding of what we asked before, and no ability to handle follow-up questions like explain that again or what about the next part. And that's a serious problem because real users don't talk to AI in isolated prompts. They talk in conversations. So in this video, we're going to fix that. We're building a conversational RAG system where retrieval still happens from your documents, but now the model also understands the entire conversation history. And the most important part, we're not going to rely on any deprecated chains, hidden abstractions, or black box helpers. Instead, we'll implement everything manually and explicitly. We'll manage chat history using messages. We'll inject conversation history directly into the prompts. And we'll combine that with a retrieval in a clean, future-proof way. And by the end of this video, you'll have a rack system that can handle follow-up questions naturally, maintain conversational context, and still stay grounded in your documents. So without any delay, let's start building. So at the beginning, we're going to write all of our imports. The first import will be our PyPDF loader. Then we'll import chat group. Then a list. A base message, a human message, and AI message, as well as a system message. Then we'll import chat prompt template and then a messages placeholder. After that, to break our document into chunks, we'll again use a recursive character text splitter. For our vector store, we're going to use Chroma. For embedding, we're going to use Hugging Face embeddings. And to load our credential, we are going to do load.env. Okay, so now, first of all, we'll load our document using the PyPDF loader class. The file name is audit report.pdf. Now we'll do documents equals to loader.load. Let me also define my model. So it is again going to be a llama model. Now I'm going to define my splitter object. Let me define the chunk size as 1000 and then the chunk overlap to be around 100. Then I'm going to break my document into chunks using splitter object here, splitter dot split underscore documents, and then I'm going to pass in my documents from up here. Now I'm going to define my embedding model. My embedding model will come from Hugging Face embeddings, and then the model that I'm going to use is sentence transformers all mini LM L6 V2. This is the same model that we have been using in our previous videos too. Now I'm going to create a vector store using Chroma, where I will pass my documents as chunks, and then my embedding as embedding model that I've just defined above. Then I'll now define a retriever object. So I'll use the vector store as a retriever, and here the search quirks is going to be let me fetch like top four result from the vector store. Now move to defining the prompt using chat prompt template, and chat prompt template I'm going to do from messages here, and inside this I'm first going to type a system message. So the system message is going to be with a content the content is going to be something like this: you are a helpful AI assistant, answer strictly from the provided context. If the answer is not present in the context, just say you don't know. Now, after this, I'm going to define a message placeholder. Inside this message placeholder, we define a variable name. The variable name, I'll keep it at chat history. And then inside this, let me define a human context double slash n, and then question will be placed as input. So this is going to be my prompt for this video. Now for the conversational RAG part, I'm going to define it into a function. So conversational RAG, the parameters here will be user input, which will be in the form of string, and then a chat history. This will be in the form of list, and then a base message. Now inside this function, first of all, we'll retrieve documents using our retriever. So retriever dot invoke user input. Then in the context, I'm going to join my context. Basically, what can I do here? So let me do something like this. I'll define a page, then page will come from d.metadata.get page, or by default it will provide an A if not found. And inside this, I'll again do do a line break and then do d.page underscore content for d in docs. After this, inside this function, I'm going to build a prompt. So I'm going to do that using prompt.invoke. And inside this, let me keep a curly bracket. Input will come from user underscore input. What else? This, yeah, user underscore input. The context, I think it's not input. Okay, so the context is going to be from context that I've just prepared earlier. And after this, the chat history is going to come from chat history variable. Then I'm going to invoke the LLM with these messages that I've just prepared, or with the prompt that I've just prepared, and then I'm going to return response, docs. So here, before calling this function, I'm going to build a list of base messages called chat history here, base message, and then this is going to be an empty list for now. So let's say conversational rag. I'll keep this inside a loop for continued conversation, and then ask for the user input. So for the user input, I'll just say you, and then to break out from the loop, I'll keep one condition. So if user input dot lower equals to exit, I'll just do break, or else what we can do is we can append our user input inside the chat history. So chat history dot append, I'm going to keep it as a human message, and the content of the human message is going to be the user input. Now after this, I'm going to call the conversational rag function. I'm going to pass in the user input as well as the chat history from there. So chat history, and since it returns two different stuffs, responses and docs, I'm going to do responses. I actually don't need the docs if I don't want to show the sources, but anyway, I'll keep it for now. So responses comma sources equals to conversational rag function called. Now whatever response we get from the model, I'm going to add it or append it inside my chat history again, dot append. So this will be appended as an AI message, and then its content is going to be the response dot content part, and then I'm going to print whatever the AI prints or AI provides, which is comma response dot content, responses dot content, and then responses dot content. Okay, so if you also want to see the source, you can just print out the source here. Basically the source will also be a list, so be careful. You might need to loop over the sources if you want to print out, but I'm not doing that right now. Now I can simply run my code. So Python 11 rag 3 memory rag.py. It seems that I made a mistake here, so let me go to the model definition part, or the LLM definition part. So inside this, I should have placed it inside the model parameter. Let me clear the log and then run it again. So the system is running. It has printed me this particular part, conversational rag here, and then I'm inside this loop here. So if I just hit break, uh, sorry, right? If I just hit exit, then it will exit from the system. Let me run this again and then start and interacting with that particular system, and then check if the memory we have implemented in this does hold up in the conversation too or not. Okay, so now that the system is running again, what I can do is I can say, hi, my name is John, and I would like to ask you what this document is about. So the AI says that the document appears to be an audit report of the institution or Institute of Nutrition of Central America and Panama, INCAP. Okay, that is all. It discusses audit findings, internal controls, and governance arrangement, as well as a recommendation for improvement. Okay, tell me about that last part, recommendations one. So the last part you mentioned is follow up to 2004-5 recommendation, which is paragraph 56-62. However, the text for those paragraphs is not provided in the context of file. Okay, so we'll discuss or we'll ask what else. Tell me about the audit findings. So yeah, the audit findings are quite long, but what I want to check here is, does it have a form of memory or not? Because in the initial query, I had passed my name here too. So here what I can ask is, from our conversation, can you remember my name and tell me what my first question was about. So it does tell me my name. It does know my name because it says your name is John and your first question was about what the document is about. Okay, uh, and after that, what did I ask you? After the first question about the document, you asked me to tell you about the recommendation one part, but then you asked me to tell you about the uh, audit findings, and then you asked me to remember your name and tell you what the question was about, and after that you asked me, after that, what did I ask you? So it does have its memory preserved, but where is that memory preserved here? That particular memory is preserved here in the chat history. So until and unless this particular chat history variable is alive and then is being processed inside this particular loop, um, the system does have its memory. But again, this particular memory is only confined within one particular session. If I hit exit, so if I hit exit and then the system breaks up, and then if I run this, if I run the code again and then I ask my name, since now the chat history is empty, whenever this particular code is run again, now it does not remember my name at all. But there are workaround to save those conversations in the databases too. So we'll do that in the upcoming videos, but for now we'll verify uh, whether it remembers my name between sessions here. So do you remember my name? So it says I don't know. So basically what we did here was implement a form of memory uh, for for a continued conversation for the user into the system instead of just one prompt question answers. So with this, we've taken another solid step forward in building truly usable RAG systems. We now have a conversational setup where the model doesn't just answer isolated questions, but understands the flow of the conversation and responds in context, while still grounding every answer in retrieved documents. So this is the point where RAG starts to feel practical, not just experimental. But we're still not done here. Right now, our conversation lives only in the memory while the program is running. The moment we restart the app, everything is gone. So in the next video, we're going to fix that. We'll build a ChatGPT style session management where conversations are stored in a database, automatically reloaded when a user comes back, and continued exactly from where they left off. And that's when we move from demos to real production ready AI systems. We are going to build a chat style RAG application where conversations persist across multiple turns, just like in ChatGPT. Each user interaction becomes part of a growing conversation, and that conversation directly influences how the model understands and answers future questions. Even more importantly, we're not just keeping this memory in RAM. We're introducing database-backed session management, which means you can start a brand new chat at any time, or you can switch between older conversations, and your chat history or entire chat history is restored exactly where you left off, just like in ChatGPT or Gemini. To make this practical and usable, we'll wrap everything inside a Streamlit interface, complete with a navigation sidebar for managing multiple chats. And under the hood, we'll combine document retrieval, conversational context, and persistent storage into a clean pipeline. And by the end of this video, you won't just have a RAG model, but you'll have a production style conversational RAG system that looks and behaves like a real world AI applications that we are using daily. So let's start building. The quite can be quite long, so follow along and then pause and repeat it if you have any errors. So we'll start with importing Streamlit. And for that, what I want you to do is go to requirements and then pip install Streamlit inside this, or basically add it in requirements and then install it from there. So I want you to install Streamlit, as it is going to be our front end for our chatbot. So first of all, I'm importing Streamlit as st. Then let me import SQLite 3 for database. I'm going to import uuid. This will be used for something that I'll show you later on. So from typing, let's import a list. This will be for chat history. And from .env, let's import load.env. This will be for loading our credential for our chat grok model as well as our embedding model from Hugging Face. Now onto the LangChain components. So from LangChain underscore community dot document loaders, I want to import the PyPDF loader at first. Then from LangChain text splitters, I want to import recursive character text splitter. Similarly, from LangChain community dot vector stores, I want to import Chroma. And from LangChain underscore Hugging Face, I want to import Hugging Face embeddings. And similarly, from LangChain underscore group, I want to import chat grok. Some more imports coming on the way. So from LangChain underscore core dot messages, I am going to make multiple imports here. So let me keep it in this way. So the first will be our base message. The second will be a human message. The third will be our AI message. And then the fourth will be our system message. And along with this, from LangChain underscore core dot prompts, I am going to import chat prompt template and then a messages placeholder. Okay, so almost all the imports are done. First of all, we are going to load our credentials. So for that, I'm going to do load.env. Now we'll work on the database part first. So for the connection, I'm going to do sqlite3.connect connect, then provide our database name. So let me call it chat underscore memory1.db, and I'll do check same thread equals to false. Then once the database is created, I need to create my table. So cursor dot I first need to create a cursor object here. So cursor equals to connection dot cursor function. Now using this cursor object, I can do cursor dot execute, and then I can actually run my query here. Okay, so my query is going to be create table if not exists. I'll provide chat history, or the table name will be chat history. The first component will be session ID. This will be in text. The second component will be role. This will also be a text, and then the third component will be content, and this will also be a text. So this particular query will create my table, and then based on this, I'm going to do connection dot commit. So now my database will also be created, as well as my table will also be created inside this particular database here. Now after this, I'm going to create some helper functions to save our data as well as load our data. So the first function is going to be save message. I'll provide a session ID in the form of string. I'll provide role in the form of string as well as content in the form of string. Then inside this particular function, I'll have cursor dot execute. Basically, I'll write an insertion query. So insert uh, into chat underscore history, and then my values will be question mark, comma, question mark, comma, question mark, and then all of these values will actually come from session ID, role, and then content. Then I will do connection dot commit again. This is for save message. Now I'm going to do the same for load message, so or load chat history, and I'll provide a session ID here in the form of string, and then this is going to return me a list of base message. Inside this, I'm going to again execute a query. So cursor dot execute. Let me write my query. So select role, comma, content from chat underscore history, where session underscore ID equals to question mark, and this particular session ID is going to come from session ID here. Now since we are fetching multiple rows here, so I'll write rows equals to cursor dot fetch all. Fetch all is a function. Now I'll create a chat history, a placeholder where I can save my chat history. So list of base message, this is now going to be an empty list for now. So I'm going to iterate it over rows. So for role, comma, content in rows, I'll check if role equals to human. If role equals to human, sorry, this should be RLE role. Okay, so if role equals to human, we'll do history dot append, and then I'll provide a human message with the content with content as content. Similarly, LF role equals to AI. I'm going to append the same message, history dot append AI message, and this is going to be stored as content equals to content again. And then I'm simply going to return history once all the rows are read. After this, one more function to get all the stored sessions. So the function name is going to be get all sessions. Again, cursor dot execute. So the query is going to be select distinct session underscore ID from chat underscore history, and then I will order by row ID, and then it is going to be in descending order. So I will return row 0 for row in cursor dot fetch all. Okay, so this completes the database helper functions part. Next, we are going to work on the Streamlit configurations part here. Configurations. So first of all, I'm going to do stringlit.setPageConfig, and then inside this, I'm going to do page title. Page title can be a conversational rag, and then the layout used here will be a wide layout. After this, I'm going to provide a title. So st.title is conversational rag with memory. Now let me also define the sidebar part here. So for sidebar, I'm going to do st.sidebar.title, and then the sidebar title will be chats. Now after this, for session management, I'm going to do if session underscore ID is not present in st.session underscore state. I'm going to do st.session state dot session ID equals to string form of uuid dot uuid4. Similarly, st.session state dot chat underscore history is going to be an empty list. I'll also have a button that when pressed adds a new chat. So for that, st dot sidebar dot button, so this will be for new chat. If this is pressed, then again I'm going to do the same thing as above. I'll create a new session ID for this. Session underscore ID is going to be created again using that uuid class dot uuid4, and after this st dot session state dot chat underscore history equals to empty list. Now to load all the previous conversations, I'm going to have a markdown here. So st.sidebar.markdown, let's call it previous conversations. And here what I can do is I can call this get all session functions, and then basically get a list here in which I can iterate. So for SID in get all sessions, so if st dot sidebar dot button, and then the text of this button, I'm only going to keep this 7 characters from our session ID. Okay, 7 characters from the session ID. What I'm going to do is if this is present, or like if I'm if I am reading from each session, then st.session_state.session_id equals to sid, and st.session_state.chat_history equals to load chat history, and then I'll provide the session ID here. So if I go to load chat history, then basically based on a certain session ID, I can generate a role and content from here. So everything seems to be done, and then once this is done, I'm going to set session_id equals to st.session_state.session_id. So again, the particular session ID can come from anywhere. It can come from this particular part, it can come from this particular part, or it can come from this particular part here. It can come from any part. We'll go to our LangChain component part. So first I'm going to load an index our PDF here for the RAG model. And for this, what I'm going to do is I'm going to cache this particular resource here. So the resource is, the first resource is the load underscore vector store. So once the vector store is loaded, it needs to be cached throughout the session here. So I'll call PyPDF loader for this one, and then I'll provide in the PDF file that we have been using, the audit report.pdf. Now I can do document equal to loader loader.load. So this is only, or this will only be loaded once whenever we've started our application. So I'm also going to define a splitter. So the splitter will come from recursive character text splitter. I'll provide a chunk underscore size. The chunk size will be 1000, and then I'll also provide a chunk underscore overlap, and then this will be around 150. Now I'm going to break my documents into chunks. So I'm going to use the splitter dot split underscore documents, then provide the document here. Once this is done, define my embedding model. So my embedding model is going to come from Hugging Face embeddings. We will use the same model that we have been using. So model name equals to sentence transformers all LM L6 V2. So this is the model that we have been using from very earlier. Now I'm going to do vector store equals to Chroma dot from underscore documents. So here my documents is going to be my chunks, and then my embedding is going to be the embedding object that I've created earlier using Hugging Face embedding. And finally, I'm going to return a vector store. So all of this part will run only once, and then that particular same stuff will be used throughout that particular session in the application here. So now what we're going to do is we're going to define a vector store, and then that can be basically done calling this load vector store function from here. After this, I'm going to call our retriever class or retriever object, and then this will be done using vector store dot as underscore retriever. Vector store dot as retriever, and then from the search parameters, I'm going to provide or I'm going to ask the model to generate the top 4 results here. So k equals to 4. Once this is also done, I can define my LLM model here. So LLM model is going to come from ChatGrok. Again, I'm going to be using the same model, the same llama model that we had been using since quite some time in this tutorial here, 70 million. Now let me define my prompt. So my prompt is going to come from chat prompt template, and then from underscore messages, And inside this, I'm going to keep a list. And then inside the list, first of all, I'll have a system message. The system message will basically have the following content. So content equals to, let's say, you are a helpful AI assistant. Answer strictly from the provided context. If the answer is not present, just say you don't know. Okay, so this will be my first message inside my prompt. Then after the system message, I'll have a message placeholder for my chat history. So here the variable name will be chat underscore history. And then I'll also have a human message inside this. So a round bracket, and then let me provide a role first human, and then basically provide in the context. So the context will come from the context placeholder, and then a question will come from the question placeholder, or we'll call it input here for now. Input. My prompt is also created, or my prompt template is also defined. Now what I'm going to do is I'm going to invoke this conversational RAG function. So def conversational RAG, I'll pass in the user input, which will be in the form of string. Then I'll pass in the chat history, which will be a list, HISTORY, which will be a list, and then list of base message. So base message. Then I'm going to do docs equals to retriever dot invoke, and then user input. What this is going to do is, based on the query that I provide, it is going to retrieve chunks, or the top 4 chunks from this particular retriever object that I have here. Now I'm going to join in the context, but I don't think I need to do this. Basically I have the context here, right? So what I can do directly, or no, I need to join in the context because I need to provide it into the prompt. So let's do something. So I'll insert 2 blank lines dot join function, and then inside this join function I'm going to add page. So d dot metadata, I'm going to get the page number from where the context is being extracted. If we have a page, then I'll provide a page. If we don't have a page, then I'll just give a default value here. Then again add a line break, and then do d dot page underscore content. Now for my messages part, I'm going to do prompt dot invoke. Then I'll pass in input as user input. I'll pass in the context as context, and then I'll pass in the chat underscore history as chat underscore history. So I seem to have missed something. I need to do for D in docs here. Okay, so this particular part is also complete. Now I need to invoke my model. So for that I'm going to do response equals to LLM dot invoke, and then pass in my messages that I've prepared from my prompt, and then finally I'm going to return response as well as the docs part. So this is done. Now whenever we switch session or like we load chat history, we need to define the logic for that too. So for that, what I'm going to do is if not st.session st.session state, if not st.session state dot chat history. So if this is not present, then I'm going to do st.session state dot chat history, chat underscore history equals to load chat history, and then provide a session ID here, session ID. Now for the chat window part, let me write chat window part. So for the chat window part, I'm going to do for message in st dot session state dot chat history. So if I have multi-turn conversation in my chat history, then I'm going to check what the role is. So if is instance message is a human message, then I can write st dot chat underscore message and then name it user, and then for user I'm going to write a message dot content. So I'll also do elif is instance message dot AI message. If it is an AI message, then st dot chat message, then I'll call it assistant or just call it AI, and then dot write message dot content. Now if a user provides an input, I'm going to log it in user input. So st dot chat underscore input, and then I'll give a placeholder ask or question from a PDF. So if user has provided an input and then submitted the input, so I'll first write the user message in the chat message as a chat message in the user role dot write user underscore input. Then I'm going to save this message in my database. So I will generate a session ID or like whatever session ID I have. In that particular session ID, I'm going to log a human message for this particular user input, or I'm going to save this user input as a human message. Then st dot session state dot chat underscore history, I'm going to append this new message in my chat history. So chat history dot append human message, and then the content is going to be user underscore input. Once this is done, we'll get our response as well as sources. We might not use sources here, but anyway, so we'll call the conversational RAG function and then pass in the user input first, and then our chat history st.session_state.chat underscore history. Okay, now so we have some response from the model. So first of all, I'm going to save that as an assistant message or AI message. So we'll call it AI dot write, and then I'll write the response dot content part. And after this, I'm going to save the same message in my database. Save message. I'll pass in the session ID. I'll pass in AI, and then basically save the response dot content underscore AI role. Now I'm going to do st dot session underscore state dot chat history dot append, and then I'm going to append an AI message in my chat history. whose content is going to be response.content. Okay, so the code is almost complete. So whatever we've done here, we'll just go through this. First of all, we've used some import, loaded the credential. Then for the database part, we have tried to connect to this particular chat memory 1 DB. If that database is not present, it will be created. And then after that, if the table is not present inside this database, so this particular chat history table will be created. Uh, for saving message, I have defined a helper function here to save the session ID, role, and content. To load the chat history, I've again created a helper function which will return me back the chat history that has been saved into the database for a particular session ID. Then I also have another function to get all the sessions, and the database part is almost done up to this point. Then for the Streamlit configuration, I have set page config and then page title is conversational rag. I've also placed a title here, and then I have a sidebar with a title chats. Now, for an individual session or for a new session, I have created an empty chat history as well as a unique session ID. And I've also tried to load the previous conversations using this get all session functions here. So that is also done. And then the session ID is loaded from the get all sessions function, and then the chat history is loaded using load chat history function by passing the session ID inside it. Yeah. Okay, so this is also done. Now, no matter where the session ID comes from, a valid ID is maintained. Now for the LangChain part, I have used this function as a cache resource. Uh, use the loader object with the help of PyPDF loader class, and then basically loaded my document, split it into chunks, and then created a vector store using Chroma, and then these chunks as well as the embedding model, and then basically return the vector store. So a vector store is created, and then the vector store is used as a retriever here. So I have a retriever object too. Then comes my chat grok model, or basically the llama model. I've created a prompt from a chat prompt template. We basically pass in a chat history in the middle, as well as add new context as well as the user input in this particular place. So now for the conversation rag model, I have retrieved the documents based on the user input from the vector store, and then I have appended them all into one single string. Now my prompt is in the form of this particular form here, including input, context, and chat history. Then I've invoked that particular prompt and then returned the response as well as document. So whenever a chat is loaded, it is loaded using a session ID, uh, and for a particular session chat, I need to show all the conversations. So for that, I have looked around this chat history here, and then basically I have two roles, the user message as well as the AI message, and then showed them accordingly here. We provide this user input as well as the chat history to this conversation rag function, and it will return me the response and docs, and then I have basically printed the response as an AI message in my chat window as well as saved it in my database too. So this is all for the code. Now I hope I don't have any errors, so let me run this code. So I can do streamlit run and then basically provide the file name. It is inside this folder called rag here, and then the file name is for database memory rag.py. So let's start the project. Okay, the network URL is provided, and then the system is running in this particular window. So it will take some time for everything to be set up, and then once it runs, I'll show you what kind of system we've made. Okay, so this particular window is open. We have a sidebar with chats as heading, new chat, and then we also have previous conversations. But since we are doing it for the first time, so we don't have anything. The load vector store function is used as a cache resource. So for the very first run, or like whenever we run for the very first time, that particular function is called. Okay, so we do have some error. So let me check what the error is. So it is in line 160 and then line 47. Line 47. So let me check what happened in line 47. So session ID, okay. Line number, let me pull it a bit down. Line number 47. What did we do wrong here? So select a role as well as content from chat history where session ID equals to something, and then I passed a session ID here. Let me again see the error. So the load underscore chat underscore history, and then it is inside this function. What does it say? Session ID, session ID, session ID. Incorrect. Number of bindings applied. Let's see the error here. The error says incorrect number of bindings applied. The current uses 1 and there are 36 applied. Okay, so let's verify this error and then see what we've made wrong here. Two errors here. So the first error that I was doing is I should have inserted a comma inside this load chat history function. So it should be a comma along with the session ID as well as the comma at the end. And somewhere down here, where was that? Let's see. So probably where we have written this particular part. So somewhere down here, instead of writing right, I had written wrote. So make sure it's all right here, okay? And along with this, it's right here. So now we can actually run this code. So Python, uh, I've only I've already tried this. So not Python, it should be Streamlit run 11 rag mem database memory rag.py. So I've already tried this rag like I said, so let me close this and then we'll start from the very beginning. We already have some conversations in the database, and mainly it should load those two sessions that I've stored in the database. So here the load vector store will always run in the beginning as a cache resource. I have two different conversations as a previous conversation. So these two conversation sessions are actually loaded from the database, and then they are loaded from this particular function here from get all session functions. Where was that? And then I have iterated with that get all session functions here. So yeah, with this particular part, no, not this part, sorry. Where was that? So yeah, it is being displayed from this particular portion here. So now let's go to our previous session conversation. So it does load the conversation that I had, and then I can continue the conversation here. So in the first query, I had provided it my name. So let me just ask what is my name, and then it should tell me that my name is John here. And in the second conversation, where I had said, hello, help me with this PDF, and then it asked me for the issue to address, and then I said, my name is Abhishek, can you tell me what this document is about? It gave me the answer. And then now if I ask what is my name, so for this particular session, my name is Abhishek here, so it does reflect my name. So it does have its own history, a session specific history, as well as these two session conversations are stored in the database. So this is just like using ChatGPT, where we can start a new chat and then start talking to it. So hello, this is a programmer asking you to help me with the code that I am building for a rack system. Basically, it doesn't it does not have any idea about rack system from that particular document, so probably it will say I don't know. So yeah, it says I don't know how to help you with your rack system, as there is no relevant information provided about the code or the system you're building. The context appears to be related to related to accounting and financial reporting. And then if I ask, does it contain any maybe tutorials on explainable AI? So, so, so the content does not provide any explainable tutorials on AI. And then if I ask what is a RAG, it should say I don't know. So it does says I don't know, and then I have created my third session as well. So this is how you build a chat-based system in RAG, but the chat history is saved in the database here, and then you can extract that particular chat history anytime you want and then continue the conversation there.
Up until now in this series, we've been building retrieval augmented generation step by step. We started simple, loading a single document, splitting it into chunks, embedding it, storing it in a vector database, and finally querying it using an LLM. And that works, but only in very controlled scenarios. Because in the real world, information rarely lives inside just one document. Think about enterprise systems. Audit reports are stored separately, policies live in different PDFs, risk guidelines are in another file, and compliance rule exists somewhere else entirely. Now, imagine asking a question like, does the audit report violate the policy guidelines? A basic rack system cannot answer this properly because it only knows how to look inside one document at a time. And this is where things get really interesting. In this video, we are taking rack to the next level. We're building a system where multiple documents are embedded together. A single question can pull context from different sources, and the model can reason across documents to produce a combined, grounded answer. Even more importantly, the answer will not be a black box. We'll make sure that the system clearly shows which document the information came from, which page it was extracted from, and how multiple sources contributed to the final response. And this is the foundation of enterprise-grade RAG systems, the kind used in legal analysis, compliance tools, research assistants, and internal knowledge copilots. So, in this episode, you're not just learning another feature. You're learning how to move from toy RAG demos to real-world multi-document intelligence systems. So, without any delay, let's get started. So, for the implementation part, I have these two PDFs here. The first is ca.pdf, which contains node from computer architecture, and then the other is dl.pdf, which contains node for digital logic course. So I'm going to use these two PDFs to build this multi-document RAG here. And first of all, we'll start with import. So the first import is going to be from .env import load.env. Then I'm going to load the credential using this function here. I have some more imports to do. So from typing import list, and similarly from LangChain community document loaders, will import PyPDF loader. Again, from LangChain.TextSplitter, will import recursive character text splitter. From LangChain underscore Hugging Face, we're going to import Hugging Face embeddings. From LangChain Chroma, we will import Chroma. From LangChain core dot documents, we are going to import document. From LangChain core dot messages, we're going to import human message and a system message. Similarly, from LangChain core dot prompts, I'm going to import chat prompt template from LangChain underscore grok. I'm going to import chat grok, and finally I'm going to import OS to read the files inside this docs folder. Now the first thing that I'm going to do is load multiple documents. Now to do this, I'm going to mention the doc folder. So my doc folder is going to be the docs folder that I have created here, which contains 2 files. Now to load all the documents inside this doc folder, I'm going to create an empty list of document. For now, it is going to stay empty. Then I'll implement a loop. So for file in os.list directory from inside the doc folder, I am going to check if my file, if file dot ends with dot pdf, then I'm going to do loader equal to pypdf loader dot, or I can directly do this os.path dot join doc folder and file. Then I'll do docs equals to loader dot load. After this, I'm going to attach a document level metadata with this. So for this, I'm going to do for d in docs d dot metadata, and then I'll keep it inside the tag source document equals to file, and finally I'm going to add everything inside all document, and I'll do all documents dot extend and then put in docs. So finally, let me first print what I've done here. So loaded length of all documents pages from multiple documents. Now in step number 2, I'm going to split documents here. So for this, I'm going to create a splitter object using recursive character text splitter. Here I'm going to define the chunk size as 1000 and then a chunk overlap as 100. Now after this, let me define chunk equal to splitter dot split underscore documents, and then provide all documents inside this. And finally, I'm going to print how many chunks have been created. So total chunks created is equal to len chunks. Then after this, I'll go to step 3, where we'll create embeddings. So for embeddings, we'll use the same model that we've been doing for the past few videos. We'll use one from Hugging Face Embeddings, where the model name is going to be sentence transformers all mini LM L6 V2. Now along with this, I'm going to create a vector store. So for the vector store, I'm going to use Chroma, as I've already told you. So let me create a vector store object. So this will be Chroma dot from documents, and here I'm going to pass in the documents as chunks that I've created earlier here. Along with this, I'll pass in the embedding as our embedding model that we've defined earlier, and along with this, let me pass in a collection name So the collection name can be anything. I'll say multi-doc rag now. Then I'll create a retriever object using the vector store dot as underscore retriever. And then I'll pass in the search keyword arguments here. So search quirks will be, let me extract the top 3 result for this particular case, or we'll do top 4 results for now. Okay, now we move on to defining our LLM. So this was step 4. Now we move on to step 5, where we define our LLM. So for our LLM, we're going to use chat grok model. We'll be using the same llama model that we've been doing uh, since quite some videos. So llama 3.3 with 70 billion parameters and versatile model. For the prompt, I'm going to define a prompt object using chat prompt template. Chat prompt template dot from messages. And then first of all, I'm going to include a system message. The content of the system message is going to be you are an expert assistant. Let me do a multi-line string in this particular case. Okay, so you are an expert assistant. Answer only using the provided context. If multiple documents are involved, clearly mention them, and if the answer is not present, just say you don't know. So this is going to be my first system message here. Then I'm going to add one more human message. So in the case of human message, I'm going to pass in the context. The context will come from the context placeholder, and then the question will come from the question placeholder. So this will be my prompt for this particular video. Now what I can do is in step number 7, I can define my rag function. So for rag function, I'm going to declare a function, call it multi-document rag. I'm going to pass in the query here as a string. And then basically, we will use our retriever to invoke this query. Now, whatever content we get from the retriever, we are going to concatenate all of them into one single string here. So here I'm going to do dot join, and inside this, first of all, I'm going to connect what else? So my document or the source document will be mentioned as source.metadata.get, and as I had earlier provided it as source underscore document. Then what else? Okay, we're also going to add the page number from where we have extracted that particular document. So metadata, or we'll leave the page number for now. We'll just keep it as it is here. So just the document part. Then what else? So let me also add page content here inside this. I can make it multi-line document again directly. Then I will do d dot page underscore content, and then this will be for every documents in docs here. So this is going to be my context. After this, I'm going to invoke my prompt here. So prompt dot invoke, and then we said that we would provide these two values in case of prompt. So I'm going to pass in those two values here. So the first value is going to be, let me wrap it inside a curly bracket. So the first value is going to be context. The context is the context that we prepared here. Then along with this, I'll also pass a query or question. I think it's not a query, it's a question. So question will be passed as query that we've received in this particular function here. Now finally, I can invoke my LLM LLM.invoke using the prompt that I prepared here, and then I can return response.document. Sorry, it's content, not document. Content comma docs. This is the actual model response, while docs actually contains the source document metadata to help us understand where our result is being extracted from. Now finally, we will run our RAG application. So to do that, let me write a print statement here. So we'll call it multi-document RAG. Also, I'll present type exit to quit. Now, let me define an infinite loop while true. So query is going to be something that is going to come from the user. So I'll ask the query from the user here. Now, if query dot lower equals to exit, then I'm going to break it out of this loop. Or else, if there is a genuine user question, then I'm going to pass the query in the multi-document RAG function, and then basically get answer as well as sources from there. So my query is going to go to multi-document RAG function right here, and then I will get the answer as well as the sources for my answer here. Now what I can do is I can basically print the AI answer, and then AI answer is going to be answer that I've just retrieved. And then since that particular answer could come from multiple sources, so I can do for I comma D in enumerate sources, sources sources, and I can directly print let me do a multi-line string again here, or we can also do a single line string, it's fine. I'm going to do I plus 1 and D dot metadata dot get, and then source underscore document. Okay, so this is all for the implementation part here. Now we can run our code directly by calling Python rag for multi-document rag, and then see basically use the application, and then check whether information from multiple documents are retrieved or not. Sorry, I made a mistake here. I should have run this multi-document rag.py file instead of this above file here. Anyway, so they've loaded 231 pages from multiple documents. I think this document contains 130 pages, and then the CA document contains 101 pages. So yeah, total of 231 pages. The total chunk created was 486, and then I have this particular loop running here. So the user query is asked. Let me ask a very simple question about when is this particular computer organization and architecture as well as the DL subject taught here, basically in which semester. So if the model can provide me that particular answer here, then I think our objective is almost complete. So let me ask, in which semesters are computer organization and architecture and digital logic taught? So okay, what is this? So according to the provided document, digital logic is taught in second year first sem, which is correct, while computer organization is taught in third year and first semester, which is also correct. So yeah, the model is able to extract information from multiple documents and then combine them and basically provide our final answer. You can try many more questions inside this according to the PDFs that you have. You can upload any kind of PDFs inside this and then basically use your multi-document RAG model. So that is all for the demonstration or implementation of this video. So with this, we've officially crossed an important milestone in our RAG journey. We're no longer working with a system that understands just one document in isolation. We built a retrieval pipeline that can pull relevant information from multiple documents, combine that context intelligently, and generate answers that are grounded, explainable, and traceable. And this is exactly how real-world AI systems operate. In enterprise environments, questions almost always span between multiple reports, different policy documents, historical records, and evolving guidelines. And your RAG system must be capable of reasoning across document, not just inside one file. What you built in this video is the backbone of that capability. If you've made it this far, you've just completed a full end-to-end journey through retrieval augmented generation. Congratulations to you. In this single video, we started from the very foundations: document loaders, text splitting, embeddings, vector stores, and retrievers, and then gradually assembled a complete basic RAG pipeline. From there, we went deeper. We looked at explainable RAG, where every answer is backed by sources. We built conversational RAG, adding memory so that the system can understand context across multiple turns. And finally, we explored multi-turn document retrievals, showing how RAG scales beyond a single data source. At this point, you should have a clear mental model of how RAG actually works internally. Not just what to code, but why each component exists and how they connect together. And this is exactly the foundation you need before moving into more advanced agent-based and production-grade systems. In the upcoming videos in this channel, we'll take these ideas further, optimizing retrieval, handling complex user queries, and building more autonomous intelligent pipelines. If this video helped you truly understand RAG, make sure to subscribe to the channel, because the upcoming episodes in this channel builds directly on what you learned here. And if you found value in this deep dive, a like really helps the channel reach more learners like you. Thanks for watching. Thanks for staying till the end, and I'll see you in the next episode. Until now, in this LangChain masterclass, we've spent a lot of time building retrieval augmented generation systems. We learned how to load documents, chunk them, embed them, store them in vector databases, retrieve the most relevant context, and generate accurate answers from that data. And honestly, this is already extremely powerful. But there is a hard limit to what RAG can do. In all the systems we built so far, our AI was reactive. It waited for a question, retrieved some documents, and answered. That's it. But what if your AI needs to choose what to do next? What if it needs to choose between multiple tools, break a problem into steps, or even figure out whether it should retrieve data at all? And this is where RAG starts to fall short, and where the big concept in LangChain begins. In this episode, we're moving beyond information retrieval and stepping into agents. Yes, agents. You'll understand what agents really are and how are they fundamentally different from chains and RAG pipelines, and why agents are the foundation for building truly intelligent systems that can reason, plan, and act. No heavy coding yet. This episode is all about building the right mental model, because once you understand agents, everything you build next will make a lot more sense. So let's get started. Before we begin to talk about agents, let's clearly understand the limitation of everything we built so far. When we use chains or RAG pipelines, the flow is always fixed. Step 1 happens, then step 2, then step 3, every single time. The model never chooses the flow. We choose it. For example, in a RAG system, we already fix when to retrieve, how many documents to fetch, how to combine the context, and when to generate the final answer. The language model is only filling in the blanks. This works perfectly when the problem is simple and predictable. But real-world problems are not like that. Imagine a user asks a vague question, or asks something that doesn't require retrieval at all, or asks a question that needs multiple steps like searching, calculating, and then summarizing. With chains, we have to hardcode every possible path in advance, and that quickly becomes messy, fragile, and impossible to scale. What we really want is an AI system that can reason first, then identify, do I need documents, or do I need to call a tool, or do I need to ask a follow-up question, or can I answer immediately? Chains cannot do that, and RAG cannot do that. And this is exactly the gap that agents are built to fill. So in this episode, we didn't write code, and that was intentional. We focused on understanding why chains and RAG, as powerful as they are, eventually hit a ceiling. We saw that fixed pipelines struggle when problems become dynamic, ambiguous, or multi-step. And we realized that real intelligence doesn't come from hard-coded flows. It comes from the ability to choose what to do next. That realization naturally leads us to the next evolution in LangChain. In the upcoming episodes, we'll start working with agents, systems that can reason, choose tools, take actions, and adapt their behavior based on the problem in front of them. We'll move from pipelines to decision-making systems, and step by step, we'll build agents that feel far closer to how real intelligent assistants should work. This isn't the end of RAG or chains. It's the foundation they stand on. And in the next episode, we'll officially enter the world of LangChain agents. So I'll see you in the next video. Up until now in this masterclass, we've been building systems that follow a path. We designed prompts, created chains, added retrieval, added memory, but at the end of the day, we were still telling the system exactly what to do. In the real world, that's not how intelligence works. Intelligence is not just about responding, it's about choosing what to do next. And this is where LangChain takes a big leap forward. In this episode, we're moving away from fixed pipelines and stepping into something far more powerful: agents. An agent doesn't just answer questions, it reasons, evaluates the situation, decides whether it needs a tool, and then takes action on its own. No hard-coded logic, no if-else flows. Just a language model that can think, act, and respond. In this video, we'll build our first LangChain agent from scratch, starting simple, understanding every moving part, and seeing how tools transform an LLM into an autonomous choice maker. This episode is the foundation for everything that comes next: planning agents, RAG-powered agents, memory-driven agents, and eventually fully autonomous AI systems. So if you've been wondering when LangChain really starts to feel intelligent, this is the episode where it begins. Now we'll see the implementation and then explain some new concepts in this implementation after we've done this. So from
.env import load.env. This will load our API keys from .env file. Then from LangChain underscore grok import chat grok. From LangChain dot tools import tool. From LangChain dot agents import create agent. First of all, I'm going to define my LLM, and my LLM will come from chat grok. I'm again going to use the same model that I've been using since past many videos in this series, which is the llama model. Then I'm going to define few tools here. The way to define a tool is mark it using @tool, then create a function for it. So the first function is multiply integer b integer, and then it will again return an integer. We'll write a docstring for this. So what this basically does is multiply two numbers. I can directly return a into b. Then I'll add one more tool here, which will be def add a integer b integer, and it will again return an integer. So add a docstring, add two numbers, and then return a plus b. So these are the custom tools that we will provide to the LLM for our tasks. So I have two tools, add and multiply, which I'm going to keep it inside a list. Then what I'm going to do is I'll write a system prompt. The system prompt will say I'll do it a multi-line string. You are a helpful AI agent. Use tools when necessary. If no tool is required, answer directly. So this will be my prompt, system prompt. Now instead of directly invoking the LLM, what I'm going to do is I'm going to create an agent. So I'll call this create agent function from LangChain.agents. I'll define my model. My model will be the LLM that I have implemented here. Then I will also provide the access to tools that it has, these particular tools, and then I'll provide a system prompt. Now this will be our system prompt. Now finally what I can do is I can run this agent here. So for a continued conversation, I'm going to do LangChain basic agent, also print type exit to quit, and then add a line break here. Now let me run an infinite loop. While true, I'll ask user query here. Further, I'm going to insert a condition to break out of the loop. So if user input dot lower equals to exit, then I'd like to break out of the loop, or basically end the conversation. Now if there is a genuine user query, then I would like to invoke the agent. Response equals to agent dot invoke, and while invoking the agent, I'm going to create messages. Now this will be a list of
First of all, I'm going to add a human message. So role user and content will be user underscore input. Now finally, if I want to print out what exactly the AI response is, I can simply do AI response and then append it with response. Inside response, I'm going to go for messages. Inside that, I'm going to go to the last message that I have and then print out its content. Else, what we can also do is we can also check out the entire response that we get from the agents. So AI agent debug mode, and here what I'm going to do is I'm going to print out my response and finally insert 2 blank lines here. So my code implementation is now complete. I can directly run this code, and while I'm running this code, I'm going to explain what did I exactly do here. So Python 12 agents, 1 tool calling agent.py. The project is already running, but at first I'd like to help you understand tools here, because tools are what a language model or tools are basically those components that convert a language model into an agent. So by default, a language model can only generate text content, right? So it cannot reliably do calculations, call functions, or interact with external systems. And that is where tool comes in. So a tool is a simple Python function that we expose to the language model, so the model can choose when to use it, which tool to use it, and what arguments to pass. So in our code, we have implemented tool using this particular @tool decorator, and first we've created a multiply function. It basically takes in 2 integer and then returns their product. Then we've also created an add function that adds 2 numbers. The important part here is not the math, but it is the metadata. By using this tool decorator, LangChain automatically extracts the function name, reads the doc string that is provided here, and then infers input parameters and the output type. So that information is what the agent later uses to reason, like should I answer directly or should I call one of these tools in order to answer the query. After you've implemented the tools, so we've grouped them into a list here, basically a tools list, and that list is what we pass to the agent, specifying it that those are the capabilities you're allowed to use. Now we see the system prompt here. This is extremely important. The prompt sets the behavior rule for the agent. Here we're telling it very clearly, use tools whenever you're needed. If no tools is required, answer directly. So this instruction guides the model's choice making process. Without this, the model might ignore tools or maybe not call them at all. Now comes the most important part, that is create agent. So the create agent function is where everything comes together. We pass 3 things inside this. First the language model, then the tools, and then the prompt that we've written above. So what create agent does internally is it creates an agent loop. It also enables tool calling, and it manages reasoning, tool execution, and final response generation. So in other words, this function turns a normal LLM into an autonomous choice making system. So the agent now follows this loop. So it basically reads the user input. It chooses whether a tool is required or not. If yes, it calls a tool with proper arguments, and it basically observes the tool output and then generates the final answer. And all of this happens automatically. Now, inside this loop here, we send user input to the agent using
the format here. Here we are explicitly passing messages in chat format. This makes the agent compatible with multi-turn conversations later on. And the response we get back contains all the intermediate reasoning, tool calls, and final output. And that is why we print the particular part only. So that gives us the final answer generated by the agent. Also, to see the full response in debug mode, we've actually implemented a print statement here where we can see which tool was called, what arguments were used, and how the agents reasoned internally. So now we are going to run this. So I'll say, hello, what is your name? So if we see the response, the AI says that I don't have a name, but I'm here to help you with any questions. So if you see the entire response part, you don't see any tool calls inside this here. You directly see an AI message content, the completion tokens, the prompt tokens, total tokens, and things like that. Now if I add, what happens when you add 4 balls into a collection that already contains 5 balls. Now this is basically an addition problem. We'll see if the language model understands the addition scenario and then calls the tools or not. So if we run this now, you can see that when you add 4 balls into a collection that already contains 5 balls, the total number of balls in the collection becomes 9. Well, the large language model can do this too, but I would like to check whether this is done by the LLM itself or by the tool calls that or by the tools that we have implemented here. So if you see here, you see that there is a tool call, we have a function, the arguments 4 and 5 balls are basically passed to A and B in this particular add function, and then the name of the tool that is called is add. So this particular computation or this particular answer is being generated from this tool here and not by the large language model itself. The large language model is taking the help of this tool here. We'll do one more thing. This can also do subtraction. Now if we have a collection of 5 balls in a basket, and if we remove 3 balls from it, how many balls are there now? So again, for this too, it does call the same add function here, but in terms of parameter, the total balls previously were 5, and then we remove 3 balls, which means the parameter B takes the -3 value, and then it basically calls the add function, and we get our result. There are 2 balls left inside the basket. So the large language model is in fact using these tools that we provided to it to answer our particular query, understanding the semantic meaning of our query here. We'll do one more for multiplication. So tell me the product of 10 and 2. It should understand that it is a multiplication problem, and it does. You see tool calls, so we get arguments 10 and 2, and then the function it calls is multiply. So this is how we have now turned our agent, we've now turned our LLM into an agent where it can reason whether to call a specific tool to solve a problem or whether to do it on its own. And that wraps up our first hands-on look at building a basic LangChain agent from scratch. We've seen how to define tools and expose functions to the agent, guide the agent with a system prompt, and use create agent function to bring the model and tools together into a single autonomous reasoning system. But this is just the beginning. From here, we can expand our agent to handle more tools, incorporate memory for multi-turn conversation, and even combine agents with RAG system for intelligent retrieval and choice making. So in the further episode, we'll explore these possibilities and see how to build smarter context-aware agent that can tackle real-world tasks seamlessly. So stay tuned because things are about to get even more powerful, and I'll see you in the upcoming video. Hello everyone, welcome back to Learning Hub. Today, we're going to build something most people talk about, but very few actually engineer. We're going to build an LLM that judges another LLM. Not in theory, not with benchmarks on slides, but end to end in code. And by the end of this video, you'll have a working system where one LLM generates an answer, another LLM evaluates it for accuracy, relevance, and hallucinations, and if the answer isn't good enough, the system tries again automatically. Think of it like a continuous integration pipeline, but for AI responses. This is the same core pattern used in AI evaluation pipelines, agentic systems, and modern production AI stacks. We'll start simple, build everything step by step, and by the end, you'll clearly understand how a real AI system evaluates themselves at scale. No prompt hacks, no theory only talk, just clean practical engineering. So let's get started. But first, I'll show you a very real problem. So there is a user who asks an LLM a very simple question. The answer it gives sounds confident, it's well written, and at first glance, it looks correct. Now, here's the issue. The answer actually provided by the LLM is wrong. Not obviously wrong, not broken English, but factually incorrect in a subtle way. And that is exactly where things break down. Now, because I'm just one person watching this video, I can catch that error. But what if you're generating thousands of answers per day, or you're running RAG pipelines, or you're building agentic systems that act autonomously? At that scale, you cannot read and judge everything manually. So, what are the usual options? Well, one can be human evaluation, but human evaluations are too slow, too expensive, and they do not scale. And traditional NLP metrics like Blue or Rogue could be another alternative. Well, they just compare text similarity, they don't measure correctness, and they completely miss hallucinations. So we're stuck with a serious gap here. We have models that can generate language extremely well, but no reliable way to judge the quality of that language at scale. And that's why this pattern exists. Instead of asking, how do I measure this answer numerically, we ask a different question. Can another LLM judge this answer the way a human would? And that is the idea behind LLM as a judge. And in the next section, we're not just going to overthink it, we'll build the simplest possible version of this system, just enough to make the idea concrete. So we'll start with the project skeleton first. So I have already created a fresh project folder, and inside it I've set up a virtual environment. This keeps everything isolated and reproducible, which matters a lot once systems like this move into CI pipelines. You'll also notice a few things already in place. First of all, I have a .env file, and this is where my LLM credentials will live. Nothing is hard-coded in the code base. Next, there is a requirements.txt file. All the libraries we'll use will be declared here, so the environment can be recreated exactly anywhere. And finally, the core structure of the project: main.py, judge.py, and prompts.py. So the separation here is intentional. Main.py will act as the orchestrator here. Judge.py will contain all evaluation logic, and prompts.py will keep our prompts explicit and reusable. So nothing here is complex, and that's the point here. Before building anything smart, we want the foundation to be boring, predictable, and clean. So with the environment ready and the structure in place, we can now build the first real component of the system, an LLM that simply answers a question. No judging yet, no improvement loops, just raw generation. So let's do that next. At first, in the requirements.txt file, I would like to include these libraries: LangChain, LangChain Grok, LangChain Core, LangChain Community, and Python.env. Now with this, let's install these libraries inside our virtual environment. Now that our requirements are installed, we'll now move to main.py. So in main.py, we're going to write a simple function that takes a question as an input, sends it to our model or LLM model and returns the raw answer. Nothing fancy, just generate and print. So here, at first I'm going to do from LangChain underscore group import chat group from LangChain dot underscore core dot prompts import prompt template, and from .env import load.env. Now, first of all, we're going to load our credential. After this, we're going to define our LLM. So LLM is going to come from chat grok, where the model name is llama 3.3 70B versatile. So this will be our LLM. So here I'm going to define a function called generate answer. We'll pass in the question. The question will come in the form of string, and then answer will also be in the form of string. We have a separate file called prompts.py. Here we're going to define our prompt. So from LangChain underscore core dot prompts import chat prompt, or we'll just do prompt template for now. And inside this, I'm going to define my question prompt. So question prompt will use prompt template. Here the template will be defined as answer the following question as accurately as possible, and I'll also provide the question here in the placeholder. And along with this, I need to define my input variable. So input variables is going to be the question. So in our main.py, instead of importing this, we will do from prompts import question prompt. And now here I'm going to use my prompt from question prompt dot format, and then I'll pass in the question as question here. And finally, I will pass in this prompt to our LLM, and then generate a response. And then we can now set our question. So the question can be, what is the capital of France? And then basically call the so answer equals to, let me correct this, answer equals to generate answer. Call this function and then pass in the question here, and then I can just print answer dot let me do response dot content here, not just response, and then I can basically print my answer here, which will be the generated answer. Or let me just do generated answer. We're going to do some few minor corrections here. So in this place, we're going to add question equals to question. And one more error I noticed is here we have to invoke an LLM, so we're going to add an invoke function here. Now we can run our main.py. So let's run it. And now we can see the answer that the capital of France is Paris. So this is a very simple workflow where we provide a question to an LLM and then we get an answer from the LLM. But now comes the part that makes this system really interesting. We have an LLM generating answers, but sometimes this answer can be wrong, incomplete, or hallucinated. Now, how do we evaluate them automatically? So the answer here is to design a rubric. So think like a human evaluator. We can judge an answer along three axes. The first is accuracy. Is the answer actually correct or factually correct? The second is the relevance. Does it actually answer the question? The third is hallucination. Are there any fabricated details? And fourth is clarity. Is the answer easy to understand? So we'll convert this rubric into a structured JSON object so the system can read it easily. So now we'll go to prompts.py and then we're going to add a judge prompt. So judge prompt. I'll again do prompt template. The template is going to be, so you I'll just do multi-line content here. So you are an expert AI judge. Evaluate the following answer to the question. So I'll put a double line break here, and then I'll add question. So the question will be placed in our question placeholder. I'll put a line break again, and then I'll also provide the answer. The answer will be inside this answer placeholder. I'll again put two line breaks here. Then I'll say assess the answer based on the following criteria. Now I will define the criteria here. The first is going to be accuracy. So let the accuracy be defined from 0 to 10. The second will be hallucination. We'll do true or false for this, true or false. And then the third here can be added as a feedback, where we'll ask for a brief comment on the answer here. So this is a judge prompt. And finally, we're going to say return your evaluation as a JSON only. Now, along with this, I'm going to add two input variables. So my input variables will be question and answer, ANSWER. So these two placeholders will be placed in my input variable. Now I have one more file called judges.py. So I'm going to go to this file and then import. Again, I'll be using the same model here, LangChain group. So import chat group, and then from prompts I'm going to import judge prompt. So let me define the model here. So judge LLM is going to be our llama model again. Model name equals to llama 3.3 70B versatile. We will then create a function to evaluate our answers, which will take in two parameters. The first parameter is the question, which will go in the form of string, and the second parameter is the answer, which will also go in the form of string. And then this will actually return a dictionary type object. So the prompt here will be generated from the judge prompt, not question prompt. So judge prompt dot format. Since I have two different placeholders, so I need to pass in both question and answer to this judge prompt here. So the question will be question, and the answer that I'm going to pass will be the answer that I get in the function parameter. So with these two, this is the answer, right? Yeah. So with these two, I'm going to invoke my judge LLM. So judge LLM dot invoke prompt And here I will try to parse the JSON output that I get from the LLM. So let me include one more import. So import JSON. And with this, what I'm going to do is I'm going to do everything inside my try except block. So try except, and then here let's do JSON decoder error, JSON decode error. So here let's do evaluation equal to JSON dot loads response dot content, or else if we get an error, then we're going to create our own evaluation response here, where we'll say the first value is accuracy that we want. So accuracy is 0, hallucination is true, and basically feedback will be judge output is not a valid JSON. So whichever response we get, either inside from the try block or inside from the catch block, we're going to return this evaluation term, return evaluation. So now let me simulate this judge.py with my own question and my own answer. So if the question is what is the capital of France, and if I provide my own manual answer saying that it is Berlin, obviously it's not. So let me see the evaluation done by the model. So evaluate answer. Let me pass in the question as well as the answer here, and then basically print evaluation result and print out the result. So now let's run the evaluation or the judge.py pipeline here, and then see if the defined evaluation flow works or not. And if it does, then how does it evaluate the response? Oh, so I forgot one more import here. So from .env import load.env and then load the credential for chat grok using a load.env function. Okay, so it told me that the evaluation result is exactly wrong, or the judge output did not give me a valid JSON here. So let me see what the model printed out first. So response dot content, and why it is not providing me the exact JSON format. The model did try to give me a JSON. Anyway, the evaluation of the model is also correct. Based on the answer that I provided, it says the accuracy is 0, hallucination is true, and then the feedback, as Berlin is the capital of Germany, not France, the correct answer is Paris. So we'll try to fix this output to be returned exactly as JSON here at first, and then we'll move on to the next part. In order to fix this judge LLM output, we're going to add one more library called Pydantic here. So let me just do pip install Pydantic, or you can install it from requirements.txt too, that's fine. And once this library is installed, let me go to prompts.py and then add something more here. So the first thing that we're going to add is from Pydantic, we will import base model as well as field. Now what we're going to do is we are going to define the schema of what we exactly want back. So for that, I'm going to write a class call it evaluation, provide base model as its parameter. Now the first thing that we want is an accuracy, and then accuracy has to be in integer, and then in the field we can say a bit, or we can provide a bit of detail in what we want in accuracy. So we want to score from 0 to 10, where 10 is highest or best score. Then we also want hallucination parameter. So this is going to be a boolean parameter here. So bool, and in field we can say, or we can write the detail for this, description equals to true if the answer is, or the answer contains hallucination, except, or we'll do else false. And then finally we also need a feedback. So for feedback we'll do string, and in field we will detail it out as description. This is going to be something like brief comment on the quality of the answer. Now whenever we use such a schema, what we want to do is, wherever we've defined our judge LLM, so let me go to okay, we don't define it here inside prompts. We're going to put it in judge.py. Okay, I'll just copy this out from here. So this will be in judge.py, and then my evaluation class will also be just above the judge LLM here in judge.py. So what we're going to do here is we're going to convert this judge LLM into structured judge LLM, and then we'll do this using judge LLM dot with structured output, and then pass in the evaluation class here, evaluation class. And finally, before we can call our model, we don't call it with judge LLM, but instead we're going to call it with structured judge LLM. And once we do that, we don't need to do any of this, because our response will directly be in the format that we require. So we can directly remove this and then just print out the response. So now we'll see what it does. So Python judge.py. Let me save the prompts part too, because there is some changes that I've made here. Okay, so the evaluation result here is accuracy is 0, hallucination is true, and the feedback is incorrect answer. Berlin is the capital of Germany, not France. So this works quite well for our judge.py. Now what we want to do is, we don't want to do everything here separately for main.py and judge.py. We want to connect both of them into a single system. So let me comment this out in case of judge.py, and then just use this function as well as the other content here. So what I would also like to do is define this inside my evaluation function, so that every time evaluation is called, these two objects are also initialized and then used here for evaluating answer. Now let's go to main.py. We already have this generate answer function, which is quite good for us and then working well for us. We'll import one more thing from judge import evaluate answer. We save this. So from it is evaluate answer, right? Yeah. So from judge we'll import evaluate answer. And here, instead of passing it in this way, we're going to define a list of questions. So these questions can be, what is the capital of France, like I did earlier. Next question can be, who wrote the book Harry Potter. And then one more question can be, name the largest but dense city in the world. So these are the three questions. So what I can do is I can loop across each question for question in questions. So I can generate answer first for each question, and then let me print out the question here. So the question that I've asked is question. The answer that we get can also be printed here. So answer is answer, and then we will send this to evaluation. So we'll write evaluation, evaluate answer, and then we'll pass in the question as well as the answer to the evaluate answer function. And then based on that, we're going to see the evaluation that we get from the judge here. So just to evaluation, and then we'll add 2 line breaks so that we'll kind of see this separator here. Now I can directly run main.py as everything is saved. So for the first question, what is the capital of France? The answer we got here was that the capital of France is Paris. The evaluation model judges it as highly accurate, hallucination is false, and then the feedback is correct answer. Then yeah, the next question was, who wrote the book Harry Potter? And then we got the answer from the model that Harry Potter was written by J.K. Rowling. She's a British actor, and then something else. The evaluation said that it is correct. It is not hallucinating, and then the answer is correct or accurate and provides relevant additional information about the author and the series. And then when I ask name the largest bird density in the world, so it says the largest but densest city in the world is Manila, the capital of Philippines, and then it provides additional answer. But if I see the evaluation, the accuracy is 9, the hallucination is false, and then the feedback is the answer is well researched and provide accurate statistics, but could be improved with more comparative analysis of other densities. That right there is the core pattern used in real AI systems. It's simple but powerful. Generate and evaluate. So you generate an answer and then the judge evaluates it, and then based on that evaluation, the system chooses the next step. So you can plug this pattern into all kinds of AI workflows, RAG pipelines, agentic systems, or even automated AI testing workflows. And the really beautiful part is that the judge itself is an LLM, just like a generator. That means we can scale this evaluation process without needing humans to check every single answer now. And now that we have an LLM generating answers and a judge evaluating them, let's make the system self-improving. So the idea is simple here. Generate an answer, send it to the judge, and if the score is below a threshold, then regenerate the answer and then judge again, and repeat the same step until the answer is acceptable. And that is basically reflection in action. The model or the LLM learns to correct itself without a human in the loop here. So for that, we're going to make a minor change in our code here. So here I'm going to add a function. Let's call it something like this. So define ask until good. Here I'll pass in the question, which will be in the form of string. I'll now define the threshold. Let's write down the threshold at score as 8. This will be in the form of integer, and then we'll also do max attempts. So we cannot send it into an infinite loop, so we'll do max attempts equals to 3. So at first we are at attempt 0. Now we will run this while loop. So while attempts is less than max attempts, okay, I made this spelling wrong here, so max attempts. So when this is true, what I want is the model to generate an answer. So generate answer for the question and then pass it to evaluation. So evaluation, or what I can do is I can just do this step here. So I can just copy these steps out. So print question, print answer, evaluation, and then print evaluation. Now here, if the evaluation score evaluation dot get, and then I want to fetch in the accuracy where the default value is 0 is greater than or equal to threshold, and then we don't find hallucination. So evaluation dot get hallucination. Okay, what do we get in hallucination, true or false? Let's see. Okay, so we get a capital false. So by default the value is true. If we don't get this, then we print the answer meets the threshold, no correction needed, and then we'll just print out the final answer as that particular answer here. Include 2 blank lines. But if this is not the case, then we'll say that the answer is below threshold, and then we'll say regenerating, and then we'll do attempts plus equals to 1, and then basically repeat the same loop again. So I'm going to add a very controversial question here. So I'll just write is Israel trying to invade Palestine? So a kind of a controversial question, which exactly does not have a fixed answer here, because the AI model obviously does not know the motive behind all of that has all of it that has been happening here. So here I'm just going to do what else. So for questions in question, I'll just call the function ask until good and then pass in the question here. So yeah, it looks to be correct, and then I can just run this. So Python main.py. I have made slight correction in this code. So in place of evaluation.get function, we can directly use accuracy since we are using Pydantic model, and then evaluation is the response from that particular Pydantic model. So we can do accuracy as well as hallucination. So I've already run my code, and then you can see that for the first question, what is the capital of France? The answer is the capital of France is Paris. The evaluation is accuracy 10, hallucination is false, and the feedback is that the answer is accurate. So answer meets the threshold. No correction required. And then for the second question, the answer is correct, as well as it provides the relevant information. The accuracy is 10. So again, it meets the threshold. So no correction is required. And then from the for the third question, name the largest word density in the world. Again, the accuracy is 9, hallucination is false, and then the feedback is the answer is well researched. So again, no correction is needed. And then for the last question, is Israel trying to invade Palestine? Well, it provided some history as well as some major characteristics of the situation, and then in the feedback we can see that the accuracy is 9, the hallucination is false, and then the feedback is that the answer provides a comprehensive and balanced overview of the Israel-Palestinian conflict, but could benefit from more concise language and a clearer structure. So again, no correction is needed. But if the threshold or the accuracy threshold or the accuracy score was below this threshold score of 8, then it would have regenerated the answer again, and then evaluated it again by the LLM itself. Hence, we now have a full loop generation, evaluation, as well as improvement, a miniature agentic AI. Now that we've built a working self-improving LLM system, let's step back and see why this matters in real-world AI. So what we just built is a miniature version of patterns used in production AI systems. The first, RAG evaluation. So when combining retrieval with generation, your system needs a way to judge if the answer actually makes sense. The next is agent decision gating. So autonomous agents don't act blindly. They generate, evaluate, and then choose based on the feedback. And the large teams are now using LLMs to automatically test other LLMs in pipelines, just like unit test for code. And then we can also compare answers from multiple models to pick the best one automatically. So whatever we built today isn't just a toy. It's the same core idea that powers evaluation. Before we wrap up, it's important to be realistic about what we've just built. Even though our system can generate, judge, and self-improve, there are engineering truths every AI developer should keep in mind. The first one is the judge bias. So the judge LLM is trained like any other model. It can favor certain phrasing or make mistakes, and not every high score is truly accurate, and human oversight is still needed for critical applications. The next is the cost issues. So every evaluation calls an LLM, and scaling to thousands of answers can get expensive very quickly. So you need budget planning or caching strategies for this. The third is the prompt overfitting. So if the judge prompt is too rigid, then the system can game the evaluation. The LLM might generate answers that look good to the judge but aren't factually correct. And then the last one is the humans in the loop necessity. So some cases cannot be fully automated. So engineers often combine automated judging with periodic human checks here, which ensures quality and prevents subtle errors from going unnoticed. And being aware of these limitations is what separates a good AI engineer from someone who blindly trusts model output. And respecting the boundaries of automation is the key to building robust systems. And that's it. So today we built a full LLM system that generates answers, evaluates them, and even improves itself automatically. We started from a clean project skeleton, built a generator LLM, designed a judge with a clear rubric, and connected everything into a self-improvement loop, a miniature version of what real AI systems do in production. Take a moment to appreciate what we've done. We've done structured evaluation, we've done automatic feedback, and then we've done agentic behavior. And even with a simple setup, these patterns show how LLMs can be used to think about their own answers and reflect on their outputs. So if you enjoyed this hands-on engineering walkthrough, give it a like and share your thoughts in the comments. I'd love to hear what questions you tested with your judge and any surprising answers you saw. And finally, remember, automation is powerful, but understanding the system is what makes you a good AI engineer. Thanks for watching, and I'll see you in the next video.